which is explained mainly because of the higher chemical yields. Anyway, both this case yielded from 15 to 20% rate of return, which is quite impressive for such a configuration. Okay, so everything I've presented now was corresponding to greenfield projects. But what's even more exciting is the potential for brownfield expansions. In our current era, our sector is facing some very much to invest and to expand in order to remain competitive. And such technology, such configuration will play a key role. In such configuration, we're able to reuse all the, let's say, low-value streams from the existing complex within the new complex.
And now our next speaker is Mr. Abhijit Paul from Honeywell UOP. He would be touching upon the topic on improving ethylene profitability, the paradigm-changing UOP NEP process. Mr. Abhijit.
Thank you. Good morning, everyone. And thank you, the chairs and our fellow panelists. A special thank to CHT for providing this opportunity to talk in ETM. We oldies still call it as RTM because that's where you heard about that refinery technology meet. So it's always nice to be here and meeting fellow colleagues, and those might have, we might have went to a different route, but meeting here, it's always give a nice pleasure. And today I'll be talking about NEP. It's a paradigm changing process. And Mr. Greg Funk, he was supposed to present here, but because of the business requirement, he could not. So I'll be presenting on his behalf. And this one, those who attended yesterday, Mr. Keith Couch talked about NEP in his presentation it was more as a trailer, and now probably we will show you the full picture of NEP. But before that, let's give some clarification of the legal requirement that this presentation will have certain forward-looking statements with certain assumptions which may or may not be applicable in all the cases. So yesterday we talked about various parts of various issues of the petrochemicals. This session is more about petrochemicals. Let's just see about what is the key growth potential in the petrochemicals. There are two specific areas, two light olefins, which is ethylene and propylene. And if you can see this slide, that both ethylene and propylene, both the demands are expected to grow across various regions, very specifically in India and China. The expected growth rate predicted to be around 3%. And that's not end of the story. Like yesterday, it was also mentioned that there are always focus on improving the efficiency, moving to the latest technologies. And there is a chance that there may be those older crackers might close down and people might move to a newer cracker, more efficient one. And this probably will increase this demand by not 3%, but it may be 6%. That's the best case scenario. So definitely there is an increase in the both these light olefins, both in the ethylene and propylene demand. But it also comes with certain, but this light olefin industry also comes with certain challenges. Now there are two types of crackers you all know. One is the naphtha cracker, one is the ethane cracker. Now naphtha cracker, I mean most of our, in the Middle East and in India, a lot of naphtha crackers are there. Those are very high capacity, but it comes with a certain disadvantage of a higher cost feedstock, low olefin yield and higher capex, resulting in the lower ROI. The alternate is the ethane cracker, which definitely is better ROI. Unfortunately, the supply is limited, and I think it was also mentioned by Mr. Rajiv Agarwal just now, that this supply and uncertainties of the supply because of the geopolitical reasons makes a lot of challenge in the ethane. On the other hand, for the liquid naphtha, the demand for liquid fuels are declining, so it is possible that the feedstock may be less, maybe easier available for the liquid cracker. But with the focus on the sustainability, again, light liquid crackers or naphtha crackers is in a disadvantageous position. So there is a lot of these challenges which comes in the light olefins industry. So essentially what is required is an improved approach to light olefins production. And that's what we will talk about. But before moving that, let's talk about and dig a bit slightly deeper on the feedstocks. And if you see these two curves, and this talks about this feedstock, talks about both propylene and ethylene. And a very logical that ethane, the most efficient feedstock for ethylene is ethane. You get a maximum amount of ethylene and minimum amount of byproducts. And the same thing is true for propylene. So if you use propane and go through propane dehydrogenation route, you get the best yield of propylene and minimum of the byproducts. So essentially, both this ethylene and propylene, if you want to improve its yield and reduce the byproducts, the best feedstock is ethane and propane. And NEP addresses this specific area where it converts the naphtha to ethane and propane, and that's the beauty of NEP. And it becomes the most efficient feedstock. And it comes with a very simple chemistry. Okay, now we'll introduce NEP a bit. If you see, it's a relatively simple process where we have a NEP process unit. Generally, the lighter feedstock is provided as a feed, and then it converts those naphtha to ethane and propane. It can be tuned, and this ethane and propane then subsequently is separated, and separate ethane can be put as a feed to the ethane cracker. The propane, it's an optional product, can be put to the propane dehydrogenation. And ethane gives ethylene. Sorry, my apologies. And ethane gives ethylene, and propane gives propylene. Now, this is a highly tunable, and the overall olefins production is pretty high. It's in the range of around 80%. It has a much less methane and also pretty much less pi oil or pi gas. I don't know what's going on. Not sure. So how it benefits? So NEP in comparison with mixed feed cracker, because of the efficiency and because of the feedstock, it increases the light olefin yield significantly, which is around 50% to 70%. And it obviously reduces the cost of production, which results in increasing the operating profit. It comes with a lower capex, and capex per metric ton of olefins also reduced significantly, which is somewhat in the range of 30%. And here there is a high feedstock flexibility. This NEP is isotolerant. Essentially, in naphtha cracker, it's sensitive to iso. So if you have a feed, you have an iso component instead of normal component in the feed, the yields are slightly less. And NEP addresses this issue. So NEP is isotolerant. And overall, the CO2 intensity is much lighter, much improved. And one specific thing which I have not mentioned, but here it is now, this is highly tunable. So there is a wide range of ethane to propane we can produce by tuning the reactor parameters. And that becomes a very, very unique value proposition for NEP. And that is the reason we are talking this NEP technology as a game changer in the light olefins. So how does this tuning of ethane and propane helps? So if you see that there are various customers will have a different need. Somebody would need ethane only. So there are the refiners, or there are the processors, they need more ethylene or more ethane. Those ethane-starved customers will definitely benefit from NEP by addressing this ethane gap. If it is suppose if it is a grassroots and greenfield project, there they might not have fixed it. They might need both ethane and propylene, ethylene and propylene. Yes, that also can be done with using the NEP. Again, there may be in some cases, customer might have to balance between natural gas liquid and LPG, and then the ethane supply. That also is possible, again, to utilize this ethane only mode. So this is a specific case where option is there with the customer. I mean, think about those cases, like if those options are given, it's always better because that option helps you to actually invest whatever you actually require. You need not have to over-invest anything. So NEP has this potential to meet a variety of industry needs. Here we will show two case studies. The first case study will be on item number 1 and 2, where it addresses this ethane gap. It addresses a brownfield application. And we will also give one case study for a case which is a greenfield application, where you need both ethane as well as propane. So the first application here, the customer wanted to optimize the existing cracker. The problem statement they had is they want to reduce their propylene production because the propylene market, because of the overcapacity in China, is really in a dire need, and a lot of extra capacity is there. So they want to reduce the propylene. They want to increase the ethylene, and they have a flex feed furnace where it can take both naphtha as well as ethane. So this is the problem statement we came up with to have a discussion with the customer. In the left-hand side, you see what is the configuration for existing mixed feed cracker. It has two dedicated liquid furnaces. It has two dedicated gas furnaces. The gas furnaces are fed by propane. The dedicated liquid furnaces are fed by naphtha. And then it has two flex furnaces. It can have both naphtha as well as a liquid as well as gas. And that also they are utilizing naphtha. In the revised configuration, what we suggested is to reduce naphtha or remove naphtha from one of the flex furnaces, use the NEP, divert this naphtha and some extra naphtha to this NEP, produce ethane, and that ethane then get fed to these two flex furnaces, and then the propane goes as usual to the gas furnaces. So this is the change which we have suggested. So here the NEP was tweaked to meet this ethane production, and essentially what happened is they have to shut down naphtha to one of the furnaces, added some more more naphtha, which around 800 kMTA naphtha has been fed to NEP unit, and this provided a ethane of around 625 kMTA. What it resulted with this tuning? It resulted in an increase in the propylene by around 300 kMTA, whereas the reduction, increase in ethylene is 300 kMTA, and also resulted in reduction in propylene as well as reduction in pipe gas or pipe oil significantly. And the best part is it is a low cost modification. Here there is no big ticket item to change on the naphtha cracker. Yes, the lightens, the separation section need to be worked out. Obviously there will be the challenges, but this gives a very nice IRR of around 20% with a total investment of 300 million. So it gives a very, very nice what the customer needs, a solution fully catered to the need of this particular customer. The second one will be on, coming to this second case, this is on the, this is a greenfield project. In this greenfield project, the customer wants, it's a bit, if you see the API, it's a bit lighter crude. And the objective here is maximize the polyolefins, but customer has not fixed what ratio they want ethane and propane. So they are flexible on that. But one thing they are clear, that they don't want too many byproducts, especially on pie oils and all the stuff. And obviously they want to maximize the ROI. So here it shows two solutions. One is the conventional crude to chemicals, very typical one. It's a simplified, and you have from the crude, you have a gas separation plant, you have a hydrocracker, and then the product goes to the mixed feed steam cracker. You have polyethylene, we have polypropylene, you also have pie oil and pie gas. Our suggestion here is to convert this hydrocracker, I mean, not convert, it's a greenfield. So this hydrocracker is configured as a advanced hydrocracker, which gives only LPG and light naphtha. And then all this LPG and light naphtha is fed to the NEP unit. NEP produces the ethane and propane based on the whatever the tuning factor is. And then the ethane is sent to a ethane cracker instead of mixed feed cracker, and the propane is sent to a PDH unit. As I was telling in the a couple of slides back, that if you get ethylene from ethane and if you get propylene from propane, you minimize your byproducts, and that is what we are seeing it here. And if I compare the yields based on whatever we did the study, so on conventional crude to chemical complex, where the polyolefins yield was about 50%, around 53%, and the pi oil plus pi gas is around 35%, with a E to P ratio of 1.8. Now, here E to P ratio is why important that it's a fixed E to P ratio. You cannot change it. On the other hand, when you go to the NEP based crude to chemicals, you can have a higher polyolefins yield. It's in the range because we have looked into 3 different scenarios because the customer did not fix on ethane to propane ratio. We looked into high E to P ratio, mid E to P ratio, and low E to P ratio. E to P, ethane is to propane ratio. And the total polyolefins, total E to P comes out to be somewhere between 83 to 86%. Here you directly get the aromatics. Yes, you get certain amount of aromatics around 13 to 15% aromatics from this NEP, but you get basically the mixed xylenes and benzene and toluene. And your pi oil and pi gas yield is significantly less than the typical mixed feed steam cracker. And this results, if we consider the base value of the investment for the crude to chemicals, this gives an incremental IRR about 4 to 5%, significantly good. And with an incremental expenditure just 10 to 20%. So certainly it's a bankable, and it's very, very effective. And the best part is it can be suited to the requirement of the customer. So here is the commercialization update. So right now our demonstration unit for a Chinese company is, well, we just completed the design last week. We completed the basic engineering package, and now it will go for the plant startup is second quarter 2026, second half 2026. And we are also moving with technology approval from Chinese government. We also signed the MOU with Petroleum, and that is about the first commercial unit, which is the previous one. This one was a demo unit. For the Saudi unit, it is pretty much a first commercial unit with a planned startup of 2025. There are the discussion with about 15 more clients, including Indian clients, and there are a lot of interest in India, and there are some advanced level discussion going on. If everything goes right, maybe we will get some more licensing, probably end of this year or early next year. Another good part is NEP can be offered as a modular unit, and that will be a big advantage and as a perfect solution for brownfield applications. And obviously EOP is prepared to license and guarantee the NEP. Overall, I think it's very nice to see there are a lot of good interest in NEP because of its simplicity, its flexibility, and I think yesterday it was talked about bankability and flexibility, and that is exactly which comes to this light olefins. So it converts readily available naphtha and LPG to a tunable amount of ethane and propane, and it's get a very efficient ethylene production, ethane to ethane steam cracking, which becomes the very efficient production. Generation of propane is optional. If you need, yes, you require, then you can. If it is not required, then it can be converted to ethane only, If it is back integrated, added this advanced hydrocracker, then it becomes a perfect solution for C2C complexes. And as I said earlier, it's an efficient, flexible, and bankable olefin production. And it's ready for license. And again, EOP is there to help you out and definitely try to meet your requirement. Thank you so much. Thanks.
Thank you, Mr. Abhijit. As you rightly indicated, ethylene demand globally is expected to touch around 200 million tons shortly. Especially India is going to see the ethylene demand growing to double over next 15 years. Your process NEP is a powerful tool which allows operator to leverage readily available naphtha and LPG while enjoying the superior yield benefit of ethane cracking. So thank you very much. Now our next speaker is Mr. Jing Wong from KBR. He is going to deliberate on chemical value chain for phenol and acetyl chemistry.
Thank you, and good morning, everyone. I'm very honored to be here in the ETN 2025 and share with you the KBR technologies on the pathway in acetyls and phenolics chemistry. We have been very successful in India market, and we are fully committed to this market and provide more unique solutions to our customers. Today, I'm going to talk about our portfolios and share with the chemical market trends and discuss the technology could enhance our clients' profitability along the chemical waves in India. And we are currently focused on two chain technologies. We can see here the acetic acid and vanillin acetate monomer along the acetyl chain technologies. And the phenylacetone BPA and propylene oxide by cumene, which is POC technology through the C3 and phenolic downstream technologies. And we are offering other chemical technologies over here as well. If you are interested in any of other technologies, we are happy to discuss further with you. So let's move on to the acetyls. Let's look at their applications and market. So this is the acetyl value chain that KBR licensed in the dark blue boxes. And it's downstream chemicals. Methanol and CO are converted to acetic acid. And acetic acid can further react with ethylene and oxygen to produce VAM. If it's just ethylene and acetic acid, it can make ethyl acetate. The other applications for acetic acid will be the PTA as well as the anhydride. VAM and acetyl acetate are used to make other applications on the right. We have highlighted the EVA and solar panel applications because it's highly demanded in Indian market. So firstly, we talk about the acetic acid market. The demand is growing significantly in the recent years and reach up to 23 million tons per year in 2030 globally. The major production areas in China and US. Let's focus on Indian market. The India acetic acid has reached 1 million tons per year in demand, and 90% of the demand is imported from Singapore or Southeast Asia and China. And we highly foresee that India is bringing all those production facility in the market in the recent years. And we expect to adding up 2 million acetic acid capacity in the next 10 years. The VAM demand has increased dramatically as well. and it's expected to reach 10.6 million tons by 2030. The main driving force comes from the paint industry and solar panel, as I discussed earlier. The Indian current demand is about 200K TA, and 75% of which is imported. And India is expected to bring new VAM plants online in the next 5 years as well. Our client's Asian Paint will be the first startup in 2027. Talking about the technologies, KBR has acquired the acetic technology from Chiyoda in 2020. And Chiyoda has spent over 30 years of successfully developing and commercializing this technology. Acetic technology has a significant advantages over the competitors due to its unique heterogeneous catalyst system and bubble column reactor design. This unique design allows a significant reduction in precious metal loss and a much simpler operation and maintenance. And KBR currently is the only licensor available in the market. The others are all operators who will compete further with you, our customer, in the future. This slide shows the traditional route to acetic acid and downstream applications used today. Syngas can be maturely produced by fossil feedstocks and further produce methanol and CO through ATR, SMR, or POX unit. And the acetic acid can be produced via methanol carbonations. With the current green initiatives to produce renewable chemicals, it can be sourcing by biomass or solid waste via gasification to produce CO or methanol. It is also possible to convert captured CO2 into methanol and CO using reverse water gas shift and green hydrogens. This allows CO2 to make into the acetic acid and further down chemical can be produced. And it will help our customer to be flexible in the CCUS areas. The VAM technology is exclusively licensed by KBR through global alliances with Crisis Chemicals, formerly known as Shevchenko. So CSC has been a VAM operator for over 40 years. So they accumulate tremendous operation know-how in the technology and keep developing the catalysts along the time. The 300 kDa single reactor VAM unit has been started up recently and reached guarantee figures within a short period of time, just 45 days. And after the acetyl chain technology, let's talk about the phenolics. These are the phenolic chain technologies KBR offers in dark blue boxes and the downstream applications. Today, we are focused on phenol acetone, BPA, and propylene oxide. The phenol market demand is gradually increasing in India. Similar to other chemicals, phenol is heavily imported from China and Middle East for phenol. The imports are partially offset by starting up the new unit plants in DPL and others. The current driving force of phenol demand is mainly from the PF resins. However, we also see the potential demand along the value chain from BPA and polycarbonate. Then the BPA is 100% imported in India and consumed by the epoxy resin. And with the growing epoxy resin industry and downstream development of polycarbonate industry, we believe there are a few BPA units will be built in the next 5 years as well. And talking about PO market, we foresee at least a 4% yearly growth globally till 2030. And the high growth region we foresee is in India with a double-digit growth. There are mainly two downstream users for PO. One is polyether polyols, which the end application will be polyurethane. And the other one is propylene glycols, who is produced unsaturated polyester resins, personal care products, and detergents. And the phenolics technologies, we will focus on the phenols and BPA and PO, as I mentioned just now. And KBR is the leader in phenol technology. We have licensed over 35 grassroots units, which counts for more than 50% of the market share globally. And we continuously to improve the phenol technology by improving the efficiency and integrate with downstream technologies. KBR also offers BPA technology via alliances with the Mitsubishi Chemicals. It is produce a superior quality BPA that's suitable for epoxy as well as PC requirements. It also incorporates over 20 years of operating know-how and superior engineering capabilities bring up by both parties. And we are keeping adding new reference in recent years all over the world. And right now, we are offering unique integration solutions for phenol and BPA units showing here. We could simply save CapEx by at least 2% and save OpEx in the area of acetone yields, wastewater purifications, and energy consumptions. And the POC technology is offered through KBR Global exclusive alliances with Sumitomo Chemicals. And KBR and HICC will jointly develop the project leveraging the superior engineering capabilities and with over 20 years of operating know-how to our clients. And POC process is established technology with 4 operators right now producing just under 1 million tons per year of POs. And the co-product-free POC process is using cumene as oxygen carriers for its oxidation of propylene to propylene oxide. The core cumene reaction cycle is pictured in the figures. And each of the reaction steps in the cycle has been improved and optimized over the course of development and operations, resulting in high yields, low impurity generations. Especially the epoxidation catalyst has been developed and with high yields, low impurity, and long catalyst life. This optimization means fresh cumene makeups required is very small. And the oxidation and epoxidation sections reaction are exothermic. So POC technology takes advantage of these reactions and in the heat integrations and recover it. This helps to minimize the overall plant OpEx and energy needed. And this chart shows a direct comparison of the energy consumptions compared with various PO technologies. On the left-hand side is the first generation chlorohydrin technology, establishing base cases as one. And third generation PO technology has achieved a 60% reduction compared to chlorohydrates. over the course of 20 years of operations and continuous development, the POC has achieved a further 15% reduction through the heat integrations and process improvement. And the flowchart pictures here shows the basic scheme of the phenol and PO co-production scheme. The joint oxidation sections supplies the cumin hydroperoxide to both POC process for EP oxidation as well as PO purifications. Similarly, the joint oxidation section supplies CHP to phenol plants for cleavage reaction and the purifications. So both process recycles cumin back for future oxidations. So this integration solution allows a diversification of the plant products, and this provides a more market stability through the product diversifications and gives our clients a lot of flexibility during the flexible chemical markets right now. So overall, the key takeaway is for KBR, we provide unique solutions for our clients in acetyl chain technologies, in acetic acid and VAM, and phenolic chain technologies in phenol acetone, BPA, and POC. Thank you very much.
Thank you, Mr. Jing. In fact, sustainability requires a fundamental shift in how we source our chemical building blocks. And Mr. Jing has very nicely mapped out the strategic necessity of transitioning production towards renewable feedstock, including CO2, biomass, e-methanol, even for fundamental chemical like acetic acid and VAM. So thank you very much. Our next speaker is Mr. Simon Morfoni. He would be deliberating the valorization of C4 cuts through Conser portfolio, focusing on butyl and halobutyl rubbers, maleic anhydride, and derivatives.
Okay, good morning. Thank you for the introduction. I'm very thrilled to be here to present to all of you some solutions that I believe that well fit with the solutions that my colleagues introduced before me. And I believe also that this solution could also satisfy the mandate that we received yesterday. So crude to money, we have to resume in these few words, because we believe that beside the commodities produced by crude, another way to improve the economics is to integrate also with higher value products downstream the commodity. And the products that I'm going to introduce to you and that can be offered by Conser portfolio are some specialties, but not niche specialties, that are also some internal demand in India. Then we see very strong opportunity. More in detail, I will speak about butyl and halobutyl rubber that are produced by isobutylene, and maleic anhydrides and its derivatives that are produced starting from normal butane. But before to start, just a few words about Conser. Conser is part of Maire. Maire is an Italian group, international group, that provides not only integrated engineering and construction solutions with the company like Tecnimont and KT, but also provide sustainable technology solutions thanks to the NextChem company. And Conser is one of the licensors belong to NextChem. In Conser, Conser is a company, an Italian company with 55 years of history, and during these years we developed inside a lot of technologies. We can resume in this slide. We offer technologies about advanced polymers, related to the advanced polymers, like bioplastics, rubbers, and fibers. We provide technology related to the special solvent. We have also technology dedicated for the food industries, like malic and fumaric acid. And we have also technologies that are related to the resins and plasticizers. And finally, we have also technology for the industrial solvent, for example, the acetone derivatives. Our services as a licensor are providing the license, the PDP, the proprietary catalyst, and proprietary equipment. Now we can start talking about the valorization of the isobutylene. Isobutylene is the raw material for the production of butyl and halobutyl rubber. Is polymerized with a low amount of isoprene at a very low temperature in a cationic polymerization. Then the products are recycled and purified. Not the product, the unconverted monomers can be recycled and purified in order to decrease the consumption of the raw materials and then the OPEX. Then the product, the rubber, can be sent to the finishing in order to produce the regular butyl rubber. Otherwise, it's possible, in order to improve the vulcanization property of the rubber, the butyl rubber can undergo an halogenation process in order to produce the halobutyl rubber. That is, can be bromobutyl rubber or chlorobutyl rubber. In Conser, we developed two technologies, both of which are industrially proven. One process is the conventional double slurry system. The other one is the PDD, the polymer directed dissolution process. The first one, the DSS, is more suitable when the main product is the regular butyl rubber or another rubber that is called the polyisobutylene rubber. Since the market demand is more occupied by the halobutyl rubber, in order to decrease the capex, in order to improve the capex, the OPEX, and in order to improve also the quality and the operation, in order to improve the quality of the product and the operation of the plants, we developed also the PDD process that is more dedicated to the production of the halobutyl rubber. But what is halobutyl rubber? Halobutyl is a rubber with very important properties in terms of impermeability. It is the rubber with highest impermeability properties, high resistance to the heat, high absorption, energy absorption, and these properties make them a rubber that find applications in the tire industry. Indeed, is used for the production of the inner liner of the tires, and also for the production of pharma stoppers, or also for sportive clothes and sport goods. What is important? It's important to underline that Conser is the only licensor that can be offered this technology for butyl and halobutyl rubber without imposing its involvement in the market, in the product marketing and in the plant ownership. We see that there is a lot of opportunity for this product in India, since there are more than 60 tire industries in India, and with a CAGR expected more than 10%. At the moment, there is one only plant for this product, and a large amount of butyl and halobutyl rubber are at the moment imported in India. Then we can talk about the valorization of the normal butane, and we can start to talk about the maleic anhydride plant. Conser is among the main licensor for the maleic anhydride plant, and compared to the other competitors, we have the possibility to offer the off-gas recycle solution. That is a way in order to decrease the OPEX, because we reduce a lot the normal butane consumption. We produce an off-gas recycle, a lower amount of off-gas recycle, and also with the lower CO2 emissions. And we have also the possibility to offer a plant without any wastewater effluent. What is maleic anhydride? Maleic anhydride is an important key intermediate in the petrochemical industry. Indeed, is used for production of several products, as you can see in this slide, and all of these products belong also to the Conser portfolio. We have technology to produce malic and fumaric acid used in food industry, special anhydrides used as hardener in epoxy resins. We have technology for the succinic anhydride, for the production also of malates that are plasticizer, and we have technology also for the production of BDO, DMS, THF, and GBL that we will see also in the next slide, and we have also technology for the production of PTMG used for the production of textiles like spandex, and also technology for the production of NMP and pyrrolidons. A few words about malic and fumaric acid, that are additives used in the food industry, since they have properties like pH corrector. Malic acid is produced starting from maleic anhydride and water. We can produce also in campaign, and we can produce only malic acid, but it's possible also to have a production of fumaric acid, and we can adjust the production in order to meet the market demand. Regarding instead the other product starting from maleic anhydride, we have technology for the production of the monomers used in the biodegradable plastics like BDO and DMS. BDO is used in biodegradable plastics like PBAT. And we have the possibility also to offer the co-production of DMS. When this approach, the co-production of BDO and DMS, is part of the so-called duetto Conser technology, this process allows a reduction of the production cost of the PBS, that is a very promising biodegradable plastics. In this slide, you can see some words about the biodegradability. Biodegradability belongs to the molecular properties. So it means that molecule can undergo microbially induced chain fissions to mineralization, and this belong to the molecular properties, so we can obtain biodegradable plastics even if are fossil-based. In the last years, the production of bioplastics increased a lot because it's important to understand that some recycle process for sure helps the sustainability of the plastics industries, but for some applications, the so-called hard to recycle applications, it's important to apply the biodegradable plastics. And PBS is one of the biodegradable plastics with very important properties. For example, heat resistance, flexibility and compatibility that make it a very important product that with several applications. And it's important also to understand that the growth of the biodegradable plastics is linked also to the mandate by the government, and in the recent years important input as done by China and Europe for the substitution of single-use plastics in China, and in Europe for the applications in the agrochemical. Regarding other products that derivatives of maleic anhydride, Conser has also technology for the production of special solvent, for example GBL and THF. We can propose a first solution in which we can produce directly from maleic anhydride, and in this scheme we have the co-production of the GBL and the THF. In the second configuration, we can produce GBL and THF starting from the butanediol. That is also, as we saw, also a derivative of maleic anhydride. The GBL find several applications in solvent, as a solvent, mainly in electronic industry, and has also an application because it's the raw material for the production of NMP. NMP with a very simple process. This technology belongs also to Conser technology. What is NMP? NMP is the solvent used for the production of lithium battery, and its demand is still grow due to the growing production of EV.
Mr. Simon, we are running out of time, please.
Yeah. Regarding the THF, also THF has important applications as a solvent, but main applications is the production of the PTMG, that is the precursor for the production of spandex. As you can see, we developed our technologies is as low capex and important improvement in terms of energy consumption and recovery of raw materials and production of very pure co-product like methyl acetate that allow to have a very interesting production cost of PTMG. TNG, as I said, is used for the production of spandex and also for special polyurethanes. Spandex is fiber used, for example, in sportswear. Just a summary about Conser portfolio, that we can see that Conser offers an integrated solutions for the production of butyl, halobutyl rubber and high molecular polysubutylene starting from isobutylene, and maleic anhydride and its derivatives starting from the normal butane. Just a few words about Conser reference. We have several reference industrial proven both for maleic anhydride derivatives and butyl rubber. Then thank you for your attention. Please feel free to contact us if you want to enter more in detail in some technology. Thank you.
Thank you, Mr. Simon, for touching upon such a critical value chain of C4s. So now our next speaker is Mr. Praveen Lokhande from GAIL. He would be touching upon the critical aspects of propane dehydrogen technology. GAIL is executing its own PDS project at Usar. Mr. Praveen.
First of all, good morning to all of you. And there are a few people I want to thank you first from CHT, Agrawal sir, Gorang and Lav Kumar, and our ED project is also there, Mr. Anup Gupta, and our team from GTI. Because of them, I am here to present a case. Propane dehydrogenation technology, which we are commonly calling as a PDS technology, it may be a new technology as far as India is concerned, but if we go by like last 2 decades, there have been a lot of advances and there are development in the catalyst section also, and operation point of view, a lot of efficiency factor has been taken care. So that's why I am discussing about the advances in the propane dehydrogen technology and with a sustainable propylene supply. So before going and discussing about the PDS technology, I'd like to highlight what is the present global propylene market, and then the different production route propylene we are having, and then how the regional capacity evaluation has been happening worldwide, and then why we are going for PDH and what are the demand factors which are being considered as far as PDH is concerned. And then technology point of view, there are various companies like UOP, KBR, they are having Lamas also, and then UOP, they are discussing about the technology factors as far as efficiency is concerned. And then GAIL, we are setting up a first PDHPP plant at Usar near Alibag in Maharashtra. And then one of the important factor which is being considered with PDH is that we are getting, since we are hydrogenating propane, we are getting propylene and hydrogen. So since we are discussing the hydrogen is a buzzword right now with the National Green Hydrogen Mission. So I think hydrogen also plays a important factor as far as energy requirement is concerned, as far as India is concerned. And then normally any process which is there, there are challenges, there are efficiency factors we need to take care. And in that sense, there are some challenges. And then lastly, conclusion. So as we all know, propylene is second most essential starting product in the petrochemical sector after ethylene. And basically polypropylene is the key derivative which normally accounts for around 2/3 of total propylene consumption. And propylene we have been using for our production of chemicals like cumene, propylene oxide, then acrylic acid, alcohols and other chemicals. And the major growth drivers, which normally includes for propylene, polypropylene industry, packaging, then automotive, construction, textile, and consumer goods industries. As we see that there is a definite propylene production increase over the last 2 decades, I say, and the more so in the future, there is a projection of around 200 MMTPA by 2030. And the global propylene market size is also going to estimated at a CAGR of around 3.76, which is normally considered as a bulk commodity like propylene as a very fairly a good demand. And the Asia Pacific, which normally considered by China and Japan, they are the key player, and also India is coming up with that. So Asia Pacific continues to be a demanding global propylene consumption production. And then USA presently is being benefiting because of the abundant shale gas reserve they have discovered. And it's also cost effective, and there is a lot of demand factor as far as packaging, automotive and construction sector is concerned. So we'll be discussing, I mean, most of people must be knowing about how the propylene is being produced, but there are certain processes. Most commonly is the steam cracking of ethane and naphtha, where, I mean, if we crack ethane, we are getting smaller share of propylene, but then we are, if we are cracking a heavier hydrocarbon naphtha, then we are getting a comparatively a higher content of propylene. Then obviously in refining sector, we are having fluid cattle cracking where we are cracking the vacuum gas oil, we are getting lighter products like LPG, gasoline, then propylene. And then of course the propane dehydrogenating is basically on purpose production of propylene from propane. So we'll be discussing more about that in details. And then there is also olefin conversion technology, which normally the metasis reaction is there with the ethylene and butane, and then we are getting this propylene. And then there's also one technology is coming of methanol to olefin, where apart from crude, like we are having natural gas, coal, from that also where we can produce olefin. So if we share wise, there is around 45% of propylene production route is coming through the steam cracking, and then fairly share of around 30% from FCC, and then there we are having around 16% of PDH. That's a lot. Last decade there have been a lot of plant set up, especially in China. So because of that, the percentage is increasing globally, and then other routes is contributing around 9%. So let us see how the regional distribution is there, global propylene market. If you see like North America, it's a stable growth led by USA around 26%. More importantly, 41% growth is there, which is led by China in Asia Pacific region. Europe is fairly stable at 24%, and then the Middle East and other markets is around like 9%. So if we see last decade, PDH has shown rapid growth in capacity addition, majorly because of driven by the growth by China and USA. If you see the share, which is highlighted in the green portion, fairly for last decade or so, there is a increase in the PDH plants. So what is the reason why we are emphasizing on the PDH plant? As Mr. Paul also highlighted regarding the propane to propylene. So if you see the PDH offers as the on-purpose conversion of propane to propylene, offering the significantly higher propylene yields when compared to traditional naphtha cracking and FCC and new MTO process. So if you see the graph, we can get a very high single pass conversion and high yield with the propylene. So if you see global recognition, China alone has commissioned around like 20 PDH plants, and it has a combined capacity exceeding like 15 million tons per year. And then North America is also fastest growing PDH market is coming up with the projects in Texas and Louisiana. And obviously, if you see the propylene, there's definitely a demand factors right now, but the kind of current situation which we are emphasizing with the current geopolitical situations, but maybe that is a very temporary phenomena. There is a chance that the themes will get stabilized, and then we can have a definite market there. More so, the lower reaction temperature also make it more energy efficient compared to steam cracking, and reducing the environmental impact and aligning with our sustainability goal. As I said, high pass conversion is also there, and yield is also there with this on-purpose propane to propylene. Another is that we are getting as a byproduct, that is a hydrogen. And if you see the cracker units and all, we need to have a hydrogenation unit separately to make it a more stable saturated product. So that kind of hydrogen is not required in this. Straight away we are getting, it's a very simple process, and we are getting straight away from propylene to propylene after dehydrogenation. And as an operation point of view, we get a very quicker time to start up and make products. So that is also an advantageous part. And then we are having easier and shorter turnarounds, which makes a very able case. And then another important factor is that the catalyst, which is like chromium alumina based, it's also a noble catalyst. So the price wise also there is a different advantage here. And of course, there is no chlorine or caustic handling as we see in steam cracker, where we are having downstream part consisting of quench towers and all. So it's a simple process which we can see that we are just preheating the propane and then straight away of fitting it to reactors where we are getting the dehydrogenation, and then whatever effluent we are getting, we are processing it to get the product. There are fairly technologies which are available, and it depends on how cost-wise and what is best suited for your process. Like Lummus CATOFIN technology is there, which uses the fixed bed reactor and is known to have high yield of propylene at low operating costs. Then UOP has also developed catalysts, and they are also coming up with the catalyst reagent system to convert propane to propylene. Then obviously FCC hydrogenation also there developed by Dow Chemical. And then the STAR process is there, which is normally developed by the Philip Petroleum and now licensed by Thyssen Group Uday. KBR also is having a technology where they are saying it's a low cost catalyst and a fluidized bed reactor where we can get this PDH. As far as GAIL is concerned, we are coming up with India's first PDH technology, PDH-PV project. This is said this location at Usar, Alibag in Raigad, Maharashtra. We are having EPCM Engineers India Limited, and the technology for PDH unit is Lummus Technology USA, and the for PP it's Grace Technology. So it's a very simple process. We are getting feed from our Uran jetty, and then we are having the terminal there, and then we are having a 12-inch 45-kilometer pipeline, and then we are feeding it to our PDH unit, and we are getting C4 mix, heavier, and then hydrogen also, and then from propane to we get propylene, and then we are feeding it to our PP unit. So if we see the licensed PDH process is a CATOFIN because we are going with the Lummus technology. So it's a very simple process. We are having like 5 reactors. 2 will be on reaction side, 2 will be on regeneration, and 1 will be in evacuation. So after getting these propylene, then we are compressing it, and then we are having separation, then lighter and heavier, and then we are getting propylene, and the rest is back to recycle as propane. So it's a very simple catalyst, simple process where we are getting dehydrogenating propane, and we are getting propylene. As I said, hydrogen also we are getting as a byproduct, and presently hydrogen being a very clean, versatile, abundant fuel, so it has an opportunity where definitely there is a potential to transform the global energy landscape with that. And in PDH, hydrogen is produced as a valuable byproduct, and it's already equipped with a pressure swing adsorption unit to produce high purity, low carbon intensity hydrogen, thus enhancing the environmental footprint also. So we are presently using this hydrogen for our fuel requirement also, and then there is a availability of surplus hydrogen. And if we integrate with that our the CCUS units, and there is a potential to have a more cleaner hydrogen also. So obviously there are challenges with the technology, and it's up to us how we work on that. And as we say that there is a issue, if there is an issue with the catalyst deactivation because there is a cold buildup over the period of operations. So how we operate with the high temperatures and performance point of view, that is an important factor. Then energy efficiency also remains always a important factor, since as we see steam cracking, there is a very high energy intensive plant. So in that way, PDH is offering us a more energy efficient, and improving heat integration and reducing losses always be a challenge there. And obviously when we are going for any process, economics and competitive always plays an important part. It depends on how we source the propane, what the cost of propane, which is there, because when we are going for online on-purpose production, definitely the cost of propane will play an important role, and the differential part will have a different advantage in getting the profitability over the propylene market. And then I have talked about the hydrogen part. If you put the carbon capture and storage and utilization, then definitely that investment part will be there. But in long run, that will produce a lot of advantages as far as hydrogen is concerned. So, in a conclusion, I can say that definitely there is a market there for PDH, and it experiencing significant growth globally. As I've said, shown to you that especially China is coming with a lot of plants, and India's role also is increasing rapidly in the petrochemical industry, and the supportive government policy is also playing a key player. I mean, after GAIL, Petroleum LNG is also coming up with second PDH plant. And then the on-purpose production advantage is always there, since it's an efficient route of getting propylene. And the innovation part is always be a part in the this technology, because how the catalyst development process optimization is done, it depends on that how this PDH industry will go forward. So that's all from my side. Thank you very much.
So thank you, Praveen. And thank you for making the PDH process so simple for the audience by repeatedly mentioning that it's so simple, but still you covered the challenges very effectively. So now,
So with this, I think we come to the end of these insightful presentations, and I'm quite sure that the presentations would have given the industry a lot of insight that, how can they optimize their petrochemical facilities in terms of feedstock supply? How can they optimize on the capex? It may be optimization of conversion versus feed. If you have lighter crude versus heavier crude, or let us say if you have a lower conversion and a lower capex. So with this, I think because a lot of petrochemicals is being planned in the country as of now, and I think this will definitely help the industry to, let us say, that how that they can make their projects viable in the coming future, and as well as the other two presentations on phenols chemistry, acetyls chemistry, and value addition, that how they can valorize the various molecules, the C4 molecules produced from the cracker, to butyl rubbers and maleic anhydrides. So this is how the industry will gain from these presentations. I think we are already running short of time, and maybe if we can have about question answer session for just 5 to 10 minutes. So that
I'm so sorry to interrupt, sir, but we've overshot the schedule allotted for this session. We'll not be able to take questions at the moment, but please feel free to connect with them during the networking session, during the break sessions. Thank you so much. Can we hear a big round of applause for this phenomenal session that we've just had? What a great start to day 2 of ETM 2025. I now request Mr. Rajiv Agarwal and Mr. Sanjay Kumar Papneja to kindly step forward and present a memento as a token of our appreciation and thanks to our eminent speakers on stage. Thank you, Mr. Subhabrata Guru. Thank you so much for your value addition to this fantastic session. Thank you, Mr. Gopal Gattu. Thank you so much, Mr. Gopal Gattu. Kindly step forward and accept your token of our appreciation. Alexis Paleo, thank you so much, sir, for being here with us this morning and sharing your valuable insights. I now request Mr. Sanjay Kumar Papneja to hand over a memento to Abhijit Pal. Mr. Abhijit Pal, thank you so much for your amazing contribution to this session. Please keep the applause coming, ladies and gentlemen. Mr. Jing Wong, thank you, sir, for joining us this morning and participating proactively in this session. Mr. Simon Morfuli, thank you. Thank you for joining us. Thank you. Congratulations on being a part of this phenomenal session. Thank you. And I request Mr. Rajiv Agarwal to present a memento to Mr. Pareen Lokande. Requesting everybody to put your hands together, please. A collective round of applause. As I invite Mr. Satya Prakash, ED, Baruni Refinery IOCL, to present the mentors to our esteemed moderators. Thank you, Mr. Rajiv Agarwal. Mr. Rajiv Agarwal, thank you so much for your contribution. And thank you, Mr. Sanjay Kumar Patneja, for ably moderating the session. Thank you. Now I request everyone to step forward for a group picture. If you will, gentlemen, thank you. And a collective round of applause, ladies and gentlemen, for this phenomenal set of experts that we have here on stage. As we click this group picture, I'd like to tell you all that we will now take a break for 15 minutes and 15 minutes only. Kindly come back after 15 minutes because we will resume the session. Again, let me remind you all two things. One, of course, that we will have sessions happening parallelly in the adjacent room as well. Check your schedules accordingly. Make the most of the sessions. The second thing is, we also have QR codes placed at various junctions. Please ensure that you scan the QR code and send in your questions before the session ends. Only then we'll be able to accommodate a Q&A session. The only way that we will take questions is when you scan the QR code and send us your questions. Organically, we will not have the time to take the questions. So ensure that you scan the QR code and send in your questions during the course of the discussion. Thank you so much, everybody. We'll see you all in the next 15 minutes. Enjoy your break. Refreshments and tea is this is going to be the technical session number 6, and this is day 2 of Energy Technology Meet 2025. The topic of discussion still continues to be technology frontiers in refining, efficiency, integration, and sustainability. Before I introduce the moderators and bring them onto the stage, gentle reminder, we have QR codes with these posters of QR codes kept at different places. Please scan the QR code in case of any questions. Towards the end of the session, the moderators will take questions and address and direct them to our eminent speakers, and they will address the same. With that, without further ado, I'd like to take this opportunity to invite our moderators, our session chairpersons to the stage. Please put your hands together for Mr. Abhijit Chakraborty, EDIOCL. His areas of interest: engineering, design, project planning and execution, green energy, environmental protection. His achievements, to name a few: engineering on grassroots projects, execution of brownfield projects, execution of mega projects. Please put your hands together for Abhijit Chakraborty. And joining him on stage is Mr. Senthil Kumar, ED, Coordination, BPCL. 3.5 decades of varied experiences in plant operations, petchem, polyols, planning and countrywide capex investment management, ERP implementation, international trade, crude oil products shipping. Currently, Executive Director, Refinery Coordination, overall coordination of all refinery operations across BPCL, acts as a key liaison between refineries and the Director, Refineries for policy implementation and project execution. Please put your hands together for Mr. Senthil Kumar. And now I'd like to take this opportunity to welcome our distinguished speakers to the stage. Put your hands together for Mr. Chiranjeev Bhaldar, Technip Energies India Limited. Welcome, sir. I think there are few too many people, but we do not have the applause coming as much people as we have. So can you please take it up a notch? And let's welcome Mr. Chetan Mittal, Topso India Private Limited. Welcome, sir. Joining the dignitaries on stage up next is Mr. Sunil Kaul, Lin Engineering India Private Limited. Welcome, sir. Please keep the applause coming as I invite Mr. Somendra Banerjee, Honeywell UAP. Mr. Banerjee? Oh, welcome, sir. And last but not the least, please put your hands together for Mr. Abhijit K. Ram, Engineers India Limited, joining our distinguished panel of speakers. Welcome, gentlemen. Thank you so much for being here. Looking forward to a very insightful session. With that, over to our chairpersons. Gentlemen, take it away.
Welcome all, ladies and gentlemen. After a very nice yesterday's session with our Honorable Minister, right from fireside chat and interaction with the Indian diaspora and the startups, today's sessions I think will enlighten on a dull day in Hyderabad today. It was quite raining and when we walking, coming to this venue, it was quite dull. We are sure these sessions will enlighten us, electrify us back into the mainstream discussions. Today's topic, the topic of now, is technology frontiers in refining, efficiency, integration, sustainability, which is aligned to our national goals of Viksit Bharat, wherein refining tech will support India's march towards the Viksit Bharat. These technical papers are from well-known technology leads in our country who are contributing in the refining space, right from Technip, Topsoe, Linde, EOP, and EIL. The topics cover right wide spectrum, right from integration of fertilizers, companies and or refining. Then comes our bread and butter, heat recovery and energy efficiency, and also the main topic which is going on our country on expansion and how to make it more efficient. Refinery configuration, integration, and expansion. These topics are quite interesting, and we'll spend our time. And after this, while there will be question and answer sessions which will be there, please put in your through your QR codes all these questions and address to the person who will be covering the topic. And each session will be for 15 minutes. I think Mr. Abhijit and me would be checking the timing also so that we complete the sessions in time. Yeah.
Good morning, everybody. Thank you, CST and BPCL, for giving me this opportunity to conduct this session. For the sake of repetition, let me repeat, we are in a changing time. So energy is changing, we have to change. And today, we talk about renewable energy, petrochemical, etc. Today is a new dimension being discussed here, integration of fertilizer. Already, many of the companies are collaborating with fertilizer for integration. So today, two of the topics will be on fertilizer. And the next important thing is efficiency, which will be discussed here by replacing how to replace fuel oil with electric power, especially from renewables. And what improvement in the system can be done for the new revamps, etc., which will be dealt by all the learned participants from various companies like Topsoe, Linde, EOP, EIL. I missed anybody. So we'll not take too much time. We want to listen from them. So let's start with, first with, we'll start with Technip. Mr. Halda, please. So it's your call.
Thank you very much, sir. Thank you very much, sir. And good morning, ladies and gentlemen. So my topic is basically integrating fertilizer production into refining and petrochemical complex, driving towards sustainability. So before I start, just a little bit of introduction about Genesis. So Genesis is basically the consulting and advisory arm of Technip Energy. It is 100% owned by Technip Energy, but at the same time, it is independent entity with technology agnostic approach. And we are not a mere consultant. Our advisory services consist of both consulting as well as engineering capability. So whatever we suggest to our client, definitely we can engineer the same. And just to mention that in India, Genesis has completed 5 years of operation. Now moving back to my topic, that integration of fertilizer production into refinery and petrochemical. So as you know, there is a global pressure on the refineries to decarbonize. And at the same time, we're going for a transition to the EV. So obviously, there will be less demand of fuel, and we need to decarbonize. So by integration of petrochemical into refinery complex, to some extent, we're fulfilling this requirement. But at the same time, if we look overall complex, still there are good amount of streams, which are like low value streams or so-called waste or effluent, basically like ammonia, H2S, carbon dioxide, etc. Those can be recovered and used as a feedstock for the fertilizer complex. So this integration basically that will create a circular economical model where waste become a valuable resource. Thereby we are reducing emission, we are reducing the raw material cost, and also we are enhancing the profitability. So I'll briefly cover about the background, the integration concept or the technology available, simple case study followed by opportunities and challenges, and finally the conclusion. So why I'm talking about fertilizer? Because if you see in the year 2023-24, total fertilizer consumption was about 60 mmTPA, and out of that 17.7 mmTPA was imported, which is almost like 30%. So in the right hand side, if you see urea, the import dependency is 13%, NPK 10%, DAP 60%, MOP, that muriate of potash, almost 100% we have to import. And there is a strong demand that this fertilizer will further go, driven by the population, the food security, the expanding basically crop area, and the soil condition. So in order to make India self-dependent or self-reliant, basically, we need to produce more and more fertilizer. And there, this integration comes into effect. Like if we talk about the fertilizer complex, the key ingredient are ammonia, sulfuric acid, carbon dioxide. Like if we talk about urea, it is ammonia and carbon dioxide. If we talk about DAP, diammonium phosphate, ammonia and phosphoric acid. And how we are generating phosphoric acid? By reaction of sulfuric acid with phosphate rock. So the key ingredients are basically ammonia, sulfuric acid, carbon dioxide. How we are producing ammonia? By reaction of nitrogen and hydrogen. Nitrogen we are taking from air, hydrogen we are getting from the SMR. Similarly, carbon dioxide we are also recovering from the SMR in a fertilizer complex. And for production of sulfuric acid, we are using sulfur. Whereas in the left-hand side, if you see in the refinery, what we are doing, the crude content impurities like nitrogen and sulfur, that nitrogen is getting converted to ammonia during this hydrotreatment process. And what we are doing, we are just burning that ammonia in the sulfur recovery unit. So in the fertilizer complex, there is a demand of ammonia. And on the other hand, in refinery, where ammonia is already available, we are just burning it. Similarly, sulfur that is converted to H2S, and we cannot release it to atmosphere. So we are forced to convert that H2S to produce basically sulfur. So this is not to make money, but to meet the stringent regulatory regulations basically. Same for carbon dioxide also. We are eliminating so much of carbon dioxide, we can easily recover those carbon dioxide and utilize it for the fertilizer complex. So thereby basically this low value streams can be used as a feedstock for the fertilizer complex. Thereby it can lead to additional revenue generation, so it will improve the economics, and it will also contribute to self-reliant India for fertilizer production. At the same time, this integration will lead to improve operational efficiency and flexibility, leading to reduction in the environmental emission. Now, how this integration is going to happen? Like as you discussed in a refinery and petrochemical complex, also this basically if we talk about waste streams, so ammonia, H2S and carbon dioxide, these are the main waste streams. So what we are doing with H2S in refinery, we are converting H2S into solid sulfur, and then we are dispatching. And what is happening inside the fertilizer complex? They have to import sulfur, then solid sulfur, they have to melt it. We are burning it to produce carbon dioxide, then the carbon dioxide is converted to, sulfur dioxide, and that is converted to sulfur trioxide, oleum, followed by sulfuric acid. Whereas H2S can be directly converted to sulfuric acid. Thereby, we can eliminate a lot of intermediate steps. So there is no intermediate storage requirement. There will be no transportation, no sulfur melting, burning, etc. So there will be significant capex reduction, same significant reduction of plot area requirement, manpower reduction. At the same time, there will be ease of operation. There will be much better efficiency, leading to reduced carbon footprint. So, like if we see on the right-hand side, we need sulfuric acid. So as we discussed, we can directly convert H2S into sulfuric acid. So that means the sulfuric acid plant, which is required for the fertilizer complex, that can be eliminated. Next, we can recover this carbon dioxide and ammonia. Okay, the question could be how much ammonia we are recovering? Is it good enough to sustain this operation of fertilizer complex? Certainly not. We need to produce more ammonia. Now, how we are producing ammonia? We need nitrogen and hydrogen. If you look at the refinery, there is HG unit already available to support the demand of hydrogen for the hydrocracking, hydrotreatment process, etc. So when you are integrating steam cracker and aromatic complex along with the refinery, the steam cracker and aromatic complex, they are hydrogen rich. So they are already exporting hydrogen to refinery. That means there will be spare capacity available in my HGU. Besides, we are going for more and more green hydrogen. That will also lead to availability of surplus hydrogen. So this surplus hydrogen we can send to the fertilizer complex. So that means the SMR, what is normally required for a standalone fertilizer complex, the capacity can be significantly reduced if we integrate it with the with the refinery complex. Similarly, we need nitrogen. We're generating nitrogen from the air separation unit. And in refinery also, we already have nitrogen, the air separation unit available. And normally, this air separation unit or nitrogen generation unit, that is designed for the governing case. And governing case is basically like for purging and for regeneration, etc., which is not like a normal operation. So during normal operation, there is a significant margin available or capacity available in the air separation unit. So that nitrogen, we can route it to the fertilizer complex. So thereby, if we integrate the fertilizer along with the refinery complex, that means not only the SMR capacity, but the air separation unit capacity that can also be reduced. So sulfuric acid plant, we can totally eliminate. And at the same time, we can reduce the capacity of both SMR and air separation unit. So one way, there is a feedstock integration. So waste streams are getting converted as a feedstock for the fertilizer complex. And at the same time, when we are integrating, there will be shared utilities, as well as basically it will lead to much reduction in the capital intensity. So this integrated complex will have much lower capex if we compare with the standalone fertilizer and refinery complex. And at the same time, it will lead to a reduction in carbon footprint. Now, question is, do you have the technology available to recover this ammonia, carbon dioxide, or conversion of H2S into sulfuric acid? The answer is yes. In each and every refinery, we have the sour water stripper unit, whether it is a single stage or two stage. In a two-stage sour water stripper, what we are doing, we are taking out H2S rich gas from the overhead of the first column, and from the overhead of the second column, we are getting ammonia rich gas. Now, depending on the recovery target, okay, there could be some low-cost modifications required, but the scheme, the columns are already available. We can easily get ammonia from the existing system with some low-cost modification. Okay, in order to meet the specification of the fertilizer complex, there is some treatment required for the ammonia. So there will be ammonium treatment of ammonia, followed by ammonia compression, liquefaction, etc. So with some addition of basically lower amount of capex, we can generate, we can convert basically this ammonia as a feedstock for the fertilizer complex. Similarly, if we talk about H2S, so yes, that can be directly converted to sulfuric acid. It is a licensed unit. There are several licenses available. I think my next speaker, he's going to talk in detail about this system. So I'm not going in depth, but the technologies are already available for conversion of acid gas into sulfuric acid. And for carbon dioxide capture also, yes, technologies are already available, whether you're going for amine scrubbing, whether it is a membrane separation or cryogenic process. The technologies are already available. We can recover carbon dioxide, we can capture it and utilize it for production of urea. So that will lead to the proper integration. And just to give a typical case study, simple case study, like let us consider one refinery and petrochemical complex of 10 MMTPA capacity. So in the feed, normally we have feed sulfur, let us consider average feed sulfur of about 1.25 weight%. So that can lead to production of about 1150 tons per day. That is almost 0.38 MMTP of sulfuric acid. Similarly, if we consider the nitrogen content, there is a potential to recover about 40 tons per day of ammonia, which is almost like equivalent to 6.6 million USD. And if we see in 2024, we have imported 1 billion USD of ammonia. So at least to some extent, we can recover ammonia and we can reduce this import dependency. If we consider overall refining capacity, 258 MMTPA, and if we recover ammonia from all the refineries, okay, the total ammonia recovery potential will be roughly about 0.34 MMTPA. That means something like $170 million. And utilizing this 0.34 MMTPA, if we want to produce some fertilizer, let us consider DAP, diammonium phosphate, because 60% of the DAP we are importing, which is about 5 MMTPA. So utilizing this 0.34 MMTPA of ammonia, recovered ammonia, we can generate 1.3 MMTPA of DAP, which is almost like 26% of what we are importing. That means based on the recovered ammonia from all the refineries, we can satisfy 26% of DAP import demand. And if we produce more ammonia, obviously, we can go for the whatever total DAP demand we can satisfy. Otherwise, also, we can go for alternatively like ammonium sulfate production or ammonium phosphate sulfate production. There is a huge demand of all this fertilizer also. So basically, if we go for the opportunity and challenge, yes, when we integrate this fertilizer complex along with refinery and petrochemical, it leads to a circular economy, basically reducing the overall capex, and at the same time, there will be environmental impact, a reduction of environmental impact. And when you talk about the challenges, okay, the first challenges will be the amount of ammonia, whatever we are going to recover. It is not a significant amount, so it will not be self-sufficient for the fertilizer complex. We need to produce more ammonia, but we already discussed there are surplus hydrogen and surplus nitrogen available inside the refinery. So utilizing that surplus hydrogen and surplus nitrogen, we can meet the additional ammonia demand also. Another point could be introduction of green hydrogen. Nowadays, we're going for more and more green ammonia. So if we're going for more and more green ammonia, that means there will be less demand for SMR for the fertilizer complex. And SMR is not only supplying hydrogen, they're also supplying carbon dioxide. So there will be shortfall of carbon dioxide in case you are going for more and more green ammonia. But if we integrate a fertilizer complex along with this refinery and petrochemical, so we can recover carbon dioxide, and that carbon dioxide can be used as a feedstock. So we can leverage a carbon credit system basically for the integrated system. Third point could be higher solid handling. Yes, because we're producing so much of fertilizer, we need to have bagging, packaging, storage, etc. But thanks to our expertise in the petrochemical sector, we are already handling this solid. So there is no issue at all. It can lead to seamless operational transition and management. There is no issue related to handling of higher amount of solid. The fourth point could be like permitting and regulatory hurdle, because there is a cross-sector integration. One side we have MOPNG, and another side like a Ministry of Fertilizer. So that can be easily sorted out by early stakeholder engagement. We can establish a joint policy framework in order to address the concern early and basically facilitate a smoother approval and coordination process. As said by Albert Einstein, in the middle of every difficulty lies opportunity, and here we have the opportunity. And also, as said by Nelson Mandela, it's always seem impossible unless it is done. So this can be easily done. So moral of the story, refineries are facing challenges to reduce carbon dioxide emission, adapt to the evolving market dynamics, and simultaneously improving profitability. Integration of refinery and petrochemical to some extent address this concern, but there are some low value stream available. We can recover all this low value stream, use as a feedstock for the fertilizer complex. So when we integrate the fertilizer along with the refinery and petrochemical complex, it will lead to like a circular economy leading to better profitability. And if we talk about the key enabler for success, the technologies are already available. There is no issue at all. There is a very good demand for the market for all the fertilizer products. And with valorization of this low value stream and producing a higher value fertilizer, it will lead to greater economical resilience. There will be much less capex requirement, much less area requirement, plot plan requirement, basically manpower requirement will be optimized, and thereby it can lead to significant reduction in the carbon footprint. And ultimately, we will be able to contribute to self-reliant India for the fertilizer production. So this integration of fertilizer with refinery and petrochemical complex, so it is creating basically a circular economical model where these low value resources or waste streams are converted as a valuable feedstock product, reducing the emission, reducing the raw material cost, improving the overall efficiency, leading to better utilization of the existing OSBL system as well as the existing facility, and thereby overall profitability is going to increase. So it will make sustainable. So being part of Genesis and Technip Energy, will be happy to help in this integration process, whether it is from the early stage engineering, preparation of pre-feasibility study, feasibility study, basic package preparation, licensor selection, or detail engineering, feed, EPC, etc. Because in Genesis and Technip Energy, we believe that sustainability not only reducing our own carbon footprint, but to assist our client to help them to attain their sustainability target, to achieve their goal for the decarbonization, to increase basically the efficiency of their existing system, and thereby making it much more profitable. So why to wait for? Let us break boundaries together and engineer a sustainable future. Thank you very much.
The mic is not working. Your mics are working. Yes, sorry. Mr. Haldar, it was a very good presentation, and you have touched upon a subject which is a new avenue for the industry to integrate together and to value add to the West, whatever is happening. Already many of the companies have, refineries are doing collaboration. I am told yesterday there is a collaboration done between FACT, Tribanco, HICC, along with BPCL and Oil India Limited for green hydrogen, green ammonia, green methanol, and to use their manures from BPCL. So it's already, the action is on. With your expertise, I think industry will go further, and everybody should take this opportunity when you go back to your office to please look into how we can improve your system by integrating refinery, petrochemical, fertilizer. Thank you, Mr. Haldar, once again. So next is Mr. Mittal. He will be talking again on fertilizer. Let us hear from Mittal what he is telling, and then we will conclude.
Thank you so much, sir. Am I audible loud and clear? Good. Okay. So let's start. So I will try to recap what happened yesterday. Yesterday was a fantastic day. It was full of knowledge sharing sessions, and not to forget, with full of fun as well. I must mention, I really enjoyed yesterday's gala dinner. I hope you were there. If not, you really missed my dance. You have to wait for next year, maybe probably then. Apart from the fun part, yesterday we have learned about current development in India energy sector. What is happening? What are the challenges going around the industry? And what are the future aspects? My key takeaway from that session was, like, Indian refinery sector is under growing pressure to balance between economic growth and environmental responsibility. There is a need to reduce the import of crude oil to ensure profitable operations with expansion happening in the refineries, and also at the same time reduce greenhouse gas emissions in the refineries. And this, refinery operators must find innovative solutions, to tackle these problems and adapt those solutions. Today, I am going to talk about such a solution offered by Topsoe named wet sulfuric acid, or in short, we call it WSA technology. In coming 15 to 20 minutes, the clock is running, but I will try to finish in 15 minutes. How WSA technology, with the help of refineries and fertilizer sectors, can support India towards the self-reliance goal and eventually help India to become Viksit Bharat. So let's start. We all know India is facing numerous challenges in the journey of Atmanirbhar Bharat. We rely heavily on energy import, and that leads to a lot of burden on foreign exchange. And we have decarbonization target as well, like net zero by 2070, etc. And also we import a lot of critical chemicals like sulfuric acid. And these challenges requires demand and innovative solutions. And Topsoe is here. Topsoe offers such solutions. We have a wide portfolio, and we are already helping our customer to get to their net zero targets. And we have technologies for low carbon to green segments, like be it hydrogen, ammonia, methanol, sustainable aviation fuel, renewable diesel, you name it. We have almost every technology in the renewable sector. And we also have a huge portfolio in the clean air. And just to put in perspective how impactful Topsoe is that every third molecule in world is produced from the Topsoe solution. And the same goes for the sustainable aviation fuel as well. And today's topic is about WSA solution within our clean air portfolio. So let's get started. So what is WSA? So WSA technology takes the sulfur emissions from the various industries like pulp and paper or cement industry or coal industry or anything, and an industry like refinery, and converts that into the clean air by removing more than 99.99% of sulfur waste. And that sulfur waste is converted into commercial grade sulfuric acid. And the process is inherently exothermic in the nature. That is why we produce high pressure superheated steam as well. So how WSA technology, empower India towards self-reliance? So okay. I'm really surprised. I am not able to see the animations here because there was animations all over the place. Anyway, I'll continue like that. So the thing is that with WSA technology enables us to produce sulfuric acid locally and also reduce the foreign exchange rate. And the WSA technology has the lowest levelized cost of sulfuric acid production. We have designed the technology in such a way. And with the WSA technology, we can reduce the carbon emission to a larger extent. And this is a perfect opportunity for the hubs where refineries and fertilizer sectors are placed nearby. And finally, the technology is not new. It is proven for decades. So if I start with the first topic, the self-reliant India. India imports sulfuric acid and fossil fuel. With sulfurous gas, refineries can convert these sulfurous gas into commercial grade sulfuric acid, thereby enabling India to produce sulfuric acid domestically. And at the same time, you can produce high pressure steam, which will reduce the load of the boiler. And if I put that in perspective, if the WS is installed in all the refinery across the India, it can cut the fuel oil demand by more than 1.5 million tons per annum. It has that much of potential. And that is equivalent to over $600 million of foreign exchange. Next is how we are saying it is having a reduced levelized cost of sulfuric acid. So for that, I will have to explain you how sulfur is being handled in refineries in today. So sulfurous gas, at the top you can see it converts the sulfurous gas into sulfur by going through the sulfur recovery unit and tail gas treatment U2 to get the recovery of more than 99.9%, which is very energy intensive process. And then this sulfur occupies a huge prime space within the refinery. And then finally, this sulfur is transported to the sulfuric to the plant, to the location where sulfuric acid plant is located. This requires a lot of equipment, energy, and space to convert sulfurous gas into the sulfuric acid. But with the WSA, the story is completely different. With WSA, the sulfurous gases directly go to the WSA system and generate the sulfuric acid. There is no need of TGTU, SRU, sulfur pile, no need of transportation, nothing. And also, WSA can treat ammonia, hydrocarbon very easily, which cannot be done in clouds. It is a bit complex there. So the key message here, with the WSA process, you can reduce your capex by more than 50% and generate steam 3 to 4 times higher as compared to the clouds process. And this number becomes 6-fold when we consider TGTU unit as well. And at the same time, there is no need of sulfur pile, so it significantly reduces the prime space. And then next topic is it reduces the CO2 emission reduction. How it does? In the currently refinery uses fuel oil to generate the steam, and that emits a lot of CO2 emissions. But with the WSA, you can generate 3 to 6 times to high pressure steam, which will reduce the load of boiler. In some cases, it eliminates the boiler itself and reduce the CO2 emissions. And this, if I take an example of a typical refinery, the WSA cuts the emissions, the total refinery emissions by 9%, which is just 2% in case of the Klaus process. And if I extrapolate this situation, if I implement the WSA process in all the refinery in India, the CO2 emission reduction potential of the WSA technology is more than 5 million tons per annum. And at the same time, you can generate the carbon credits. Next is how refinery can tap this opportunity. So 95% of the sulfur produced in the world converted to the sulfuric acid, and out of that 70% goes to the fertilizer industry. So, and India has numerous places where refinery and fertilizer industries are located very close to each other. So it's a perfect opportunity for refiners to produce sulfuric acid and transport it to fertilizer industry as an end use. This will reduce the complexity of logistics. So it is really a good opportunity for refiner to adopt WSA technology. And finally, the last piece of the puzzle is how ready is the WSA technology. This is not a new technology. This has been there for decades. It has more than 160 references running all across the world, with 50% references within the refinery itself. Secondly, the WSA plant is already there in India. It is running at Haldia refinery, IOCL, since 2020-22, and they are already saving more than 75,000 tons per annum of CO2, and also generating 40 tons per hour of steam. So with this, I would like to say, please grab this opportunity, produce sulfuric acid cost effectively. At the same time, reduce your carbon emissions and save the money as well. I, as a TOPSO, encourage refinery and fertilizer sectors to join hand with the TOPSO WSA solution to decarbonize your refinery. IOCL has already started this journey of decarbonization, and I'm sure rest of the refiner will follow the same path soon and decarbonize their own refinery as well. With this, I would like to end my presentation, and with the sentence that together with innovative solutions like WSA technology, we can help India to get closer to Atmanirbhar Bharat and eventually become Viksit Bharat. Thank you so much.
Yeah, that was a good presentation. One thing which always surprises us, because many of the refineries, like what is there in Kochi or in Chennai, the old Madras refineries, and other places, like even in Bombay, the fertilizer units are quite close to the refineries actually. So this has not kicked up in a big way. I think because of the decarbonization and the steam efficiency which you're bringing in, I think these technologies will again find some new ground. I think yeah, good presentation.
So, as you said, the carbon emission is getting reduced. Area is becoming very clean. Handling of sulfur reduces, and of course the value addition. So we have covered this aspect of fertilizer. Next topic is very interesting, that electric cracking furnace to reduce fuel oil consumption and increase the use of electricity. So welcome, Mr. Kaul.
Good morning, everyone. Thank you, session chairperson and CST, for giving me the opportunity to talk about Linde's Star Bridge technology. What is Star Bridge? It is actually the electric furnaces for production of ethylene. I will touch upon three aspects in my presentation. First, giving you an overview
which is the introduction part. The second is the demonstration plant, which has been built at BSF site in Germany. And third is the commercial design, which we are ready to offer to the industry. To start with the introduction, as such, petrochemical accounts for 5% of the CO2 emissions globally. And when it comes to the furnaces, the enormous amount of CO2 is being emitted into the atmosphere to the tune of 300 million tons every year. This was the problem. And the three companies came together, which is BSF, SABIC, and Linde, to address to this problem and came up with the two concepts to be developed for offering e-furnaces as a technology and named it as Starbridge technology. It is a licensed technology and it will be offered by Linde. What are these two options which we have? We try to evaluate and try to, in terms of which is the best one. But still, there is a lot of learning which needs to happen to come to a conclusion that which is better. So we evaluated both the technologies, which is Starbridge indirect as well as Starbridge direct technology. When it is Starbridge indirect technology, the resistive heating element is on the walls of the furnace and the electricity is applied to the resistive heating elements which is on the walls, and the radiation happens, because of which the heat transfer happens and the heat is being transferred to the coils. Whereas in direct heating, the resistive material is directly imposed on the coil itself. These are proprietary coils and are much efficient in many ways than the indirect. But nevertheless, I cannot conclude that any of the technology is better at the moment. Though direct heating has some advantages, which we will cover in coming slides. So what was our target? Target was to reduce the CO2 in terms of avoiding it by 90 to 95%. Why 95% or 90%? Because some amount of the coke formation is there, and that will occur because of the inherent process of cracking. So 5 to 10% you can say that CO2 anyhow will be emitted in the form of coke. Then the second was that it has to be flexible. It has to be easily adapted by the industry. And the third one is that it has to be easily, I will say, integrated with the existing crackers, as well as technology ready for the feed and EPC execution. These were some of the highlights or the goals which we had kept in front of us to achieve by providing this technology. Now, where we are in terms of technology development, it's done. We have worked with various partners, various vendors. Earlier, we used to understand burner management, flame infringements, or hotspots. Now we are more understanding electric equipments, transformers, thyristors. So those knowledge transfer was there. And after that, we came up with a demonstration plant, which is, as I said, in BSF, Germany. And this is in operation for almost now more than a year. And we are still learning about the behaviors of the furnaces and how once option is better than the other one. More about the demonstration plant. It's a 6 megawatt electric power is being supplied for a feed of 4 ton per hour of naphtha, producing cracked gas, and which is being separated in the commercial scale BSF plant adjacent to it. So it's a running plant in which the cracked gas goes and is being used for producing ethylene, propylene, and other valuable components. Here, the electricity is being used is renewable in nature, and both direct as well as indirect heating will have preheating concepts as well as cracked gas cooling as a part of the furnace offering. The basic learnings which we had in terms in the demonstration plant was actually we wanted to validate our tools and methods which we have adopted. We have first time done e-HICC, which earlier for the process we used to do only HICC. For the electric verification and the safe operation, we have done e-HICC also. Other than that, TUE was involved into the certification of the entire demonstration plant. We have interacted with, when it comes to procurement, we have interacted with various vendors, especially electric suppliers, telling them our requirement and they meeting our requirement with their innovative designs for both direct as well as indirect heating technologies. Factory acceptance test. In terms of construction, we have learned more about assembly procedures. We have developed them in terms of tolerances or fits for the construction which we have adopted in this demonstration plant. Apart from that, during commissioning, sequence procedure with respect to electric elements, transformers or thyristors, star delta connections, those were incorporated in our sequence procedures, and ramping rates extra were analyzed. And with respect to operations, run times, yields, I will say that slightly better than the conventional furnaces we have already achieved. In terms of, I will say, different behaviors, transition behaviors, we have learned how it operates and how best it can be operated. Then the maintenance efforts for electric components as well as for the coil or for the entire furnace, those aspects were discussed and learned. Now, as the demonstration plant is already operating since last more than 1 year, so we have commercial design available and we are offering to our clients, esteemed clients. Just to tell you that we are receiving, I will say, queries or inquiries with respect to study of various small scale furnaces as well as add-on furnaces to the tune of say around 40 to 80 KTPA single furnace. And that's where we are working with our esteemed clients. To start with the commercial design aspects, we have the radiant box design which is available. We can offer both direct as well as indirect heating solutions. We have feed integration. It can be done with power. It can be done with steam. That both options are available and we do offer it on case-to-case basis to our clients. Then the process safety aspects have been taken care of.
in terms of in case of rupture of any of the tubes or any malfunctioning of the furnace, what kind of safety provisions are there in the furnace so as to address to them. And power supply concepts in terms of thyristors or transformers or electric supply systems, we have come to a conclusion. And general arrangement in terms of the furnace geography, and good to tell you that we can fit into the location, or the size we have come up with is identical to what a commercial scale furnace size will be. We have different options, and we can offer them as far as general arrangement is concerned. To give you some aspects, when it comes to heat integration, you can see that we can use steam or power, both for preheating of the feed. And then we have our own flex feed exchangers. It can be clubbed with the secondary or other heat exchangers as per the need. With respect to maintenance aspects, you can see over here, the blue one which is shown over here, it is for removal of the coil, and based on the requirement, we can open up the radiant box and remove the coil. Let me tell you that in both indirect and direct concepts of Starbridge, we have seen that the coil life is much better than the conventional, I will say, conventional life, conventional furnaces with coils. And as far as furnace or maintenance space is required for electrical components, you can see that at various places we have left some space for the maintenance of electric components. So, as I conclude my presentation, I would like to summarize it that Starbridge is now a commercial design which is established and is available to our esteemed clients. Demonstration plant is integrated one, and it produces cracked gas so as to for production of real products. It's not a pilot or a lab scale plant. And we are ready to offer the feed and EPC execution for such electric furnaces under Starbridge technology. Thank you very much.
Thank you, Mr. Kaul. This is a new technology, and I just want to ask Mr. Kaul, are you getting inquiry for from the customers for the commercial design?
Yes, sir. Okay.
You have already...
Yes, as of now, we are receiving inquiries for replacement or add-on furnaces.
Not for new plant?
Not for the new plants.
Okay.
Because still we want to test the waters with respect to less than 100 KTA furnace sizes.
Okay. Thank you, Mr. Kaul. Thank you very much.
One more question I can ask, Mr. Abhijit.
Yep.
This is regarding, you are talked about in the furnaces used in the mini crackers. Actually, this electric furnace is one of the key transformation areas in the decarbonization sector in the refinery side. Are you, because most of the heaters in refinery, even the secondary side heaters, they start maybe 6 million or 10 million kilocals and above. What you have shown was 6 million kilocals capacity.
Right.
Are you into the refinery side also, supplying heaters?
See,
because this is one of the challenges which we are having.
Yeah. See, at moment, these furnaces are very critical, and these are being offered as a part of the technology offering
full
of
package.
cracker
Okay.
from us. So we will definitely, in the second phase, we will look into refinery heaters as well, because though that is not our core business. Okay. Our core business remains as furnaces, but
large scale heaters, we have it in mind that we will offer it.
Okay, that's a nice presentation.
Thank you.
So next session is Mr. Banerjee from Honeywell EOP. We will be discussing about energy technology, the next level, how to recover the heat and improve the efficiency. Welcome, Mr. Banerjee.
Good afternoon. I am audible, right? Okay. So let me first start by thanking CST, BPCL, and also my session chairs for giving this opportunity to come and talk to you about low-level heat recovery. So we have heard yesterday, a few of my takeaways from the sessions yesterday was, it was really fascinating to know that the energy demand of the world growth, India is about 25% of that. So it's a substantial thing. Then we heard about how energy efficiency is important because the energy intensity index preferably should be below 80. I think that's what the refineries are targeting, and how to bring down emissions by reducing CO2. So we'll be discussing mainly about efficiency and how to increase efficiency by recovering waste heat. Keith Couch, in his presentation yesterday, talked about how do we understand efficiency, right? It was like carbon, water, hydrogen, utilities, emission, and these all acting together to reduce or optimize the capex. We do understand that the plot area and the time of implementation is also important, but here, let me talk about a level of energy which cannot normally be captured by process integration. My friend Abhijit will talk about, I think, about pinch analysis and all those things. So this typically is the heat, which is the cold utility of pinch. Means you have to reject at a very low level. Okay, so this presentation will have some forward-looking statement. It's like some predictive statement, and take it in that spirit, and we will go forward with that. So this was typically the level of heat that I was referring to, heat which is in the temperature range of about 140 to 80, typically 130 to 70 kind of temperature range, which is the air condensers. Basically in the refinery, these are the air condensers to which this heat is lost to air. And if you know, everybody knows that your refinery, this is a substantial amount of duty which goes to the air. And it normally cannot be recovered, but it's at low level because you cannot integrate it to the process. So let's see how we can integrate this low-level heat to the process. So typically, what we can do, we can either elevate that heat to a higher level, to a higher temperature level, so that we can use it in the process again. Or there is an alternative where we can use this heat and we can convert it to power. And organic Rankine cycle, this is nothing new. This has been in the industry, so you can recover the waste heat in terms of power. And whereas the other one is typically a heat pump, where you can elevate the heat, take it to a higher level, and then use it in the process. Very, very on a high level, this is what we intend to mean, like in a heat pump, in a MVR, which is also a heat pump, but is using a water or steam as a driving fluid, and then the organic Rankine cycle. So fundamentally, what is happening? There is a low boiling point liquid, which is kind of picking up heat from the process condenser, which is actually the evaporator in its case. It becomes vapor. So when you go into a heat pump, you are compressing this vapor. So you are utilizing energy from outside, electrical energy. So you are compressing this vapor, and if you compress a vapor, your temperature goes up. And then you use that temperature in some process reboiler or for process heating. MVR is a similar thing, means you use the process condenser and you generate low pressure steam, then you compress the steam to take it to higher levels. And you can take it to the levels you want it to, depending upon the number of compression stages and the power that will be required to drive it. As you know, that these are typically defined by something called coefficient of performance. So it's the amount of duty which you can give to the process divided by the amount of power which you use in the process. So typically the higher the COP, the better the process is. On the extreme right, the organic Rankine cycle is also similar. There is a low boiling point liquid which is vaporizing, and instead of compressing it, now you use it to take the power out of it. So it will go through a turbine instead of a compressor, and it will give you power which you can either use in the process or you can put it in your grid, depends upon how you want to use it. So you can see that in both these processes, it's happening that you are using some kind of mechanical force, right? It's like a thermally driven mechanical process. So in one, you are using the energy to compress, the other, you are rotating motion of the turbine is helping you to recover the heat in terms of power. UOP has been doing heat pumps in its technologies, in many of its technologies, and typically, as a rule of thumb is, if you have two components in a column which is boiling pretty close to one another, maybe a difference of 1 or 2 carbon number, then you can maybe use the condenser heat and then compress and reboil it. So what you do in the process, you actually save the steam, because generation and steam leads to emissions and is not that very CO2 friendly, CO2 emission friendly. So you are cutting back on your steam import or steam generation, and you are using the process heat itself to reboil. And it moves, obviously it will move in a loop, it will condense, come back, and again go in the same thing. MVR, as we talked about, is steam doing in this process. Instead of a low boiling fluid, it is water which is moving around, and it is getting steam, compressing steam, and then coming back. Organic Rankine cycle you are generating power out of it. But one important thing here is you are limited by the thermodynamics, so you are limited by Carnot efficiency. You can't exceed that for any reversible engine, as you know. So lower your sink temperatures, means the lower your cooling water temperatures, or you can reject the heat at a lower level, you will get more efficiency, because that is how the whole process works. We heard a lot about innovation yesterday, right? So these processes, although are effective measures to improve your efficiency, it uses some mechanical element in it. So, and it is known, but the way we use it for process is something which is different. Now we heard about innovation. So here is something where it's a novel, innovative technology. It's called Q-pinch. It is developed by a company in Belgium. And now EOP and Q-pinch has an exclusive alliance. So, which leverages kind of EOP's extensive experience in technology development, licensing, design, and then our expertise in modularizing and using the global network of customers which we have. So these two in combination, we are bringing this technology to our customers. So what does it do? Now fundamentally, it's a very simple thing. It's like a phosphoric acid solution which is moving in a loop. So if you see the cold reactor, it is nothing, the first step is an endothermic reaction which happens. That means it takes it in from the process. So your waste heat, which is at low level, will be taken in the endothermic reactor, and phosphoric acid molecule will dimerize. When it dimerizes, it releases water. So it's an endothermic step. It dimerizes, it releases the water. The water which is separated is then heated by using a part of the heat from the waste heat itself, which is coming from your process, and is converted to steam. Now the dimer is taken to the hot reactor. We call it the hot reactor. And this steam, when it contacts the dimer now, the reverse reaction takes place. That means the dimer breaks into the monomer and it releases heat. So because it releases heat, the temperature level goes up. So what we saw in the last two, that it was thermal and mechanical. Here you see that's a thermal process boosted by chemical reaction which is happening. So this is what it is happening. Means in the forward direction, the endothermic step is two molecules combining, releasing water, and the exothermic step is it coming back to the monomer again. So it is moving around, and it is increasing the level of the heat by the heat of reaction which is happening in the whole process. It looks pretty cute and pretty innovative, but The next question is it simply on paper or we have something running right now? So as we speak, it's a very flexible energy, and because one of the main criteria where it is outweighs the other technologies is that you are putting in, suppose you are putting in 10 megawatt of waste heat, you'll be able to get about 5 megawatt out of it. So slightly differing depending upon cooling water temperature and the conditions. So 45 to 50% efficiency. No other waste heat recovery process can give this amount of heat recovery within the process. And it's very flexible. For example, just to give you an example, if you have a waste heat coming at 80 degrees centigrade, you will get the hot reactor output at about 120. So by the way, the hot reactor output as of now is in terms of saturated steam. So you generate saturated steam, and so for example, if the inlet is at 120, if we get a relatively high temperature steam, it can give a temperature of 200 degrees centigrade. So higher the inlet, higher the outlet goes up. So 200 degrees centigrade will be about a saturated steam of about 15 bar or something like that. So that is how it can boost up the entire process. So as we talk, there are units already operating, although in Europe, but the one which you see on your extreme left is for a LDP unit. It's in Antwerp, Belgium. And you can see that it picks up heat from different sources. So it picks up heat from one source at a time. It is so flexible that you can change it to another process. So you can see, depending upon the inlet temperature, the pressure of the steam at the outlet is varying. Because the inlet temperature less, because the delta is a little less, the inlet temperature goes up, it goes up. The second thing, it's also, it's called ethanol vinyl alcohol copolymer plant. It is also in Purare, it's in Belgium, and it's same kind of 1.3 megawatt. Here, there are two columns from the condensers of which this is picking up heat and then giving the heat back to the reboiler of the column. By doing so, it cuts back on the energy requirement by 50%. So you can imagine 50% of the steam can be backed off, is no longer required. It's self-sustaining. The third one is one we are really very proud of. It's a kind of our demo unit. We are doing all the improvements in hardware, software here, and we can emulate customer design conditions here and can show you the lift which we can give for a particular process, and customers are welcome to visit this plant. It is in Belgium, but in a different site. And we are also working with global customers now to go to different refinery processes and use this to recover the heat. Typically, this is the one I was talking about, picking up the heat from the overhead condenser and then use it in the reboiler. Now, although it is illustrated for this process, you can well see that it is not limited to this process. It can be used for other things also, other processes also. An example of how it is done in traditional refining. This is a hydrocracking unit. You can see the different sources of heat from which it picks up. And again, you see that instead of about 22 megawatt inlet, you are getting about 11. So kind of 50% of the heat is available. This is for a renewable jet fuel unit. And so it's kind of process agnostic, means as long as the waste heat is there, it can use it. It can use it. It depends on how we configure the heat pickup. And then you need to have a heat sink. That is very important. Means you can pick the heat, but where to put it. So that needs to be identified. And we are more than willing to work with you. So it's kind of a very simple kind of questionnaires which we work, and we do the initial screening, which will work with you to develop the project. And as Matt said in his plenary session, that be bold and take and adapt new technologies, right? And we are there to work with you at every step. So with that, I think thank you. And I think I give 1 minute to Abhijit extra. You can take the time. Thanks a lot.
Thank you very much. It was a very interesting session, low-hanging fruits. This has to be adopted and bold steps to be taken. So I hope everybody here has taken a can work with EOP to find out some real solution, and this type of 50% efficiency recovery is a good proposition. So thank you very much, Mr. Banerjee.
Hello. Yeah, Mr. Banerjee. Actually, it's good to hear a new type. Always we have been hearing about the Rankine cycle, organic Rankine cycle, and now we are also introducing the chemistry also into the process, dimer, monomer, reconversion reactions. What are the challenges you had in implementing in refineries? Anything you found on the metallurgy front?
Which one?
The new one, the Q pinch, especially in the metallurgy front, because
So it's a great question. And metallurgy-wise, as far as heat pickup is concerned, we use a kind of tempered water loop, which picks up the heat and takes it to the Q-pinch module. So there is no direct interaction between the process, okay? So your process metallurgy does not change. As far as Q-pinch unit is concerned, there, as long as you are, it's not that even if you give us a higher inlet temperature of 150, 160, we will take it to even higher temperatures. But in that thing, the metallurgy of the Q-pinch unit will go up because you have phosphoric acid moving around, right? So although it is a very benign phosphoric acid which we use, it's kind of the same thing which is used in Coca-Cola, right? So it's kind of edibles, the variety that we are using. But if the temperature goes up, then the corrosion rates goes up. So we have to give the metallurgy accordingly. So the capex goes up. So the unit is perfectly capable of doing that, but the metallurgy should be adequate. So no change in the process side. The Q-pinch module is designed as per which services you select. But these are the services you need to look for us to look into, and accordingly we can decide what will be the capacity and what will be the load.
So our last session today is from Mr. Abhijit Ram from EIL. He'll be talking about novel methodology adopted. This is a live case for selecting optimum revamp configuration for CDU and VDU. Let us hear from Mr. Abhijit Ram. Welcome, Mr. Ram.
Yeah. Thank you, Session Chairman. And special thanks to CHT for giving me this platform to present my case and methodology, what we have adopted for revamping the CDU units. Of course, it applies to other units, but since we have applied, and we have been applying for this over the years, so we have tried to put some new dimension into that, and we will try to present that. And before that start, I think I have a tough work at my hand because I am standing between you and lunch. That I know, so I will try to finish it as quick as possible. Because in a project implementation, the last phase, the construction, people have the most difficult work because they have to catch up with the schedule. So I have to catch up with the schedule because I'm the last speaker here. Anyway, good afternoon to all esteemed guests here. So what is new? So why are we speaking about CDU revamp options? There may be many questions crossing your mind. What is so new about a revamp option? That answer I would try to find through my presentation. At the end, when I present a case study, and with some numbers, you will understand why this case is different and how you can evaluate a revamp not by the traditional way and the myths that we go. I'm trying to present a different way to look at the revamp options. So that is how the crux is. So my presentation will be divided into three different spaces. One is that how the typical revamp options looks like, and we all know about that. Second is that what is the comparison between traditional methodology and the methodology which now EIL uses. Evaluation criteria, basically, what is the evaluation criteria we are talking about? And third is a small case study which will corroborate or which will farm of the findings of the methodology. This is how it goes. So I will skip we have some slides on the EIL capabilities that I will skip for the paucity of time. So I will directly go to the typical revamp requirements. So we all know that typical revamp requirements comes from capacity expansion for higher good throughput, product yield structure. This is important because even if we don't have a downstream integration of petrochemical, product yield structure is also important to revamp the unit. Energy efficiency, when we talk about energy efficiency and footprint, these are closely related. And we talk about energy efficiency, we will talk about in my presentation in the later part, is that you have to quantify. Energy efficiency is a very vague term. Nowadays we quantify it with energy numbers. So feedstock flexibility for heavier opportunity crudes, this is the upcoming subject for any refiner. And integration with petrochemicals, that is how to retrofit your refinery with petrochemical unit. Next, what are the challenges of revamp? This all we know. The revamp, two things are looked traditionally. One is cost and another is the time of shutdown. So we have added some more flags. Look at the last flag at the left-hand side is the energy number. So this is the key of this particular presentation. And then ease of constructability. The ease of constructability means it is not, there is a thin line between the constructability and the ease of modification. Constructability would be to avoid all surprises during execution. That is how it is being done. That is we define as constructability in the stage of inception. So this is typical revamp options. We all know, I will not spend time on this. Addition of free flash drum, column internal modifications, installation of pre-fractionator, pump sizing. So this is, now what are the non-conventional revamp options? This is prelude to what is coming up. A parallel crude column, can we do that? A parallel crude heater or parallel preheat train or all of them together. So this is what are non-conventional revamp options where you can go for a clean revamp. We are talking about a clean revamp with ease of modifications, least amount of modification, but with a better energy number. So traditional methodology versus novel methodology. The criteria are defined on the left-hand side. Design approach, the energy efficiency, capex, ease of constructability, shutdown duration, and flexibility. So design approach, obviously the traditional methodology or whatever I have written, you know all that modify the existing crude column and add free flash drum or free fractionator. Because the biggest challenge for any revamp, whether it is a yield structure changes because of the crude basket changes or you are doing a capacity expansion, the heat is on the crude column. Because you have high traffic going through the crude column, how will you manage the traffic in the crude column? That is the biggest challenge. So that is how it is done. Now EIL's methodology is that you have multiple configurations you have to evaluate. It is not that simple the way we used to do. Do the simulation, do the modification and just put it on the PNID and execute it. It is like that you have to multiple configurations, you have to look at it from different angles and then finalize what is the best configuration. Then energy efficiency, which I have said, there is optimized through energy number analysis. This is the key. And capex, of course, once you get many configurations, you will get many different capexes. That I will come. So, ease of constructability, shutdown. Shutdown is known to everybody. Of course, in a shutdown, when we are talking about a parallel train and modular structure, you have lower shutdown time because we are not touching the existing unit. So EIL's evaluation criteria, once again, the energy intensity, shutdown duration. It is just follow-up of the earlier slide, capital investment, constructability, and plot fit. So we are talking about a clean revamp, only it is possible if you have a plot fit. Reuse of existing equipment. So case study. So this case study is basically to check whether we can do a revamp without doing minimum, without touching the existing unit with minimum modifications, and mind it, we are talking about a capacity increase for a more than 50%. So what is new in this? The new is that even there are stages of modifications or stages of revamps we can do, like 30%, 40%, 15%. So 15 to 20% typically by a thumb rule we can manage with a pre-flash drum if it is not originally there. With 30, 40% we can do with a pre-fractionator. More than 50%, yes, EIL have done it in earlier stages with 60% revamps with a single pre-fractionator. But no more that approach is taken now. So that is how it is. So we are talking about whenever you're going for 50% or more capacity increase, you should look at a different way how this revamp should be done, looking at all the angles, looking at all the options. So this was the objective of the case study: energy number, minimize capex, asset reuse, that is a basic requirement of any revamp, implementation, ease, and space feed. So this was for the case study, it was very difficult for us more because this is a generic case study. This is not a very typical to any refining or in any particular unit. It is a basically generic taken from all the revamp options what we have studied. So if you have a single design case, your life is simple. If you have two design cases and with so much variation of API, like it is one is less than 30 and another is more than 40. So you are in a dilemma. So you are sure before you start the process, you know that your crude column is going to hit. Your internals will change, your nozzles will change. How will you handle it? So we had 4 or 5. In fact, we do many models, maybe 10 models, 19 models. And here I am just summarizing with 5 configurations. So we will deal about 3 configurations, which are extreme cases. First configuration, which is the traditional with a configuration of upstream prefractionator with utilizing the existing preheat in the circuit and with the possible lift of naphtha. The second configuration is this is the one with a prefractionator. Then I will come to this later. Then the second configuration where we will use a heater upstream of the prefractionator and check. This is the objective of this doing is this. When we do this, we're trying to relieve the crude column as much as possible. And that can be done only with a crude in one more heater upstream of prefractionator, because that will give the lift which is required to relieve the traffic in the crude column. So this is also a good option. These also can be tried. Now coming back to the option which you can select is this option. Is that although it is against the mindset, many people who are sitting here might be knowing crude unit and the revamp options. So this is against the myth, this is against the mindset. So if you do a parallel crude column and along with a crude heater, probably it will give a better energy number. And of course, it might offset with the capex slightly. But so new stabilizer in parallel, we didn't struggle with the stabilizer also. And then minor nozzle modification is the crude column. So we kept the crude column clean as much as possible. So what are the advantages? A very lower energy number, short shutdown time, and because the walk was going on parallel, and parallel setup and minimal times. So I will come to this slide. This is the entire the study or under the options, evaluation of the options or criteria for evaluating the options hinges in this particular slide. Now here you see X and Y are the numbers, are the basic configuration what we have chosen. That is a basically traditional configuration. X is configuration with a capex value. This is related to the prefractionator with only naphtha. But what we do, typically we take out the naphtha and then rest of the thing we put it in the crude column back. So this is the basic configuration, configuration 1, which is X and Y with the energy number and a capex value. Now when we go to the configuration 2 or so configuration 5, where we have taken out the naphtha, light naphtha, heavy naphtha, total KRO, entire the KRO band. From the prefractionator, we need a heater, I told you earlier also. Then the capex is also high, it is 17% high, and 5% high is the energy number. So we had to forego this. Then what was the option left? The option left was to put a crude column and a crude heater. Surprisingly, we also found that although the capex value was slightly higher, 11% higher, the energy number was 90% of the earlier configurations. The configuration which prefractionator and with naphtha. I told you we have done this with 66%, 65% revamps with only prefractionator. because there was no different thought at that time. So when we introduce this parameter of energy number, so we come to this table. So although the capex value was 11% higher for configuration 3, we selected this because we calculated the capex value and we checked with the energy number, the recovery paid off. Recovery had facilitated the payoff of the enhanced capex in no time, maybe less than 1 year or something, I don't remember, but it is less than 1 year or maximum 2 years. So that's how we overcome all the challenges of a huge revamp of 55 to 60% revamp without touching the existing. The only thing, the problem here you can face is that the turndown. So if you can manage with the turndown with interconnection flexibility between the two trains in such a way and design the unit with adapting suitable controls, we had to design control because there will be challenges in the pre-flash jam overhead vapor controls. It is not so easy because you have to space it to the two crude column flash zones. Then you will have a challenge with the preheat train. The idea, the most important thing or the flexibility is that you don't have to touch the existing preheat train. And why this energy number increase? Because in revamp, you cannot increase the energy number. So everybody must be thinking, how can it be possible? Yes, it is possible because you have a new preheat train and you can maximize the preheat number. We have achieved the numbers like, say, 319, 318. We have the lowest CDVD running in India with lowest energy number at HICC. So we employed that same idea. We had a parallel heat train, and with that balanced the overall loss in the energy number in the entire unit. So this is how we have done, and this is how we have achieved lower energy number and selected the configuration. So whenever the moral of the story is, whenever going for revamp options, more 40 or 50%, evaluate with all this, rank it with respect to energy, with respect to capex. Of course, the third dimension has not been taken because it is not easy to quantify constructability. I think we are running out of time, so I'm coming to this novelty. This is a novelty which I have already explained. Multi-criteria matrix, energy plus cost plus constructability, and by list of the thing you know. And this should be the benchmark for Indian refineries in the future to come. And so finally conclude, EL's methodology delivers a structured and practical approach to revamp selection, not the traditional way. Parallel crude column, lowest energy footprint, minimum disruption, fast rate of returns, and a benchmark case for energy optimized CDVD revamp. Thanks for listening to me.
Thank you, Mr. Abhijit. It was a nice presentation, but I have a small query. You are basically comparing capital cost along with energy cost, and you said the payback is coming less than 1 year. Is it absolute conclusion that everything will be like this, or we have to evaluate each and every revamp case?
No.
Energy versus capital cost.
It is. That's why I've said the study, or the presentation is about the approach you will take to the options.
Yes.
So every option has to be evaluated.
Yes.
Some, I said that it is also, the basic assumption is that the capacity increase should be more than 50 to 50, in the range of that. If you are revamping, because nowadays the expansions are like that only to fit the downstream, to retrofit the petrochemical downstream complexes. So if you are going below, this parallel preheat train may not work.
Yes.
So if you are going beyond 50%, and most of the revamps are coming to us like that only. So you have to evaluate this, and you will probably get this every time.
So these are the three possibilities approaches.
Yeah.
We have to evaluate those three approaches. Whatever the best configuration is coming, energy versus capital cost, that will be selected.
Right, but these are the three approaches I have listed here. Yeah. Actually, when we did the study, there were up to Kero we have lifted. So there were studies where we have done up the naphtha plus heavy naphtha, only the lighter part of the kerosene, and then the whole kerosene. So you have to check all these options where you get the minimum energy.
Thank you, Mr. Abhijit. I think with this
one question.
One question.
Yeah.
Mr. Abhijit, yeah, it was nice to see a new approach, adding a parallel crude column. Here in this configuration, we have seen that the VDU capacity, the VDU column, there is no big modifications, but there is an increase in capacity. Was there any change in the crude diet before and later? Because the overall economics includes the crude.
Yeah, you're right. Very good question. This was a change in the crude diet. Originally, the crude was around, say, this is actually mix of 2-3 revamps. So the crude mix, you can say, was 27, 28 API like that. Now, when we try to revamp, we have gotten our hand in more than 40. What shall we do? So we know that right from the day one that more than 40, it will take away the crude column. So you will have many internal change and probably the nozzle modifications. Now, coming to the vacuum column, here one thing what I didn't say is that energy number can also be optimized in a revamp, not only with a parallel crude pre-trend. In a revamp we have seen, I will not mention, but in a revamp we have seen where we have not changed the vacuum column, but the vacuum column parameters, the operating parameters were very haywire. So when we modeled it once again for the revamp options, we have reduced steam appropriately to minimum steam required to run the column. And that has also contributed to the lower energy number. So it is a multiple, I have only highlighted one. There were multiple areas where we have worked. So that how, otherwise in a revamp you cannot do it energy number.
Yeah, okay, nice presentation.
Thank you.
So any question from the audience, please?
Mike.
Sorry, I'm just taking just 1 minute. My question to Mr. Soumendra Banerjee. I've just got one quick question for you, sir, if you permit. The question is that Honeywell and Q-Pinch has done a collaboration for a kind of waste to energy. So my quick question is that collaboration on a broad way, it is a equity-based business model, or it is a kind of technology collaboration, or is it a kind of technology transfer? Can you just quickly answer this?
So I am not at liberty to disclose everything on the business model, but it is definitely a collaboration. And we are working together on all the projects as of now.
So suppose if any company wants to implement this kind of facilities in their premises,
they can approach UOP.
The Honeywell or?
Yeah, it's Honeywell UOP. It can.
Okay.
Same thing.
Thank you.
Yeah.
Thank you for your question. And respected panel, we don't have time to take more questions, but of course the audience will connect offline. But anything that chairpersons would like to say to conclude?
Thank you, all our panel presenter. It was a very thoughtful presentation for each of you. Everybody who are here should have some takeaway from this presentation. And if you can take some lessons from it and can implement, then only these sessions are successful. New technologies are coming. Those, unless we adapt in this changing scenario, we have to act very fast, as said yesterday. So there are a lot of benefits available, whether it is integration or whether it is energy efficiency, whether it is revamp. So I request everybody, please be in touch with all these people and take the maximum benefit out of them and implement in your refinery, petrochemical, or wherever it is. And then this type of program will be successful. I think, thank you very much. Thank you, everybody.
Yeah, thank you. All these presentations were again aligned to our refining towards achieving sustainable refining in the future. And though there are less questions from the audience as of now, I'm sure the questions, whatever questions are there, they can be mailed later, so that the people in the panel would be able to answer that. And I think it was a good attendance with respect to we're closer to the lunch and second day. Anyway, thanks for the patience and listening till the end. Yeah, thank you very much.
Thank you, gentlemen. Thank you so much. Ladies and gentlemen, please request for a round of applause. It's been truly a phenomenal session. And with that, I request Mr. Abhijit Chakraborty to step forward and present mementos to our esteemed distinguished speakers, starting with Mr. Chiranjeev Haldar. Thank you so much for your time, and thank you for sharing your thoughts with us. Big round of applause. Thank you, ladies and gentlemen. Mr. Chakraborty to present a memento to Mr. Chetan Mittal from Topsoe. Thank you, sir. Please keep the applause coming. I request you all to applaud the expertise that we get to witness here on stage as a part of ETM 2025. Mr. Sunil Kaul, thank you so much for joining us and sharing your valuable thoughts with us. I now request Mr. Senthil Kumar to step forward and present a memento as a token of appreciation to Mr. Somendra Banerjee. Thank you, Mr. Banerjee, for your very insightful presentation. Truly impactful, I must say. Mr. Abhijit K. Ram, thank you for joining us. Thank you for your participation and your valuable inputs. May I take this opportunity to invite Ms. D. Padma, ED, Corporate Planning, IOCL, to join us on stage and present mementos to our respected chairpersons. Mr. Abhijit Chakraborty, thank you, sir, for ably moderating this session. A round of applause, please. Mr. Senthil Kumar, thank you for your contribution in making this panel a success. Can we keep the applause coming, ladies and gentlemen? And with that, I request everyone to please step forward, come together for a group photo. We'd like to cherish this very moment for years to come, all the amazing brilliance and excellence that we get to celebrate on stage. A collective round of applause once again, ladies and gentlemen. Thank you so much. With that, we take a break. We break for lunch. We come back at 2 p.m. for the next session. So please ensure that you look at your schedules. We have parallel sessions happening in the adjacent hall as well. So if you are a part of the next session, which is session number 8, technical session number 8, which will happen here in Hall A. So we'll see you all at 2 p.m. Enjoy your lunch. Thank you so much. Lunch is served at Hall 4. Yeah, so thank you so much. Join us for lunch. Enjoy your lunch, and I will see you all at 2 p.m. sharp as we resume. Thank you.
In a time of significant transformation in the energy sector, Baker Hughes remains committed to its mission of driving sustainable energy development.
Let's show some impeccable energy as we resume the session. Everyone, come on, put your hands together. Not bad at all. Well, on that high note, I take this opportunity to welcome our moderators for the upcoming session. The topic of discussion is driving innovation for operational excellence and reliability. And to take the session forward ably, may I please request you all to put your hands together and join me in giving a warm welcome to Mr. Prasad Panikar, Chairman, Naira Energy Limited. His areas of interest: environmental, social and governance compliance, decarbonization strategies, carbon markets, refinery turnaround and modernization, artificial intelligence, digitalization and cybersecurity, workforce development and skill enhancement. A few of his achievements: Tech Business Leader of the Year, Danone Business Leader Award, co-chair of FICCI Committee on Hydrocarbons and President of Kerala Management Association. Another round of applause as we welcome Mr. Prasad Panikar. Welcome, sir. Joining him on stage is Mr. Abhay Raj Singh Mandari, ED, Mumbai Refinery, BPCL. Please put your hands together and join me in welcoming him onto the stage. His areas of interest: chemical engineer with 35 years of experience across diverse refinery setups in India and abroad, led operations, technology projects and HICC functions. Unique distinction of heading all three BPCL refineries, Mumbai, Kochi and Bina. Many achievements of his, but a few to mention: played key leadership roles in establishing and stabilizing MRPL, NRL and BOIL refineries, delivered major products like hydrocracker and CDVD units across refineries, led value-added initiatives including MS Block at NRL and capacity expansion at Bina, contributed to renewable energy projects like solar at Bina and CBG at Kochi. Let's give him a warm welcome with a round of applause, everybody. We can do better than that. Come on. And now it is my privilege to welcome our eminent speakers, our distinguished speakers to the stage. Mr. Manoj Prabhakar, Independent Project Analysis. Please put your hands together. Welcome, sir. Mr. Shekhar Gundal, BPCL, joining him on stage. Welcome, sir. I do not hear the applause, ladies and gentlemen. Keep it coming as we welcome Mr. Varun Nidhi, Kinman Innovation Private Limited. Mr. Naresh Kothari from HPCL, joining the dignitaries on the dais. Mr. Bilal Ghosh from Baker Hughes, India. And Mr. Manish Saraswat from Loinville Basin, joining the eminent speakers on stage. First of all, let's extend a warm welcome to the brilliance that we get to see here on stage. Can we collectively celebrate the brilliance that we have here on stage? Come on, everybody, please put your hands together. For any questions at all, let me remind you that we have QR codes. We will not be able to take organic questions like asking you to raise your hand. We will have to do it digitally, so please scan the QR code during the course of the session and send in your questions. And towards the end, if time permits, we will be taking your questions. With that, over to our moderators. Gentlemen.
Good afternoon to all of you. We know that it is very difficult, second day after lunch, but we will try to make it as interesting as possible. My dear colleagues, it is a great privilege to chair this very important session on driving innovation for operational excellence and reliability, extremely important for us. And when it is read along the larger theme of this two-day conference, that is on Vikasit Bharat and sustainable refining, the relevance of this topic is extremely important. But at the outset, let me congratulate Center for High Technology and BPCL for successfully organizing 28th ETM. I am very happy to note many new initiatives this time, ETM. Now let me welcome my co-chair, Abhay Bandari. As it has been introduced, he has got very wide experience in multiple organizations in multiple countries. So Abhay, welcome. Let me also welcome all the speakers here. They will and hopefully they will share good insight for all of us. And let me also welcome dear colleagues from the industry, including my boss, Ramchandran. He is here. Friends, Vikasit Bharat reflects a national aspiration, all of you know, by 2047. It is not whether we become a 30 or $25 trillion economy or GDP growth. More than that, it is actually a reflection we need about the lifestyle of Indians. That is exactly what is needed. So the measure should be the Human Development Index All of you know currently we are less than 0.7, we need to go to 0.9. Studies indicate it requires multiple times of energy, at least 3 to 4 times of energy. And as has been said yesterday, and in the recent reports, it is very clear that oil will continue to play an extremely significant role for many, many more decades. There is no clarity issue now on this. And in India, it will be, you know, that much, much more years. So the relevance of refining, that is our core job, will continue for many years. And in this context, we have to look at how to make a refinery more reliable, more efficient, while we move towards a sustainable future. There was a tendency for us in many last decades, expanding capacity and expanding efficiency was something we were focusing, and we were very successful. Now, in the recent benchmarking study also, I was told, Indian refineries have performed outstandingly in the global benchmarking. So we succeeded in making refineries efficiently. But the same journey further will not make us competitive or make us relevant. It requires a growth which we have to be more cleaner, we have to be more digital, and we have to be more resilient also. Why it is resilient? You know that when we go from this current development to a developed country, we have to face many challenges on this. So this is the context of, first let me talk about reliability. You know, the reliability would decide what is their cost of production. Because a frequent downtime refinery will not have a very good GRM or margin. That will impact our ability to meet the demand, and obviously that will also impact your sustainability target, including energy, including the carbon emission. So reliability factor is extremely important. And you know that we have got one more responsibility from April this year, 2025. Carbon has got a price. The emission of carbon has got a price. This is a good opportunity for us to make some of the projects which we have not implemented so far to make viable, since you have to pay a price if you have to emit more. So it is good opportunity for us to improve on efficiency, improve also on the part of reliability. So good reliability projects and efficiency project will find more attractive when you started making a price for the carbon. So we have to use all type of tools available, including the digital tools, to ensure that we are improving on efficiency and also on the refinery. So what is that required actually? We need a culture. We need a culture of innovation for a continuous improvement. It is not at the control room alone. It has to be up to the boardroom. Each and every employee has to participate. So most important thing, I believe, for a transition from a refinery of our current nature to a sustainable digital refinery, which has to be cost competitive and also ensure the availability of fuel to the Indians, we need a very agile, highly competent people. That is the most important thing. I am very sure that the 6 experts we are speaking today would definitely enrich you with the new tools on the subject. Now I will hand over to my co-chair. He will be driving this session, and we will ensure that the presentations are limited to 10 minutes, and we will definitely open last 15 minutes for a Q&A depending on the availability of time. Thank you very much.
Thank you, Prasad Panikkar, sir. It's an absolute honor to be part of this session with such a knowledgeable, experienced delegates. Our gurus are also sitting here with such a distinguished panelist and also chairperson of the session, a stalwart like Mr. Prasad Panikkar. So we have total 6 papers in this session, and we have 1 hour 45 minutes. So we have a lot to cover. So what we'll do is that straight away we'll go to the paper presentation part. For each presenter, I'll request that try to limit it to as short as possible because we need to give time for the Q&A session also. So try to limit it to 10 minutes, but 15 minutes is the outer time limit. So please try to close within that time. Without much ado, I would like to invite Mr. Manoj Prabhakar. He is director in IPA, and he will be presenting his paper about enhancing predictability in refinery and petrochemical projects execution. So, Mr. Manoj Prabhakar, please.
Good afternoon, ladies and gentlemen. Good afternoon, everyone. Moderators, fellow panelists. First of all, I'm not the cricketer. Just want to make sure that everyone understands that. It's great to be here. Thank you, CHT, for the opportunity. I just want to start with what Honorable Minister Mr. Puri said yesterday. He said that his vision is to take India to be number 3 to number 2 in the coming years as a powerhouse for supplying, refining, and petrochemical products for the whole world. That's a very interesting suggestion because I never heard that. I know he really wants to move in that direction because I thought that most of the refiners are focusing on India only. At least that's what my belief. Maybe I'm wrong. But by hearing that vision, I thought that how can we beat the other countries or companies who are doing better than us? How can we be more competitive? So what I did was in IPA, what we do is that we do project research, capital projects. That's our CapEx. That's our main area of study. We do a lot of research and benchmarking and risk assessment for them. So we work with most of the major oil and gas organizations in the world. So we have the data from all of them. So I look at a set of Indian projects and a set of global projects, see that how we are performing in India versus how the industry in other parts of the world is performing, and what are some of the best practices we can follow from the industry and incorporate into our projects. So that's what I'm going to talk about today. As we know that we have a lot of challenges in executing large projects in India, which I know that not a good things to say, but that's what if you look at the data says. A lot of challenges. We know that there are internal and external challenges. Internal means within the organizations. External means there are wars happening, supply chain issues, things like that. But what we can do is we can look into internal aspects. That's what I'm focusing here, and what can we do to improve ourselves. So I'll be looking at India projects as well as global projects and the practices. And here I am particularly focusing on one aspect, which is schedule, because that is very common in Indian projects, slipping the schedule. I looked at the cost as well, compared to the estimates which sanctioned at the time of board authorization or after DFR, versus when the project's completed, what's the status? So 0 means we are almost on, whatever we budgeted. When we complete the project, we achieve that one. And plus 20% means we, spend 20% more than the budget. So in general, out of the 55 Indian projects I looked at, it ranges from, minus 10 to, 20%. So, but the median and mean, which is roughly states around 0, which is, we are almost more or less at the money. However, when I look at the schedule, I have a different observation. On average, You can see that average is 40%, median is 30%, and it ranges from almost 0 to 80%. That means when we estimate it versus actual, the schedule slip can be anywhere between almost double what we estimated, which is pretty bad. Why it is bad? When we look at, one thing is your business case. Your business case go haywire. Your NPV calculations and whatever the market to product issues. Even sometimes you also notice that project typically slips a lot, have a lot of operability issues as well. It's a byproduct of that. So what is driving these issues? I know that I talked about external issues, but internal issues as well. I look into internal issues. So typically, why the cost is zero? Most of the time, we see that the lump sum EPC contract in India, there is very less chance of having a late changes, in those contracts. We have ironclad contracts in India. So that's actually keeping that cost part stable, but the schedule is a problem. A lot of reasons in the planning, project planning is not proper, issues in the construction, late engineering, vendor issues, permits, lack of skilled labor, land, bunch of issues as you all are aware of it. Some of the issues we know that, but I want to focus, as I mentioned, schedule. If you know that we have a strong team of cost estimators and controllers in our organization, but we have very less schedule or planners in our organization, because our focus is most of the time on the schedule side, very less on the, cost side, less on the schedule side. So I see projects which has a milestone type of schedule for $1 billion project. The project team, the owner team, says that the schedule is contractor's responsibility. That's not true, because the less they know about it, the more problem they're having at the site. A lot of reasons, because also the lack of project management knowledge within the teams is a big problem in India overall. Many organizations do not have proper systems to manage the projects. Some of systems set up in 20 years ago think that they still work in the same way. World has changed a lot. We have not adopted a lot of practices what the other organizations have practiced across the globe. And we do less planning in the front end. That's another key issues. So what I did was, I look at this Indian story. I know it's not a very nice one, but still. So I look at the global projects. I look at 100+ projects in the refining and petrochemical sectors. And then I grouped into two. One is one set of projects which are doing very well. And other one is just rest all the group, or how they perform, and see that why some projects are doing in a better way, and identified a few of the practices they follow. Okay, let's look at those practices. So this is the data set I used. Across the world, last 10 years projects, same time period as Indian project, I looked at it. Average cost is close to $179 million to $5 billion. This is a data set I used. So the practices, it's all fundamentals. Number one, clarity of business objectives and priorities. The projects, when they set it up, sorry, I'm running short of time, right? Sorry. I'll make it quick. Most of the projects do not have a very clear set of business objectives. Quantifiable business objectives, which is lacking. I want a petrochemical plant, that's it. What capacity, what the details are missing. And in between, they change the scope, which is quite normal. I have seen the projects like that. Priorities, what's the priorities? Is the cost-driven project, schedule-driven, operability-driven? What's the priorities? Most of the projects I have, Indian projects, they want everything, which is not possible to get it, okay? Having clear and documented business objectives and priorities, the first step, which drives the team, effective team, they can do it, and which drives a complete front-end loading, that is the project definition, project planning. So the team can translate that business case into a scope of work, into a project that is about to execute. That drives to a detailed baseline and integrated resource loaded schedule. Unfortunately, say that I have looked at almost 100 plus Indian projects. I haven't seen a single one have a integrated resource loaded schedule at the time of project sanction. Control grade cost estimates, a detailed project execution plan. Execution plans, typically the project team says to me that, oh, that is contractor's responsibility, not mine. That's wrong. Which drives them to have a very solid controls when they go to execute, because they know what is their cost, what is the schedule, and how they're going to execute. And here are the projects I looked at it. So the normal projects in the industry, average slip is about 24%. And the projects which followed some of the good practices, average slip is just 9%, which is within the band of plus or minus 10%. Again, it doesn't mean that you can completely eliminate the slips, because there are a lot of other external aspects which we may not be able to control. But these projects actually manage to come within that range, what their business team or management wants to do. I just want to touch upon the schedule-driven strategy, why I'm talking about it, because most of the Indian projects are very aggressive in schedule. They want everything faster. If 60-month projects, they want to get it done in 40 months. So I just want to caution on that one, what I see in the industry. So as my boss says that, speed kills. So when a schedule-driven projects, typically they can't meet that objective, as well as the cost also go overrun. Typically, that's what we see in the industry. Why? Why it's a schedule-driven projects? The problem with schedule-driven projects. Typically, the schedule-driven projects, we always have the problem of the management or the CEO will announce that projects to the market. Oh, I'm going to have these projects in, say, 40 months. So the project team has to work within that range of 40 months, because when the boss says to the market, 40 months, they haven't done enough work most of the time. Across the world, it's not just here, across the world, that's the case. So then the project team needs to work backwards, and the only place they can cut short of the time, they can't cut short the construction phase, because that takes its own time. So the only place they can cut short is the planning side. They cut short the planning, then they go to construction, then they have all the problems along the way. So I just want to say that, there are a lot of issues we have. Management wants speed, that's common across the world. Also, please take note that we have stretched resources across the world. There's a lot of problem in the Western world. There's a demographic cliff happening. So they are depending on countries like India to do most of the engineering and most of the work. So as you know that the GCCs in India are expanding rapidly. So India is supplying a lot of people across the world. So that will impact your projects as well. Don't expect that you get the A teams. Gaps in the project planning, that is significant in Indian projects, something we can do internally. We can be better in that one. So essentially, doing these basic things, it's not something rocket science. These are the basic things we do in our projects, actually drive our projects in a better way. And we can have a more predictable projects and improve our competitiveness as well. Thank you.
Thank you, Mr. Manoj Prabhakar. The importance of front-end loading or the project planning you emphasized, and that really becomes very important because schedule can make or break a project. So thank you for sticking to time also. Our second presentation is by Mr. Shekhar Gunavel, BPCL. He will be talking about transforming refinery planning. BPCL's journey from basic crude assay management to advanced operational optimization using Aviva Spiral. So Shekhar, please.
Good evening, everyone. Good evening, Prasad sir, Bandai sir, fellow speakers. I would like to thank BPCL and CST for giving me opportunity for speaking here in front of all the learned people. So today I am going to share BPCL's journey, how we have transformed our current usage of Aviva Spiral from basic crude asset management tool to the advanced optimization tool. For every LP planner or user, the two most important and challenging tasks are how he can simulate the whole refinery, complex refinery processes in simple mathematical equations, which can provide him more accurate and fast results. Second task is how we can minimize the plan versus actual gap. Because this plan versus actual gap or deviation means we are losing margin. So as Manoj talked about how plan versus actual as we are bleeding money in project stage. So here I'll be discussing about how plan versus actual gap we are bleeding money in case of our normal refinery operations. So these are the 5 challenges, operation challenges a LP planner faces, how he can model all these 5 challenges in his day-to-day planning. One is slow processing. Every refinery processes slope, but during his LP run, he is not able to include those conditions in his plan. Second is intermediate product. So all the refiners want to sweat their secondary units. So for that, sometimes they purchase intermediates like high sulfur diesel, high sulfur VGO and other intermediates so that their downstream streams units are sweating. But it is very difficult to calculate the break-even cost of that. So that also we'll see how we have modeled that. Second is special operating conditions. So that special operating condition is from one of our refineries where we take periodic shutdown of our vacuum column. At that time, our crude unit will be running at reduced throughput, and vacuum atmospheric column will be bottom will be routed to my crude tanks. That will be reprocessed later. Second is crude evaluation complexity. So here we'll see how with a single click we'll see directionally which are the crudes will show more value to our refinery. Third is cut point constraints. Cut point constraints, currently we use static cut points in our basic asset management. So sometime in actual operation we'll change the cut point of cut points of crude unit, but this how it impacts our profitability, that also we'll see. So with this aim, we started our journey with the aim of reducing the gap between plan versus actual. So whatever we plan, we'll get actual out of it. Second is how we can model the complex scenarios like slow processing, how we can get the more accurate value of break-even values of our intermediates. When going to market, we should purchase intermediates at more accurate price. Second is how fast we can take decisions, and while doing my crude evaluation, I should not miss any crude. Third is this. Fourth, how all these decisions I can take with the data available with me. So we'll start with slope tank modeling. So all the refineries reprocess slope. So based on the 3 conditions, they will limit the slope processing. One is physical constraint in the crude unit. Third is metals and sludge. So metal and sludge, we cannot model it. But the physical constraint we'll model it, we'll utilize assay synthesis capability of spiral, and we'll take 2 to 3 properties we'll test in our lab and generate a pseudo assay of our slope tanks, and that will integrate with our PIMS output, and then we'll get whatever we plan, we'll get in actual also. So this is how we'll simulate my actual planning with my LP tool also. Third is ISDs. So few refineries have capacity available in downstream, so they want to purchase high sulfur diesel, high sulfur VGO, all the ISDs they want to purchase. But challenge is how to calculate the break-even cost of that. Another thing, there is infrastructure limitation, how they can take those intermediates inside the refinery. So only option left is they can take this along with the crude, and that will be processed in the crude unit and then subsequent to the secondary units. So how to calculate the break-even cost of that? So here we missed 3 major things. One thing, is when we are taking all these things in crude tanks and processing atmospheric column. So there will be physical constraint in the crude column that will not be available with us when we are doing with basic crude management tool. Second is there will be always having inefficiencies in my tray columns. So that will not be taken care in my normal process. And third one is how both we can take and calculate the more accurate utility consumption of crude unit also. So all these things, so what we'll do, we'll use the product synthesis tool of Aviva Spiral. In that we'll generate the pseudo crude assay of that particular ISD and take that and crude unit, and there we'll able to calculate more accurate break-even values. This is one issue we face in our refinery. So in that, during plant shutdown, we'll take a shutdown of our vacuum column and we'll run our crude unit at reduced throughput and route our RCO to crude tanks that will be processed subsequently in the coming month, and vacuum column is available. But how to model that in our normal operations and how we can get this output without doing any manual intervention outside the LP tool. We have taken a single crude and then distributed that crude in two parts using product synthesis and stream synthesis feature of Aviva. In that, crude is broken in two parts. One is from IBP to the atmospheric column bottom, and then second is from vacuum diesel to the VR. And there's two crudes are processed in the refinery. With that, we are able to get more accurate results, and our pan versus actual gap is also minimized. Here the this freeze point. So this is one major issue faced in our refinery. So different crudes, kerosene has different freeze point. So what issue we are facing, that whenever we are processing certain crudes, we are forced to reduce the kero cut point. So whatever kero was dropped, it was getting dropped in diesel. So our diesel treaters were already saturated and we were forced to reduce the crude charge. So in this scenario, instead of using the static cut points, we use the property target feature of Spiral and made dynamic cut points. In that, my cut point will depend on my freeze point. With this, it helped me in getting better crude evaluation, and I'm more close to my actuals. Fifth one is straight run product value. So every refinery have different process to evaluate crude. In BPCL, every week we evaluate 300 to 350 crudes. So after 350 crudes also, there are chances that we'll miss some crudes. So how to ensure that all the crudes are evaluated? We are not missing any single crude. So straight run product value will not give the exact output, which crude we should buy, but this will give direction that this crude should be evaluated. So what we'll do, we'll take the products of the crude unit and see based on refinery configuration. Suppose my high sulfur diesel is there, if I'm processing, which product it will make. If high sulfur VGO is there, how much product it will make. Based on that, we'll arrive at the product values, and that product values along with the constraints like how much naphtha a refinery can process, how much sulfur and nitrogen refinery can process, all these constraint and prices will put in our spiral. And with a single click, we'll see the crude values of 5,000 crudes. In that, we can filter out, okay, these are the crudes I should target. In my current evaluation, these crudes are not missing. So we have three use cases in that. One is vacuum residue reprocessing. So one of the scenario was we were facing furnace oil containment because of reasons of bitumen evacuation issue and delay in tanker arrivals. In that, we are forced to route our vacuum residue to our crude tanks, which were reprocessed later. So same thing with the help of product synthesis. We have taken samples and we divided which VR we have routed to the crude tanks. We generated a assay out of it. And with that, we are able to predict how much FO I'll be generating when I process crude from those tanks. So this helped me in avoiding distress export of FO. Third is, already discussed that we'll take shutdown of vacuum column and crude units will be running at reduced throughput. and RCO will be routed to crude tanks, will be reprocessed later. So this process also we have used, and we are able to match the gap between plan versus actual. And we are again able to predict our FO generation. This is how high sulfur diesel import analysis we have done. So in our Mumbai refinery, we have a spare capacity available in high sulfur diesel units. So we evaluated how we can calculate the break-even cost of high sulfur diesel if you want to buy from outside. So, but there is no infrastructure available. Only option is I can take along with the crude, then store in the crude tanks, then process in atmospheric column, then subsequent to secondary units. If I calculate the break-even cost with normal method, I will not get the operating cost of crude unit and other inefficiencies of crude column, because I will take diesel because of overlapping of the streams in my crude column inefficiencies in the tray. I will not get the whole diesel. Something will go in naphtha, something will go in VGO also. So all these things we modeled with the help of product synthesis, and we were able to calculate the more accurate break-even cost. With this, we leverage the existing tool capability without any cash outflow. We use the existing tool capability, and we match the plan versus actual gap. And so this is our way forward. So we want to use all these capabilities in our future planning and operations, and we will see how we can use this for evaluating our future projects and how we can implement this for digital twin also. Thank you.
Thank you, Shekhar. What a fine example of leveraging existing software tools which are available for modeling very complex real-time scenarios which we come across, and also for procurement efficiency by analyzing number of crudes very fast. So we are continuously challenged by these kind of scenarios, and it's a great example of how these things have been used. So thanks for that presentation. Our next speaker is Mr. Varun Nidhi. He is a director, AI and COO of Kinben Innovation Private Limited. And Varun is going to talk about LLM-powered crude oil blend yield predictions. So over to you, Varun.
First of all, I'd like to thank everyone for joining in after lunch. You won't sleep in this presentation because we'll be talking about something very, very interesting. So my fellow presenter from BPCL talked about a lot of which can be done using complex methodologies. You rather opened a door for my presentation. You talked about what if we include AI in this kind of prediction. That's what we are bringing on the table. So we can even collaborate and think about how fast we can do these kind of decisions. That used to take maybe 30 days. What about we can do in 30 seconds? What used to take maybe 3 or 4 hours to do for a decision-making parameter to come on board, and we can do it in 5 lakhs. So that is the power of large language models and AI I'll be talking about today. So we are well aware of market volatility these days. There are sanctions, you have spot cargoes that you can buy, you can save money in that. But that decision is very complex. Like we had on previous presentation as well, how complex that is. But what happens is you have to balance the cost with the risk that you can take with your refineries. That's where the power of AI can actually help you decide, once you train it effectively, that this is what we are going to use in our refinery, this is what our refinery is, and these are the crude blends which are available in the market. So we are well aware of quick commerce these days. You order something from a Blinkit, it arrives in 10 minutes at your home. Maybe we want something like that with our crude assistance as well. It has access to all of your data from your refinery. It has access to all of the data from the crude which is there. So what we are saying is, if we want to decide in a couple of minutes whether we can process that particular crude blend, what we have in storage, what kind of profit we'll have, That's the cost of delay that we want to counter. So that's where crude trade AI assistant comes into the picture. We call it trade AI because market actually govern the rate, and it's kind of a co-pilot. So we are aware of something like a Chat GPT or a Gemini or Microsoft Copilot for that. So that remains on our laptop. We can call it anywhere to write social media post or an email or practically everything. But a chatbot is not the only function of AI. What AI is very good at is it's able to understand the mathematics behind what's happening inside a refinery, what a crude assay is, how it needs to be processed. So it's practically an expert which knows the mathematics and physics behind the things. How we process it and use that AI, it's upon us. So we see it a very big approach in which we can utilize this function. The best part is you don't need to put your data on the internet. What if we bring that AI to your data centers, your servers, your data remains with you. That's your critical proprietary data sets. You don't want it to be exposed to. And that's why oil and gas companies have been hard step of not using something like a Chat GPT for their own proprietary data sets. It's connected to the internet. This is what we want to solve. What if refinery engineers, traders, and planners could think together instantly? When building a system like this, a large language model which understands the physics, mathematics, and even the costing economics of these crudes which are processed in our refineries. So this assistant thinks about all of these people, how to enable these people to decide what to do and what not to do. And whatever they are doing, what kind of risk it pertains. How we are doing that. So when we talk about a large language model, specifically speaking about what we are doing right now for a crude AI system, starts by smart shortlisting. So let's say you are processed 350 crudes. It would know what kind of crude can be processed by your refinery because it has that information with it. Then it will start to explore what the processing functions will do, what kind of outputs you will get, what kind of yields you will get. So how you will get that? You have a lot of refinery data with you, which is a historical data. It will be trained on that, and it will run how the refinery operates. We are talking about functions that used to take years to develop. Now we are talking about deployment times that can be done within months, sometimes even couple of weeks. The third aspect is, of course, we have to tune the model to understand the mathematics, like Chevron method, Revitast equation. A lot of non-linear equations are used for precision tuning. So just like GPT, when you use a GPT and ask it to solve a mathematical equation, it actually does the mathematics for you. So why not bring that into the table and ask AI model to do that fine tuning, that mathematical calculations for us? And the fourth step is the most, it does a confidence check on the historical data and give you a report, a final decision making report in which you can decide. All of this happens in 30 seconds, by the way. So we call it blending GPS. Why GPS? There are thousands of ways to blend a crude with your current crudes which are available with you. So it moves from that noise to a final decision making parameter that you can utilize. On the screen, you can see we give some information and spews out a complete cut breakdown of that particular crude, which could be a synthetic blend, which you have never seen before. And it all happens within a minute. But we want it to be without risk. So no risk buying should be there. There are different parameters in which the risk has to be understood. Some parameters are there on the screen. The software actually analyzes more than that. So it's kind of a risk radar for refineries and plants which are actually processing a lot of these crude oils. Another functionality that we have been using, like I mentioned, Blinkit for 10 minutes delivery. Similarly, what if you get a crude oil in which the entire assay data is not available? So just like Truecaller, we get the report that if that's a spam, so spam means a crude oil you cannot process in your refinery, that will be loss function. So this true caller ID kind of works in a complex way in which it creates a synthetic blend for you. So for example, you provide these 5 properties, it will know these 5 properties from which region that particular crude is. And it will create a synthetic blend for you, which will have unknown crude properties as well. Like we have not mentioned nickel, vanadium, any other thing apart from these 5 properties. But the accuracy that we are getting right now is beyond 97% across these properties. How it's doing that? A complex algorithms which are powered using large language models. So we are calling it Petro GPT for the ease of understanding. Petroleum industry and GPT just like ChatGPT. So this is the scenario. It's bound to solve faster decisions that can happen within 30 seconds. It's not supposed to replace simulation packages, rather augment them. You can even feed the data from all of your simulation packages that we have heard in the last presentation as well, and create multiple scenarios within a day, maybe 1,000 scenarios within a day, so that we are even proactively ready for the next stage when it comes. So why now? First point, we know volatile markets. That's okay. Sustainability. And so when we talk about the economy of our country, we are talking about how much we can save, how much more we can produce, and how fast we can take those decisions. In the first presentation, we talked about how the schedule delays actually cost us more than it actually does. Similarly, we are talking about that's where decision making using AI systems comes into the play. You had a previous image in which we are talking about blending GPS, lot of arrows going here and there. What we are talking about is merging those arrows in which the AI assistant does not decide for us, but guide us into a one confident decision in which we can rely on that particular AI. So this is how it happens. You just define the cuts. This can be automated as well on the refinery functionality, depending on what the data or what are the processing cuts of your refinery is. You define a blend which is already there, the crude oils which are already there. So for example, here in example, Alaska North Slope is 20% by volume, which is already available, because you're never gonna process a pure crude. It will be always be a mix of things. The last step, what you're seeing is a synthetic blend which has created. So we provided 5 properties to this synthetic blend, and we tested this data on ExxonMobil, Equinor, as well as BP crude assays with different accuracies. And when it was generating those aspects and these cut by cut breakdowns for us, we saw that we could consistently generate more than 95% accuracies for all yield predictions. Combined with this, the historical knowledge of any refinery, not only it can make your decisions much faster and accurate, but could bring you more reliance on AI, in which you can explore other areas of using AI, not just this single piece of thing. That is taking care of the refineries, the operational parameters, how it can integrate with your IoT systems, the sensors which are actually attached to it. So to gain more knowledge on this particular aspect, you can scan the left QR code. A simple change I wanted to bring to the industry. As Indians, we don't do many open source projects. So I'm sharing a couple of projects to show you the power of AI, how we can utilize that. So you can scan the right QR code to have some access to some open source projects. This will jot our mind to use large language models and AI systems and bring us back to the race where other countries are way ahead of us. So economy driven through AI is the future. We have seen this with US, China, practically every country. Currently, we are lagging behind, but I see an opportunity in which industry like ours, which is a core pillar of our industrial base as well as our economy, can change by using AI systems for all of our processes. Thank you very much.
So, thank you, Varun. The technology is really changing the way we are going to do business. We just saw that future of how the crude oil is going to be procured. And I'm very sure that our process engineers, schedulers, traders, research people will have a lot of questions on this, and you will have to answer a lot of questions after this. But it was a very nice, interesting presentation. So next we have Mr. Naresh Kotari. He is from HPCL Greens. He is a senior manager there. And he will be presenting about rational catalyst design via DFT for JP10. So, yeah, Naresh, you're already there.
Good afternoon to all of you. So my previous speakers talked about AAR simulations in like some aspects. So what I'm going to cover to you about based on first principles. Basically, I'm from HPCL Green R&D Center. I'm going to do a case study. How did we use the kind of AB initio calculations based on physics first principles, and how did we fast track one of the important fuel that is required for our defense applications. So this is the content of my presentation. Before I jump into actual what we have done, I would like to briefly introduce to you what these kind of fuels are. This is not what we get from our refineries. And then basically, how did we use our simulations, our latest, whatever you call molecular modeling data to develop one of the most important fuel that is required for our defense applications. So if you look at this slide, basically I have just listed out some of the so-called the synthetic fuels. Basically, if you see this RJ1 or RJ4, they're having density in terms of the 0.92 or 0.91, or even some of them having excess of 1. So when we compare with this, our standard ATF, which we have about 0.84, so that brings an additional density. So what does it mean? So it basically have more energy density or more payload capacity per liter basis. So this becomes an important factor, especially wherever kind of, there is a kind of volume limited issue. So for example, if you look at our aircraft from Indian Air Force or UAVs or maybe missiles, their tanks are kind of very small. So if you, typically they use the ATF. If you can replace the ATF with these high synthetic fuels, I mean high density fuels, so we have the more energy density per liter basis, you can enhance the flight range, or you can even increase the payload. So that's the novelty that these fuels coming to the table. So if you see what are the fuels that are typically known, some of them are shown in the right hand side of the picture. If you see, all of them are kind of very naphthalene kind of structures, but instead of naphthalene, these are all like very highly strained naphthenes. Instead of naphthalene that what we have in a refinery, these are all called bicyclic systems, highly strained systems. So the strain in a molecule is actually works in favor of us. Basically, when we release the strain, what happens is we get more energy density, and because of the strain, they pack well, and this is what actually the reason for their high density. So how did we achieve this? Basically, there are many ways we can make these compounds. One is coming from the take one of our refinery building block and make them. For example, all these things are use the pyrolysis oil intermediates and then basically make this kind of products. Or alternately, we can also synthesize starting from a biosource. But again, this is also kind of a naphthalene structure. But and the third option is, if it is not possible to synthesize, let's say the synthetic fuels, the alternate way of increasing density is using metals. If you see this volume energy density versus gravimetric density, these metals are having very high energy density. So if you can blend these metals in certain proportions to the hydrocarbons, because of the density is an additive property, in overall we can increase the density of the fuel. So that brings me to the main topic that what I'm going to talk about today. So JP10 is basically a fuel used in missiles and defense applications. If you see right hand side, this is a single molecule fuel. So basically about aceton hydrocarbon, which is in the range of ATF if you see the boiling point. And this has got a pour point of -79 and a very good flash point to operate it. And compared to this jet fuels, the density is about 13 to 15% higher. That is what makes it more attractive. But why, if it is so much important, why we were not practicing in India today? The problem is currently there is no manufacturer in India in bulk scale. Though some R&D is going on in some academic institutes, but still there is no commercial production available. So this is very expensive, about $10 per kg, and that makes its a low availability both in civil as well as defense applications. As far as the defense is concerned, cost is one aspect. Another aspect is the self-reliance. So if you see how this molecule is synthesized, this molecule is actually coming from our refinery. So if you see, for example, if you take our pyrolysis oil and there is a molecule called DCPD is there, that's the structure of the first equation. This is available is in a reasonably good quantity. If you can extract that and then subject to two steps, one is hydrogenation, another is isomerization, we get the actual JP10 fuel. So what we have done, this is available in India, otherwise is also freely available to import from the various other countries as well. So once you take this DCPD, which is actually formed from the cyclopentadiene in a Diels-Alder reaction, which forms an endoisomer. Endo means basically pointing towards down. So once we hydrogenate it, basically if you double bond these two double bonds, you get the endo form of it. But the challenge is, this is very complex process because this reaction is highly exothermic in nature, and these molecules break up the strain, they kind of open immediately if they see a sufficiently high energy density. So we have done a lot of studies and tried to optimize it, and there are various factors that has taken into the development of hydrogenation catalyst. It's kind of hydrogen absorption, splitting, the compound adsorption. Once we have considered all of them, and then we kind of did the in silico studies, and then the best one was taken into the laboratory practice. So this is the data, what we can see the right hand side. So with the developed catalyst at our R&D center, the conversion as well as the selectivity, this is a month's time. Basically even up to 6 months, we are able to maintain the very good conversion, and then basically also selectivity for the product that what we need. So this is the first step. The key of the synthesis of JP10 is the second step, which is an isomerization. If you see these properties, whatever it is listed here, this is an endo, which is a cetane hydrocarbon, cyclic hydrocarbon. This is also cetane hydrocarbon, which is an exo, and this is a basically kind of diamond-like structure called adamantane. And if you look at the freezing point or melting point, the first one is 79, -1, the second one is -79, and third one is 272. If you see the variation, there is a 400-degree variation. This is a kind of fascinating aspect of this chemistry. This brings an important challenge to during the manufacturing. What happens is, this is a kind of solid in nature. The moment it actually converts to, it becomes a liquid. If you don't stop here, it goes all the way there. The problem with this molecule, this molecule is exactly behave like a camphor. So if you leave it in a room, it goes and it kind of sublimes. So this creates a lot of problems, not only in the manufacturing, but also in the actual field applications. So our role is to minimize this and maximize this while achieving the conversion from endo to exo. If you look at the remarks, this is the intermediate stable compound, this is the most stable compound. So if you leave the system to evolve, obviously when I start from here, it kind of end up here. So it's very difficult to stop at this stage. That is where the tuning the required catalyst comes into picture. So obviously when we such kind of systems are there, we take the help of the simulations. So what we have done, so this is basically what we have done. We have taken some of the available knowledge at our R&D center for various other projects where we have tuned the Lewis acidity. Lewis acidity is a kind of concept where it is used extensively even in our cracking plants as well. So here we have taken we have extended the knowledge to what we call as an ionic pairs. So we have taken two kinds of ionic pairs to convert from here to here, but then to stop going to this compound. So we studied various parameters using solvent effect, and then how we can tune the combination of this one. I'm not going to go into details of these values, but what it shows is you can get these values from the simulations. Basically, we don't have to do any experiments. So what we can see here is the LUMO value. LUMO is nothing but how Lewis acid can tune based on the values. The more negative it is, the stronger the Lewis acid it is. So basically, you can tune it. There is values ranging from plus value to minus. So you can tune, and basically based on these values, and then try to optimize to achieve the good conversion. Another aspect of looking at this data is kind of where the Lewis acidity resides. This is basically obtained from the DFT calculations, what we call as a HOMO and LUMO orbitals. This is actually what determines the chemistry of the catalyst. Now, if you see, for example, the catalyst which is in a solvent 1, if you look at the HOMO, which is represented in blue and red color, which is on this molecule, the moment I change the solvent, it becomes this moiety. Basically, the pink one is an orange moiety. So that means the HOMO, which is not at all in aluminium, has become an aluminium just by changing the solvent. So that's the important information. So what it says is, if it is on this pink atom, you can control the acidity. If it is not on pink atom, it's very difficult to control the acidity. And same thing goes on the other catalyst as well. So by comparing this, by tuning the solvent as well as catalyst, we were able to kind of achieve the required selectivity. So this is a summary of the final synthesis. If you see the endo, which has kind of become JP10, and we compared the commercial fuel just in comparison with how our catalyst has got worked. So this shows the purity. The commercial one has almost like 96.3, the spec is 96.2. So they basically exactly maintain it. Whereas our product, when we got this through the simulated study, simulated aided synthesis, we actually got up to 99.5. That shows how actually you can kind of apply this knowledge coming from the computers to the actual field. And even if you look at the impurities also, so this is what I told, factor in this fuel, whereas the commercial fuel up to 1%, whereas we don't have anything. We have only little bit about endo, which is unconverted, but we have an exclusively the formation of the required fuel. So once we have done this, in fact, we have synthesized all the way from 50 grams to 300 kg. So we have done the engine testing at the DRDL lab in using a static aircraft engine. So what we can see here, basically the fuel efficiency, which was almost achieved to the almost whatever we can achieve from the theoretical calculations. So that brings me to the conclusion. So we have taken in silico studies and then applied them in both catalyst for isomerization as well as hydrogenation. So now we have done up to 300 kg, which is a relatively good scale for this kind of fuels. And then basically engine test showed the efficiency what it's supposed to have. Thank you very much for your attention.
So thank you, Naresh. You took little more time, but your topic also was quite complex. So congratulations on coming out with a very innovative catalyst, cost-effective, indigenous, and for very critical application. So moving on to the next presentation, we have Mr. Dulal Ghosh from Baker Hughes. And he'll be talking about heavy-duty gas turbines burning up to 100% hydrogen, an effort towards decarbonization in oil and gas. So, Dulal.
Good afternoon all, and thanks to CHT and Baker Hughes for giving me this opportunity to be here and present our work. So today's topic is the gas turbines that are powered with hydrogen. Why hydrogen? which is the benefit of, let's say, burning with hydrogen? We know that hydrogen is a fuel that produces zero carbon, or let's say it's a carbon neutral fuel. We burn hydrogen, we don't get any emissions related to the carbons. And that is what the main feature of hydrogen as a fuel. So I'll go to the slide. So it's not just the turbines that Baker Hughes is able to produce that burns hydrogen. We have a long history starting from back then in 1905, 1915, starting with reciprocating compressors. There also it's able to utilize hydrogen for its compression cycle. And we have experienced more than thousands of reciprocating compressors across the world that are powered with, that are running with hydrogen-rich gases. When we say hydrogen-rich, it could be pure hydrogen, or it's a mixture of hydrogen with other fuels like natural gas. So for the gas turbines, yes, we do have a history starting from year 2009. The first power plant in Italy, it's called Fusina power plant, that was able to burn pure hydrogen, or up to 100% hydrogen. Then, which is the source of hydrogen typically? Where do we get the hydrogen? We talk about hydrogen burning, but where do we get the hydrogen from? Conventionally, we know that it can be the source can be a blue hydrogen or a green hydrogen. There are some let's say differentiation between the sources where it is being produced. For example, I think in green hydrogen it is mostly from the electrolysis of water, while with blue hydrogen it is from natural gas. So depending on the sources of hydrogen, anyway, we know that there is a source, and we can try to utilize this hydrogen, which is in different frames, in different gas turbines. For Baker Hughes, we offer this varieties of turbines. You can see on the left hand side, it shows a chart where there are different turbines starting from frame 9, frame 7, even LM9000, LM6000, and some PGT machines offered by Baker Hughes. In the image that shows in this middle of this slide is the Fusina power plant I just talked about in Italy, which is a 12 megawatt plant, and it's able to run up to 100% hydrogen. The latest technology from Baker Hughes, or let's say the latest offerings from Baker Hughes, is on the right hand side. We can see it shows the greenfield application for Nova LT16. It's an indigenously developed gas turbine operating with pure hydrogen, up to 100% hydrogen by volume. Of course, it can mix with some other fuels depending on the requirement of the plant, for example, natural gas and also some heavy hydrocarbons, but mainly it is capable of burning pure hydrogen. Not only the new units like greenfield application, we do have offerings for brownfield applications with the refineries which are already existing, or the petrochemical industry which are already existing, to upgrade their gas turbines to burn with hydrogen, pure hydrogen, such as the frame 5. We have frame 5 units in India, for example, frame 5.1, the frame 5 with a single shaft, or a frame 5 with double shaft. We are typically called as frame 5 to C or D. Okay. So today we mostly focus on our product that is explicit for Baker Hughes. That's Nova LT16 H2. It's a trademark of Baker Hughes. Where all we can apply these turbines, we can see a list of applications starting from blue hydrogen or ammonia production to pipelines to recently catching up the data centers which need a huge amount of power, and we are offering these turbines to power the data centers across the globe, including mostly in United States. The refineries and of course some offshore and marine applications can also use novelty 16. What are the features of this novelty 16 apart from the fact that we know it's able to burn hydrogen? It's a 17 megawatt, close to 16, 17 megawatt of power in the, depending on whether it's a mechanical drive or it's a power gen application. The efficiency is compared to conventional gas turbines, it's quite high. We see it's close to 37.7% percentage efficiency. It can be used in combined cycle. It can also be used for cogeneration applications. It has the capability also to burn fuel and produce low NOx. Typically, these are called DLN combustion system, dry low NOx combustion system, because in the DLN combustion system we get a low emissions down to 15 ppm. For hydrogen, yes, the NOx emissions is a concern, because as we know, it has, though it has zero carbon production, but it will induce, or let's say it will produce a lot of NOx, which are again a environmental concern. So we do have, currently we have selective catalytic reactors to handle these kind of NOx emissions, or we can also, we are in a phase of developing the dry low NOx system for hydrogen application. And by the year end of year 2026, these technologies should be available to burn hydrogen and not producing carbon and producing very limited amount of NOx. Quick startup, like applications such as data centers need a very fast startup, and they can't wait for hours for the GT to reach the base load. This novelty 16, again, it able to reach the base load, or let's say the full load, in matter of minutes. Let's say the maximum time to reach the base load could be around 15 minutes, and there are some machines on some, let's say some novelty 16 which can even reach base load at a shorter duration than 15 minutes. The fuel flexibility, as I spoke before, it's not only hydrogen. These turbines will be able to burn depending on the availability of the fuel. At the refinery, it can switch it's the fuel on the fly. The machine is running and it can switch to, let's say, natural gas. If there is some cut down in the hydrogen line, then that can immediately switch to natural gas, or even a liquid fuel. It is able to operate with liquid fuel as well. Of course, in liquid fuel operation, we need to we will not guarantee the emissions, because typically they run in the diffusive mode. Startup capability. These hydrogen is typically known for its flammability, for its risks of startup because of this flammability. So it can be, it has to be studied thoroughly to make the system able to handle this kind of flammable gases. This machine, or let's say this novelty 16, has been fully proven to start up with 100% hydrogen without any risk of explosion, let's say, so in the typically at the stack. Okay. It is not just on the paper. We have the machines tested. The it's called the full annual rig test, or the combustion test, the combustion system tested in Siena, Italy, back then in 2022, where it was fully instrumented, and tons of hydrogen have been burnt in the same combustor, running up to 45 plus running hours without having any, let's say, flame instability or emissions issue. Then we also tested the full engine, including not only the combustion system, but also the compressors, the turbines in the full, it's called the FETT, full engine test. that happens in Florence, Italy, sorry, a few years back. And it was successful. It was a test that gave confidence to the customers. In fact, after this test, we have delivered a few machines for a company in Canada that is able to burn 100% hydrogen. Right now, the plant is in operation as well. As we speak that hydrogen is a flammable fuel, we need to also take care not only of the combustion system, but also the packages and auxiliaries, the downstream components of the gas turbine, the ventilation system, the purging requirement, the fire and gas system, the electrical devices, the control system, all has to be studied for a hydrogen application, different than a natural gas application of gas turbine. And even then, these studies has been performed and has been implemented in the real projects that we already have delivered, like I said, few units to a customer in Canada. Okay. So to wrap up on the novelty 16, we know that hydrogen we know how to burn hydrogen, or let's say we have the available technology to burn it. We are working with world leaders to produce this hydrogen at a lower cost and make it more friendly for the customers, even in terms of cost. And at the end, to achieve a zero carbon mission for the different customers, whether it is refining or petrochemicals. We do have a short video. I don't know if it is we can play, but I will quickly go through the. Okay, we started the discussion with Nova LT16, and we do have another machine which is a heavy-duty gas turbine, which is able to produce up to 26.9 megawatt electricals. That's called Frame 5, and we have the solution operating up to 88% as a volume of hydrogen. And we in fact have a customer interest coming from Italy again to upgrade their existing gas turbine to run 100% hydrogen for Frame 5. These are the development phases. Back then in 1980, we have the technology. We have been upgrading it for different applications and to burn more and more hydrogen. Now we are at a level of 88% as a volume of hydrogen. Similar challenges as we have seen for the Novelty 16 are applicable here, and also the different applications we see for these kind of frames. Okay. At the end, we at Baker Hughes can help to achieve your decarbonization mission in the refineries or petrochemical industry. And please get in touch with us if you are interested for decarbonization of your plant. Thank you.
Thank you, Zilal. The way we anticipate hydrogen prices to drop down, I'm sure there's going to be a lot of requirement for these kind of equipment. So moving on to the last paper of this session, I call upon Mr. Manish Saraswat from Leondel, Basel. He'll be delivering his paper on advancement in polyolefinic catalyst and process innovation.
I think you have to go back to the slide. Start from the first one. Yeah, that's fine. So good afternoon, and my apology because I have traveled overseas. I want to talk to you, so that's why I would like to stay here. So I won't stay behind this board. So here, we are talking about our company. So I think there is one slide back. Yeah, this slide is very important. My legal department loves this slide. That before you make any financial decision based on my slides, please read it carefully. So this slide is the most important slide in my presentation. So time is short, so just a brief of the organization. So other than the polymer business, so before we talk or go in my presentation, so it is little bit different than this audience because all the day we were hearing about the refinery, But this, I'm talking about the further downstream, that is the polyolefin business. So the refineries are seeing now these plants coming next to their plants. So either production of polypropylene or production of polyethylene. This is our DNA. So we start our business from the chemistry of invention of polypropylene molecule. And still in our laboratory, we have that reactor where first time industrial polypropylene molecule was made. So it is still there. And that has happened somewhere in 1954. And since then, we keep on developing new technologies. So after that, in 1955, we developed a hostylene technology for the production of SDP. And then simultaneously, you can see in this slide that we keep on continuously developing new technologies. So somewhere in 1982, we developed this technology, Spheripol, for the polypropylene. And India, most of these plants are based on this Spheripol. Not only in India, they worldwide. More than 110 lines are out of Spheripol worldwide. And this is the technology which is widely used for the production of polypropylene. Yesterday, I was in the diaspora meeting with the Honorable Minister, and I proposed that what I see that in India, we are having a lot of PP production, but most of that is commodity production because we are not moving for the advanced technologies. So after this 1982, we developed a further technology that is catalloy technology, and that was for the production of advanced polypropylene that is currently being 100% imported in India. And after that, we further in 2002 developed another latest technology for the polypropylene, and that was for spherizone. So as on date, the latest technology for the production of polypropylene is spherizone, and for polyethylene, it is hyperzone. And we are running those plants continuously in our plants, and we are licensing also. The beauty is, as a technology supplier, we are not only producing the catalyst, we are also inventing these process technologies. We are also providing the post-licensing support, and we are running these plants. So the beauty is that we know actually what is happening at our customer end. And that's how the way we are developing this, we understand this, we also understand that where shoe is pinching in the customer end. So this is the beauty. And this is a unique combination, and you will not find with any other company. And this is just a brief introduction that I don't want to, you can read, you will be getting these slides. So we feel very humble to share these numbers that in global polyolefin technology, we are the world leader. In the global polypropylene licensing, we are the world leader. In polypropylene catalyst, again, we are the world leader. We are very humble to share that. But there is a lot of hard work behind this, lot of hard work, generations. And this is what this slide will give you an idea that how we develop these advanced products, how we bring new catalyst so that the industry can produce better product to help the society. So this is the phthalate catalyst which was being used since ages. And I think now it's a time to rest. Because phthalate has been categorized as reproduction mutagenic, and then it is not helping with the health of the people who come in contact with that. So now we are moving, and now in Europe actually we have already moved from phthalate catalyst PP production to 100% non-phthalate based PP production. And there are certain advantages also. So if we try to see that spunbond grade, which is produced, so during COVID time, everyone was using those masks. So the best type of such grade can be produced by using a non-phthalate based polypropylene. And this is, say, diether catalyst, which is used best for that. And for the transparency, for the reactor grade high MFR product. So these are the advantages of using these advanced non-phthalate based catalysts. So these equipment we are using, everyone is using in the house daily basis. But there are certain type of a polymer used which can be produced only by using this type of catalyst. And that is the edge. That is the edge. Here, the key message out of the catalyst development is that we are launching for the Indian market this metosine catalyst. And the beauty is that in the polymer reaction is taking place everywhere. So we cannot control exactly like a inorganic chemistry reaction. But so then we are getting molecules which are not desired also. But in the metosine catalyst, we get exactly what we need. And that is the beauty. And that's how we get a pure, clean product. So if we are talking about the clean product for the medical applications, for hygiene, for doctor's gown, for the surgery, then it has to come from the metosine-based catalyst, actually. Typical applications where is a kind of a boxing, and then if there is a warpage, which is one of the phenomena that the plastic components get deformed, then there is a problem. But in this metosine catalyst, that is the minimum. So, but I will not go in those details. And we have further catalysts for the polyethylene as well, and we are having a huge demand of these products, so that's why we keep on expanding. So we are expanding in US, in Germany, and we have a multi-location. So we can supply from any part of the world. So now I'm moving in, because time is short, so now I'm moving on the technology part of, so as we said, that we have for PP, Spheripol, and in Spheripol, we are offering this metosine PP catalyst option for the existing Spheripol and for the future new Spheripol lines. And this metosine catalyst can also be used in other third-party technologies. So it's not only that it can be used only in Spheripol, it can be used in the other technologies as well. So Spheripol, I have already talked a lot. The beauty is in the metosine catalyst, typically for the melt-blown type of a grade, we can produce a product up to 2,300 MFR reactor. So normally industry produce those kind of grade by using peroxide, but this residual of peroxide contaminate that polymer. And then we lose that cleanliness of the product. And by using this metosine catalyst, we can produce up to 2,300 MFR, and that performance on your customer's line is perfect. So then, if we are talking about the textile lines like Recofill 4, so then the performance of metosine-based polypropylene product is fantastic. This is the latest Spherizone PP technology. And in this technology, we have a combination. So we can, so currently, industry is using only, say, propylene and ethylene as a co-monomer. Here we can use multi-monomers. So, and then it gives the strength to this product that this product can replace the conventional polymers. So not only the conventional PP, but the conventional other polymers. So if we are comparing PP to PP, so if a product is produced by any other technology, if we are producing the similar product here, we can reduce the grammage of the polymer in the same application. And why are we able to do that? Because the technology, the process technology is building the strength in the product in a way that it doesn't need so much polymer amount to give the similar strength versus existing polymer. So polymer is the same, but the beauty of the process technology, that the kind of homogenization it brings. So like if you see there are two loops, so one reactor, one loop. So but in the one side of the in the riser side, one type of reaction is taking place, but on the downer side, another type of reaction is taking place. So for you, it will look like one reactor, but with switch of a button, this reactor gets divided into the two reactors, and that is the beauty. And that gives the process advantage to bring and to develop the product which performs better. And that's why we need a lower grammage of the product. And the next one is for LDPE. And LDPE, we have both type of technologies, the reactor one and the tubular technologies. The third one, and that is for hostylene. So hostylene, we have a few plants in India, but the beauty comes from the 3-reactor ACP technology. And what happens normally in, there are typical type of properties. So if we are increasing density, then some other property like ESCR is reducing. But in ACP technology, we can increase both the type of properties similarly together up, and that is the advantage. So like P100 pipe grade, which is used for the water transportation, can be produced by using this ACP technology. So with this, the key message is that we are continuously developing, bringing new technologies, new catalysts for polymerization, and I'm always available for your help. Thank you very much.
Thank you, Mr. Saraswat, for almost making it. Yeah. So now I'll hand over to Mr. Prasad Panika, Session Chair, to take it forward.
Thank you very much. Thank you to all the 6 presenters. Very good, extremely very good presentations. I need not summarize because he was summarizing immediately after that, and there is always a time constraint, but I suggest that we can have a couple of questions.
Yes, okay. Indeed, sir. We can accommodate a question or two. Yeah. So we've decided to do this organically. So any questions at all, show of hands and we'll pass the mic.
Yeah, please start. We have got somebody has to start.
Do you have a question, sir? Can you please pass a mic? Can you pass a mic, please? All right, let me come down to you.
Yes,
thank you. This question is to Baker Hughes, Mr. Ghosh, regarding the gas turbines using hydrogen as a fuel. What is the reason I should go for the gas turbine with a hydrogen, number 1? How does it look economics wise? 3, is it only from net zero decarbonization perspective or is there any other advantage?
Maybe I will speak. Hi, thanks for your question. Okay, so first of all, I'll try to answer your first one. Why hydrogen? As I started the presentation, that hydrogen is something that is producing power without any carbon. It's a carbon neutral fuel. we know that customers, when they produce carbons in their plants, they are penalized. It's called carbon taxation. But with hydrogen, there is no possibility of producing carbon, and that's why it's carbon neutral fuel. Sorry, and if I can ask you a second question.
How does it look in terms of cost economics?
Okay. I would say the performance and efficiency for a plant or gas turbine operating with hydrogen is at par with the natural gas operating gas turbine. The production of hydrogen, yes, that remains a challenge in some cases, depending on the locality of the plant. For example, if we have a blue hydrogen there, which is produced from natural gas or is a byproduct of some other refineries, we can utilize those hydrogen in our plant. In that cases, it makes more cost effective solution. Yes, but the challenge remains in the cost of production of hydrogen, and we are still working with the world leaders to bring down the cost drastically and make it a more financially appealing solution.
The third part of the question is the decarbonization effects. Any carbon credits can be claimed on account of this initiative?
Sorry?
Any carbon credits can be claimed as a part of this initiative?
I suppose so, because the production of carbon is almost zero, basically zero. So I think they should be getting some credits out of that. That's my understanding.
Thank you.
Thank you. Thank you, Mr. Ghosh. I think another question, perhaps. One more. Any questions at all? Show of hands, and we'll pass a mic. All right. Looks like.
Yeah, I have a question.
Yes, ma'am. Please introduce yourself. And
yeah, my question is to Mr. Prabhakar. So you have shown a schedule slip of 24% for the projects. Do you have any analysis for the reasons for that slip of schedule? Like you have said, workforce requirement, statutory approvals. I mean, what is the analysis for that slip?
Good question. The slip mentioned there is start of detail engineering to mechanical completion. So not from the part of planning side, like all these statutory permits and everything should have been collected beforehand. So typically it should be part of your front end or project definition before DFR. You should have collected all those things. So that's not included in that part. Thank you.
Thank you, Mr. Prakar. And that's all the time we have. Thank you so much. First of all, I think this panel deserves a big round of applause. A mega one at that, ladies and gentlemen. Thank you, gentlemen. With that, Mr. Prasad Panikar, may I please request you to kindly step forward and present a memento as a token of appreciation to our eminent speakers here on stage. Starting with Mr. Manoj Prabhakar. Thank you so much, sir, for your valuable contribution to this fantastic panel. Please keep the applause coming, ladies and gentlemen. We truly have to celebrate the excellence that we've just witnessed in this session. Thank you. Thank you, Mr. Shekhar Gunwal, for being a part of the panel and sharing your valuable insights. Please keep the applause coming. It's a gentle reminder for us to celebrate all the insights we received as well. And the only way to do it is by applauding and telling them that we are thankful. Varun Nidhi, thank you so much, sir, for being a part of the panel and sharing those great inputs with us. And thank you, Mr. Panikar. And now request Mr. Abhairaj Singh Bhandari to step forward and present a memento to our speaker, Mr. Naresh Kothari. Thank you, sir. I do not hear an applause at all. I'll give you some good news. We are going to take a break. High tea will be served shortly. That sparks some excitement, I see. Thank you so much. Mr. Bilal Ghosh, thank you for your phenomenal presentation. Thank you for sharing those valuable insights with us. Keep it coming, ladies and gentlemen. The only way to celebrate excellence is by applauding, is what I truly believe. Let's thank our speakers, last but not the least. Mr. Manish Saraswat, thank you so much for that powerful presentation. And I request Mr. R. Ramachandran, Executive Director Refinery, BPCL, to join us on stage and present a memento to our chairpersons for ably moderating the sessions. Thank you so much. And one to Mr. Abhay Raj Singh Mandari. Thank you so much, sir. And now, gentlemen, costs a moment to commemorate. May I please request you all to step forward? So please join them for a picture. What a fantastic session this has been, ladies and gentlemen. And if you are in agreement with me, the only way that you can tell me yes is by applauding. Thank you so much. A collective round of applause celebrating the brilliant minds here on stage. While we take a picture, of course, a memory for a lifetime. In the meantime, I'm going to tell you all that the next session will commence at 4:15 p.m. I repeat, 4:15 p.m. The next session will commence at 4:15 p.m., which means it's time for us to break for some tea, from refreshments. Please head to Hall 4, enjoy some refreshments, and come back so we can have the last session of ETM 2025 Day 2. This is Day 2 of Energy Technology Meet 2025. Thank you so much for being a part of all these sessions. Day 2 equally successful. We've got one more technical session which will commence at 4:15 p.m. I'll see you all soon. Thank you so much. Good evening. Welcome back, everybody. Please settle down. We are going to start the session in the next 1 minute's time. In the next 60 seconds, we will resume the session post-break, but for now, requesting everyone to settle down. Thank you. session area, requesting you all to join us. We are about to start the last technical session of the day. Requesting everyone to come join us back, please. And all the speakers are requested to step forward and occupy the front row. We are ready for the last session, the technical session 10. If you're looking to be a part of technical session 11, it's happening in the adjacent hall, ladies and gentlemen. But for now, in the next 30 seconds, we are going to start technical session number 10 right here in hall A. Welcome back, ladies and gentlemen. This is the Energy Technology Meet 2025, the 28th edition, and here we are on day 2. It's time for the last technical session for the day. And I take this opportunity to invite the speakers. But before that, the topic of discussion for this technical session is going to be sustainable aviation fuel. And I'd like to take this opportunity to welcome our chairpersons to the stage. Please put your hands together as I welcome Dr. R.K. Malhotra, President HAI, to the stage. Welcome, sir. His areas of interest: energy transition, biofuels, hydrogen and environment. His achievements, to name a few: awards and recognitions including Lifetime Achievement Awards from Society of Automotive Engineers, the National Lubricant Grease Institute, Society of Corrosion Engineers, and IIT BHU Alumni Award for Excellence in R&D, Rudolph N. Award from International Association of Hydrogen, Energy, etc. He's right here with us. Dr. R.K. Malhotra, a big round of applause as we welcome him. Joining him on stage is Mr. Siddharth Jain, VP Imarat. May I please request his presence on stage? His areas of interest, ladies and gentlemen: sustainable aviation fuel development and deployment, circular economy and waste-to-X solutions, project economics and low-carbon transition, global energy partnerships and policy advocacies. Achievements, to name a few: led feasibility studies for MSW to SAF projects, co-processing renewable feedstocks and power-to-liquid pilot initiatives, negotiated global SAF off-take agreements and strategic technology partnerships, championing Superstep Clean Technology project to recover premium base oils and ultra-low sulfur diesel from used motor oils without hazardous waste streams. And of course, the recipient of Falcon of the Year Award for the year 2013, 2016, and 2018 for business development and cost optimization. Let's welcome him with a round of applause, Mr. Siddharth Jain. Welcome, gentlemen. The discussion, as I said, is going to be on topic sustainable aviation fuels, and now take the opportunity to welcome our eminent speakers to the stage. Please put your hands together as I welcome Mr. Shaktivelan Durai from Honeywell UOP. Welcome, sir. We can do better with the applause, ladies and gentlemen. This is the last session, but let's keep the energy really high. Put your hands together for Mr. Craig Harris from Velocys Inc. Welcome, sir. Welcoming Mr. Raju Chopra and Manish Das from Topso. Welcome, gentlemen. Put your hands together for Mr. Soumitra Deshmukh from Sulzer Chemtech USA. Welcome, sir. Joining them on stage is Mr. Vishal Vashni from Lamas. A round of applause, please. Last but not the least, Dr. Palak Tugal from Visolis, joining the esteemed speakers on stage. Welcome, everybody. Although this is the last session of the day, I'm sure it's going to be extremely insightful and very informative. With that, gentlemen, sir, over to you.
So very good evening to all my panelists, my co-chair. This is, as she said, is the last session. I was wondering whether there will be sufficient audience, but I am glad that there are quite a few number of people, if not full house, because of the interest perhaps they have in this subject of sustainable aviation fuel. This is one thing which we know is required for decarbonizing the aviation sector. I was looking at the figure, how much is the CO2 contribution by the aviation sector globally. The total is about 2.5%, which I found is the global CO2 contribution from the aviation sector. And the International Civil Aviation authorities want that this should be brought down to nearly zero by 2050, which is a Herculean task, and perhaps the only route to decarbonize the aviation sector while using the existing type of aviation engines, unless we have some innovative developments around that. And I was wondering that hydrogen possibly could be used only for the auxiliary equipment and not, although hydrogen is being tried for drones, etc. Maybe in future we'll have, but right now the possibilities look like that we may have some of the auxiliary systems working on hydrogen for decarbonization. And the main fuel will be the sustainable aviation fuel, which may come from whether the hydro-processed Eastern Facies HEFA route, or maybe the Fischer-Tropsch route, or maybe the alcohol to jet, or finally the CO2 plus green hydrogen route could also be possible. So we have some eminent people from various organizations who are experts in their own fields, and they are going to share a lot of good, technologies which they are working on in these areas. As you know, it was shown also that in the inaugural session, or when the minister was here, that India has a target of going to using 1% of SAF by 2027, then 2% by 2028, and then 5% by 2030. So this will require a lot of efforts. The SAF demand in India is current about 9 million tons, and then, the aviation fuel. And if you have 1%, you can work out, and then maybe the total consumption of aviation fuel will go up. So more and more SAF will be required in terms of the percentage also. So with these few opening remarks, I request my co-chair to take forward the session and invite the respective speakers to share their technology thoughts. And I will maybe try to say a few words at the end of this session. Thank you. Over to you.
Thank you, Dr. Malhotra. Good evening, everybody, and welcome to today's session on the SAF. SAF is going to be the only source for decarbonization of aviation in mid to long term. So I look forward to welcoming you to this session and have your feedback and question and answer at the end of the session. So for the benefit of the speakers, we have 12 to 15 minutes for your presentation and Q&A at the end of the session. So thank you, everybody. So I would like to invite Mr. S. Durai from Honeywell UAP for presenting his paper on innovative paths for cleaner sky. For everybody, I just like to mention that Honeywell has been the pioneer on SAF with the first commercial SAF plant from World Fuels in USA. So welcome, Mr. Durai.
Thank you very much, sir. Good afternoon, ladies and gentlemen. Before I start with the presentation, I would like to thank CHT and BPCL for providing us this opportunity to represent Honeywell UOP's SAF portfolio of solutions. Okay. Before I get into the actual presentation, this is just a cautionary words from our lawyers that there could be a few forward-looking statements in my presentation. Before you make any investment decisions or any commercial decisions per se, please do your own due diligence and feel free to contact UOP, Honeywell UOP for any further guidance. Okay. My broad agenda for today's discussion, I would like to start with Honeywell UOP's portfolio of offering on the SAF space, particularly on the renewable fuels. and we'll go for a deeper dive into Fischer-Tropsch pathway for SAF production. And a very high-level overview on what different parameters one would look at before choosing a particular pathway for SAF production. And I will also talk about the grand collaboration of two industry leaders, which is going to ultimately benefit the end users, the customers here. So before we start into the SAF technology part, let's have a quick walkthrough on why this particular subject is of so importance now. As both our chairs, the chair and the co-chair, talked about it, this is kind of we would say more of a significant topic for today, just because if you look at this from a global perspective, what are the things which is driving the SAF market in itself, right? On the shorter term, say for example, till 2030, we believe the government incentives and mandates pretty much, I would say, a Western phenomena based on US, Europe, and UK. So these government incentives and mandates is going to drive the market. And on top of it, corporate commitments towards GHG reduction. So this is the other big parameter which is influencing this market on SAF. However, this is for short term. If you were to look at it on a longer term perspective, and that is where I wanted you to I wanted you to focus on the chart that is on the right side, right? So this is kind of what UOP per se projects as a global SAF demand. What we see today in 2025 as a very small market is expected to grow as high as 35,000 kilo barrels a day. Okay, so this is a kind of a market that we are talking about. In terms of metric tons, so this is about 150,000 kilo metric tons. So there is a huge market which is developing, but we wanted to encash this particular market, right? And the other near-term challenge that we are seeing is, today whenever we talk about SAF, it is pretty much limited to FOGs, right? Through the HEFA pathway. And at max, it goes to the next level of ethanol to convert it into jet. But are these the sustainable feedstocks that is going us to take all the way, say 2030 and beyond? Probably not. We'll be either limited on the feed source, or the regulations would limit us from using these feedstocks for further use for SAF production or the jet fuel production. Okay, just changing gears. If we were to look at this from an Indian scenario, whatever we are showing here is coming from Deloitte's report. So what we see here is, in India, today's market, from an ATF production perspective, 50% of ATF is being exported, which constitutes about 3% of the global demand for SAF. Okay, sorry, it is not SAF, it is ATF today. So this is about 3% of the global demand. And if we were to project this with whatever our chair just now pointed out, and also Honorable Minister yesterday pointed, like if we were to go with a 5% indicative blending by 2030, this translates to easily 80 kMTA of SAF requirement in Indian market. But if we were to just focus on this particular market, we are playing in a much smaller domain, I would say. So the way that we are looking at Indian producers in this case is why India is not a producer for a world on the SAF front. There are two big drivers why India can invest more on the SAF production. Number one, we can be very easily cost competitive if we were to compare against our APAC competitors. Okay, this is very well proven on the green hydrogen front. So there is no brainer that even in the SAF space, India is going to lead in terms of cash cost of production. So this is one of the biggest levers that we have. And if we were to extend this further, the proximity to the major hub of European Union is going to help us a lot in the global play on SAF. So with this demand, what we wanted you to look at is a complete portfolio of solution that Honeywell UOP can offer in this space. Okay, so to begin with, the first and the foremost, which is readily being off-taken in the industry right now, is the HEFA pathway, which uses FOGs, basically fatty acids, oils, and greases. So any of these feeds can be processed through UOP's eco-fining process or the UOP renewable jet fuel process to make SAF. And if you want to use existing refinery assets, we can always go for co-processing, either through a hydrocracking pathway, which is UOP's union finding or unicracking pathway, or we can take it through the FCC pathway. Both of these routes will help us produce partially renewable fuel. It could be the kerosene or it could be the diesel. Okay. Leaving all this, if we were to go into the next gen market, so that is where biomass, MSW, and ultimately the CO2. So these being feedstock, these being used as feedstock is going to drive the market beyond 2030 and 2040s. So for addressing these particular feedstock, UOP have our own technology on RTP, which is a pyrolysis process, which could be the pyrolysis oil produced will be upgraded using hydrotreating to produce SAF, or else the two niche pathways. Either we can go with methanol pathway. In this particular pathway, any of those feed material, be it biomass, MSW, or the carbon dioxide, is going to be converted into an intermediary methanol, and this methanol will ultimately be converted into SAF. And the competing pathway for this is the Fischer-Tropsch pathway. So the same feed material could be converted into an FT crude and then upgraded into SAF-rich material. So for both these processes or both these pathways, UOP does offer our e-fining process for methanol to jet conversion and Fischer-Tropsch with FT unicracking process for the Fischer-Tropsch pathway. And on the ethanol space, UOP does have our ethanol to jet process, which would convert the ethanol into SAF-rich material. So this is a complete gamut of process technologies which UOP offer in the SAF space. Now, I will take you a bit more deeper into the Fischer-Tropsch pathway, right? So this is how an overall complex of a Fischer-Tropsch pathway would look like. So be it any feed, be it waste biomass, municipal solid waste, or gas, biogas, landfill gas, CO2, the first and the foremost step is we need to convert this into a synthesis gas, right? So generating syngas is the first step. And depending upon the feed that we are processing, the quantity of contaminants that will be in this syngas varies, and hence this needs further treatment to remove all those contaminants. Once the syngas is conditioned, now we will pass this through a Fischer-Tropsch building block, which is going to convert this syngas material into a Fischer-Tropsch crude, and ultimately this Fischer-Tropsch crude has to be cracked back to put all the molecules in the right space, which is less than C18 range molecules, to meet the ultimate SAF product requirement. Right? And the another major advantage of this particular process is this gives a flexibility either for us to operate the unit in SAF mode, or if there is a need, we could do diesel production, and if there is a need, we can also do base oil production. So this is a very high level overview on the SAF pathway. And from there, if we were to move into UOP's particular offering, so UOP has FT unicracking technology, which takes in feed from the Fischer-Tropsch process, which is nothing but the FT liquids and waxes. So this material would need to be cracked, as I said, to less than C18 range material. The unfortunate problem, and which presents a bigger opportunity, is this. The FT material is highly paraffinic, and once we crack it, yes, very good material to meet the ATF range, but the problem is this will not meet the freeze point requirement. And hence we need to go for the isomerization step. So together with hydrocracking and isomerization, we would ultimately meet the SAF product specification as per ASTM D7566, right? Like any other cracking process, this cracking process would also generate, I would say, byproducts, the off gases and naphtha. If there is an offtake, well and good. So this can be sold in the market, but primarily we would aim to reduce this particular byproduct material. And in the eventual scenario where we will be left with some amount of this byproduct material, that is where we talk about the carbon efficiency, okay? So the moment this naphtha and off gases are let out of the process, that much amount of carbon is lost, not in the form of SAF. So the carbon efficiency of the process is going to be less. So during this scenario, we would try to integrate all this byproduct carbon material back through a recycle reforming and generate more syngas. And ultimately, if you look at a SAF complex, with all different feed material that we start with, we'll ultimately make just one product, which is SAF, going out of the unit. So this means eventually, my overall process carbon efficiency is going to be very high in the order of 90 to 95%. Okay, so that is one of the biggest asserts and advantage of this particular pathway. Okay, So having talked about the technology in itself, yes, everybody in this hall will know that these are technologies which is there in the chemical engineering domain for many, many years. However, the systems and the market and the industry has progressed far ahead. These are not just the paper technologies. People have started investing in it. So this is just a glimpse of what UOP has done in this particular domain. We have 3 distinct customers and 3 distinct licenses sold in the recent past, in the last 2 years. So we have one unit, DG Fuels in USA, who are converting biomass material through gasification route and taking the FT pathway to produce SAF, and it is a 13,000 barrels a day unit. And a much smaller unit in Uruguay. So in here, it is a reforming pathway combined with FT to take it into SAF. Basically, the feed here is a biogas coming from dairy farm. Okay? And the third distinct license that UOP has sold is for USA Bioenergy. So this is once again a gasification pathway and FT to take it into SAF. And this is a 4,700 barrels a day unit. So these are just some examples which we wanted to quote you that this market is actually progressing. But before we get into selection of particular pathway, we wanted you to be aware it is not just a single pathway. There are multiple competing pathways available in the industry, right? So one comparable technology or comparable pathway to Fischer-Tropsch is methanol. So each one of these pathway has its own unique advantages, and we need to do this detailed analysis before we settle on a particular pathway for our ultimate project. So just to quote one example, if you were to look at eSAF, probably the methanol pathway is better. But if you want to do a biosaf, then Fischer-Tropsch pathway would be better. Okay? And if you want to adopt a hub and spoke model, because these are pathways which is dependent on the feed source, which is not available readily in single source. So we need to collect it from multiple sources. So depending upon our feed source availability and the location, we can go for a hub and spoke model. And in such hub and spoke model, what is our giveaway? Maybe a methanol pathway is better, but the giveaway is how much my capex and opex and ultimately cash cost of production is going to be. So this is a parameter which need to be evaluated before we settle on a particular pathway. And also the product flexibility. Should I just focus on SAF, or should we have the flexibility of going for a base oil as well? So if we have product flexibility requirement, then a particular pathway is suited better. Okay, and with all this background, I just wanted you to introduce, and this is my last slide, sir. We have an industry collaboration between Honeywell UOP and Johnson Matthey. This is a non-exclusive collaboration where we are working together to ease the burden of the ultimate end user here, people like you, the customers, the refiners. So the people who involved in project development knows this very well. It is not a simple task to coordinate with multiple licenses to get the project going. So from that perspective, UOP and Johnson Matthey has joined hands together, and we are offering end-to-end solution right from a syngas production all the way either through methanol pathway or the Fischer-Tropsch pathway for the production of SAF. So we have Johnson Matthey's FT cans technology, which is the Fischer-Tropsch technology, and UOP's FT unicracking for upgrading the Fischer-Tropsch crude into the SAF range material. And if we were to start with CO2 as our feed material, Johnson Matthey's Hycogen technology along with FT cans technology would help us together with UOP's FT unicracking. And if we were to talk about the methanol pathway, yes, once again, Johnson Matthey's Emerald technology with UOP's e-finding process will help us meet the end product requirement. So the key takeaway here is we are trying to provide you with a single stop solution. It all depends on what feed you have and what is the market product target requirement that you wanted to target. Based on that, we can help you with evaluating the multiple pathways and settling on the best pathway that is suited for each and individual customer. By this, we don't want to be technology. We certainly want to be technology agnostic. We can evaluate everything for you and come up with the best solution that suits your requirement. And thank you very much for your time and listening.
Thank you, Mr. Durai. That was a very insightful presentation and very futuristic pathways for the SAF community. Thank you so much. Now I invite Mr. Craig Harris from Velocis for his presentation on meeting SAF demand from waste to SAF and e-production. So please welcome Mr. Wiggs.
Good afternoon, everyone. I'd just like to introduce myself. I'm Craig Harris. I'm lead technical sales for Velocys, an advanced Fischer-Tropsch licensing provider. Today, I'm going to talk about a topic which is at the intersection of the climate, innovation, and aviation growth. I'm going to touch a little bit on the current SAF opportunity in India, look at various pathways, and then look how Velocys is uniquely positioned to help India meet its goals of building a scalable, sustainable aviation sector. So, as mentioned by the previous speaker, India has aligned itself with some realistic goals to produce 1% of SAF for international flights by 2027, increasing to 5% by 2030. All of this is aligned with the overall framework in India to achieve self-reliance in 2047 and net zero by 2070. Currently, the market is dominated by HEFA. This is largely due to HEFA projects having an acceptable technology risk to investors. This is because HEFA uses mature technologies that already exist in refining and adapting them to the production of SAF via HEFA, and HEFA projects are profitable. However, as you can see here, the HEFA demand, it builds and dominates the market between now and 2030. But from 2030 to 2035, the demand anticipated for SAF globally falls short by 23 million tons per year. And so this gap needs to be addressed by second generation SAF pathways such as Fischer-Tropsch. As these projects take a long time to develop, so we're now at 2025 moving into 2026, these projects need to be starting to move through the feasibility stages now. We cannot wait until 2030 in order to meet this demand. So India has huge potential for SAF with abundance of available feedstock that can be converted to SAF. So you've got 750 million tons of biomass available, 230 million tons of surplus agricultural residue. Indigenous SAF has been explored already with the use in sugarcane, molasses, bagasse, and maize. The estimated SAF potential in India is in excess of 19 to 24 million tons per year. So as you can see, there's a huge opportunity here. I just want to highlight where Fischer-Tropsch fits into the production of SAF. So on this slide, you can see there's three main pathways. So at the top there, we have biogas to fuels. So in the biogas to fuels, you take a sustainably generated biogas, for example, landfill gas, which is cleaned up. That is then reformed into synthesis gas, so a combination of CO and H2, which needs to then be conditioned to meet the spec of a roughly 2-to-1 ratio of hydrogen to CO for the Fischer-Tropsch synthesis path. The synthesis gas is then reformed into Fischer-Tropsch liquids, which are then upgraded to SAF by cracking and isomerization. Second to that, we have the solid waste pathway. In this pathway, you take solid waste, which is then gasified at high temperatures to produce syngas. This requires some cleanup to get it on spec, such as the removal of contaminants and adjustment of the hydrogen to CO ratio. This again leads into the same downstream processing through the FT synthesis and then product upgrading. And then finally, you have PTL. And PTL uses green electrons to produce hydrogen from the electrolysis of water. This is then combined with CO formed from the conversion of CO2 from biogenic sources into CO, which is then again generated into Fischer-Tropsch liquids through the Fischer-Tropsch synthesis process. I just want to touch a little bit on the comparable pathway of alcohol to jet and just highlight how that pathway is formed and what processes are involved. what you'll see on the right there is what everyone sees as the traditional A to J process, showing the dehydration, the agglomerization, hydrogenation, and fractionation from alcohols into SAF. But I just want to highlight that that is not the only pathway. The only process is required. You need to generate the ethanol originally. So as you can see on the left there, there's many different processes. So for example, gasification, catalytic conversion, reforming, and methanol synthesis, all required there to produce the alcohol required on the A to J route. So I just want to highlight that it's not just the A to J process. This process takes as many, if not more, processes than the FT pathway. So another advantage of the FT is that it's already a proven and the screen's not. Sorry, my screen's updating here, but that one's not.
Can somebody come and help us?
Just a moment, so we'll get someone to.
Okay.
Sorry for a small tech glitch. Hope we resort it soon.
Okay. Okay, I just wanted to highlight that FT is an already approved and certified fuel, unlike some other pathways which are still pending their certification. Now moving on to how Velocis can help. So Velocis is the combination of two companies. So it was formed from Oxford Catalysts, an Oxford University spin-out that had a superactive catalyst, and Velocis, a reactor supplier that had a reactor with high heat removal microchannel reactor. These two combined to form a reactor that was able to utilize the superactive catalyst with the high heat removal to form a compact chemistry and lower the costs. Velocis' micro FTL solution includes everything required for project developers: an FT license, a process design package, proprietary catalysts, automated controls, and FT Island design services. You'll see here in the center of the picture, we've got what's at the center of the process is the Velocis microchannel reactor. This takes syngas, converts it into Fischer-Tropsch liquids, which is then separated to remove the tails gas such that it can be recirculated to improve the efficiency of the unit. There are three distinct differentiators for Velocis: a superactive catalyst, which delivers more yield for a smaller throughput and superior economics; proven FT technology, which delivers the highest TRL in the renewable fuel space; and standard reactors and modular design, which reduce project costs, risks, and delivery times. So superactive catalyst. So what does this mean? This means that Velocis reactors are many times more productive than comparable conventional fixed bed and slurry bed reactors. This enables greater yields for less catalysts, less space, and ultimately reduces footprint and capex costs while still delivering superior production. Velocity's high single pass conversion allows us to have industry-leading overall CO conversion across our unit of over 96%. What this means is that for the same syngas feed, we produce more FT liquids, thus reducing the need for expensive recycles to convert unconverted CO and methane into additional syngas. This enables us to convert more of the carbon monoxide into precious C5+ liquids. And this delivers a potential for increased revenue and greater MPV in the order of 10 to 50%. Micro FTL technology is piloted, proven, and commercial. We have over 300,000 hours of on-stream lab testing. This is equivalent of 34+ years of lab runs. Additionally to that, we've piloted our plant, integrated it under harsh conditions, receiving syngas from a gasifier, enabling us to test our reactors in harsh conditions and to prove its resilience to varying feeds. And finally, we were able to demonstrate our technology on commercial scale on the NVIA Energy Oklahoma plant, which was a landfill gas to fuels plant, which utilized 2 of Velocity's commercial reactors, producing 250 barrels per day of renewable fuel production and 6,000+ hours of cumulative operation across 2 commercial scale reactors. We were also involved in a demonstration in coordination with Toyo and Nido in Japan, in which our fuel generated from our unit formed part of the first commercial flight using SAF from wood chips in 2021 between Tokyo and Sapporo. The microchannel reactor scales up using a proven strategy. From the lab through to the pilot and the commercial, we use the same dimensions. What that means is that the results gained during our lab testing and through the demos are very representative for the commercial scale, and it scales up in a linear and predictable fashion, reducing risk. What you can see here is our commercial size reactor. It's formed by 4 cores of alternating process and cooling channels. In the process channel, we have our catalyst packed in there where syngas flows down and out the bottom flows FT liquids. This is cooled by microchannels where boiler feed water is fed through and partially vaporized to remove the heat. This intimate design allows us to reduce hotspots and improve the selectivity and control of our reactor and manage the superactive catalyst. Velocity offers a flexible solution. We have smaller single core reactors suitable for 30 to 50 barrels per day of FT liquid production. And then we have a larger 4-core commercial reactor for capacities up to 200 barrels per day. This is then combined together in trains to scale up and to scale down to any of our customers' needs for their desired projects. Here we have our reactors being installed in the NVIA location. As you can see, they're very small, very compact, easy to transport and easy to install. This enables us to deliver our reactors in a distributed manner where the source of syngas is to provide FT liquids where it's needed. Velocity's FT licensing model is taking off. Recently, we've announced our license being selected as preferred FT licenser for the HICC project in Uruguay, which is converting dairy-derived biogas into SAF via HICC's proprietary reforming technology. Additional to that, we're partnered with NextChem and their advanced gasification process for the waste to fuels project in Imminent, El Tauto in the UK. We're also continuing our relationship with Nido and Toyo to continue the advancement of SAF projects in Japan, and we have a strategic partnership with Sekisui, an advanced CO2 to CO technology to produce highly efficient power to liquids. Post-HEFA, FT is your highest TRL commercially proven pathway to SAF, and Velocys is at the forefront of this. We've demonstrated our unit across the world with thousands of hours of commercial demonstration, piloted and lab testing. Velocys is ready today to help India meet its SAF demand through second generation, through technology licensing, FT reactor supply and catalyst supply. Thank you.
Thank you, Chris. That was a very innovative technology presentation and innovative technology emerging in the SAF field. Thank you, Chris, for sharing it with us. Next speaker for us today is Mr. Raju Chopra from Topshow. And I invite Mr. Raju to present his paper on most optimal pathways for production of SAF. Manish? Oh, Manish is. Okay, Manish, sorry. Manish and Raju together from Topshow. Okay. Thanks, Manish. Sorry.
Am I audible? Great. Thanks a lot, and I would like first of all like to thank CHT, respected chair, co-chair, ladies and gentlemen. Today I am here to present Topshow's portfolio in SAF. Yeah, so this is the major agenda for today. I'll cover a bit on trends, regulations, pathways, then move on to various production routes, HEFA, followed by co-processing, Fischer Tropsch route, and alcohol to jet, some commercial references, and client testimonial. Just a bit about Topshow. Topshow is a 80-year-old company and it's a world leader in energy transition. Every third molecule in renewable diesel and SAF operating in the globe is licensed by Topshow. Another significant aspect is 9% of the revenue is infused into R&D, which is what makes Topshow the world leader in energy transition space. This company is headquartered in Denmark and has offices all across the globe. We see that the trend of SAF has picked up from 2020 onwards. As on 24, we see a global operating capacity of 5 million tons. The traded volumes have also increased. Bulk of it is served by the Europe and US currently, but other countries are gaining momentum. As per IATA, in order to become net zero by 2050, the biggest contributor will be SAF. Of course, other contributors would be improvement in the existing aircraft engines, but SAF will pave the way, making the biggest contribution at 65%. So this is what makes SAF so special. Regulations and mandates are the driving force behind SAF deployment. Today, we see various countries have come up with various norms and regulations. Just for example, European Union, they have started already in 25 with 2% SAF and steadily growing up to 70% by 2050. An interesting thing to observe is E-Jet will also be a part of SAF, and they have defined the percentages of E-Jet also as it moves forward. USA has an aspiration to have 3 billion gallons of SAF by 2030 and 35 billion gallons of SAF by 2050. UK and Canada are also following suit. Again, we are capturing trends of some of the other countries, but I'll focus on India as also shown by the previous speakers. India is a signatory to CORSIA, 1% in 2027 and 2% in 2028 for international flights. So we can see that Indian refiners are really moving ahead and trying to implement SAF plants. The various pathways to SAF is highlighted over here. So mainly there are two pathways. D7566 is for standalone SAF, and towards the right you can see the blending limits for each. TOPSO is present in three of them, which is highlighted on the screen: FT SPK, HEFA SPK, and ATJ SPK. SPK, synthetic paraffinic kerosene, is a type of SAF. So there are various pathways, different names. TOPSO is there in FT, HEFA, and ATJ. Towards the bottom, we see co-processing also has been passed by ASTM under D1655, in which the maximum blending limit as on date is 5%, which is expected to steadily grow as we move ahead. This is a TOPSO's technology portfolio. On the top, you would see the various fuels. So we start with liquid fuels, virgin oils, waste oils like used cooking oil, animal fat. It needs to have some pre-treatment before it enters the hydroflex unit, and which is a hydroprocessing unit, and we get HEFA SPK out of it. As we move to the right, we can also use solid biomass, tires, and plastic waste. There are different pre-treatment methods like pyrolysis, hydrothermal liquefaction, gasification, from where we get syngas. Again, it goes to G2L plant where the gas is converted to liquid. We have a collaboration with Sasol for that, and Raju will be covering that in the next slides. Another interesting thing is e-fuels. Basically, E means using renewable electricity. So the water will be electrolyzed to get hydrogen, and along with captured CO2 will be converted into syngas and go into a G2L plant. So these are the few technologies that TOPSO has in its portfolio for SAF. I'll quickly cover a bit into the feedstock. So the feedstock, whether it is used cooking oil, animal fat, pea fat, palm stearin, they are all triglyceride molecules having a propane backbone, which will be removed during the reaction. There is a HDO or hydrodeoxygenation reaction. So the oxygen is removed in form of H2O or CO2. What we get is paraffin. It does not meet the freeze point, so we need to isomerize it. We have a dewaxing catalyst for it. The product we get is HVO or renewable diesel. Now for SAF, this needs to be cracked. So there is another step, endpoint reduction, and final product SAF is obtained. There are two pathways to get to SAF. In the HDO section, it is either HDO route or DCO route. In HDO route, water is produced from the oxygen molecule, while in DCO, it is CO2 which is produced. So if CO2 is produced, it will lead to loss of yield. So we prefer to go through the HDO route, and TOPSO has a selective HDO catalyst for that. Here you can see the hydrogen is used up in HDO, seems more, but in DCO route, the CO2 produced will again go into a reverse water gas reaction and finally end up using 19 moles of hydrogen. So even hydrogen consumption wise, HDO is preferable. A bit into catalyst, TOPSO has an excellent phosphorus guard TK3000. Phosphorus being the main contaminant in renewables. Topso also has a DVAX, robust DVAX catalyst and a highly selective HDO catalyst, which prefers the HDO route. If we go into the process, there can be two modes, SAR mode and sweet mode. The only difference being in sweet mode, the SAR gases will be removed prior to the feedstock going into the DVAX reactor. Of course, sweet mode can be a bit more on capex, but it gives higher yields, so NVA comes out to be better. The takeaway is with Topso technology, you have the full flexibility whether you want to go into 100% renewable diesel mode or 100% SAF mode or anything in between. Topso has the solution for you. A quick look into co-processing. So you want to use the existing fossil unit. We do have something known as co-processing. It's a ASTM certified method. 5 volume% renewable feed can be used along with 95% fossil feed to get SAF. This is also certified under D1655, same as the ATF. What we try to do is do a catalyst reload in the existing reactor. So the top has HDO, HDS catalyst and the bottom has dewaxing catalyst. We are glad to inform that IOCL has shortlisted us for co-processing method in its Panipat unit. I'll now invite Raju on stage to cover GTL. Thank you.
Check. Hello, check. Can you hear me? Am I audible? Thank you very much. Good evening. And I'm going to talk about G2L technology. To start with, this is actually unique single point responsibility with Sasol. We together with Sasol can offer the complete solution. And this is nothing but it is actually we need a green hydrogen, we need CO2, and it goes to the E-react or reverse water gas shift, followed by the Fischer-Tropsch, where this low temperature Fischer-Tropsch reaction takes place, and then it is basically done in the slurry reactor that is a cobalt-based catalyst. And here we try to maximize the yield of the SAF in terms of FT-wax. Then this FT-wax goes to the hydrocracking, which is a conventional hydrocracking. And here we crack the molecule and makes SAF molecules, and we can get as high as 82% SAF by this process. Going forward, I just want to highlight here is that it's very, very important that we utilize a innovative technology module, integrate this solution. And in this particular slide, you can see that what are the undesired product, which is gas, naphtha, lighten. From the hydroprocessing unit, it can go back to the reverse water gas shift or what you call E-react, and then it can make more syngas. So which means that we are fully utilizing this process, increasing the process efficiency. And you can see this way we can increase the carbon efficiency by more than 95%, hydrogen efficiency that we can use more than 97% of the theoretical hydrogen. Product efficiency, this product is ASTM certified. Electricity efficiency is actually electricity uses is reduced by 15%. And you can see here the yield of SAF can be 100%. So I think that is a unique part. And further going forward, I wish to mention here that we have a SOEC solid oxide electrolysis cell. This is Topso's high temperature electrolyzer, which is much more efficient as compared to the alkaline and PEM electrolyzer. So which means that if we integrate this particular process or block into the process, then this block can further enhance the, the efficiency of the system. And here on the right-hand side, bottom, you can see the further electricity consumption reduced by 33%. So I think it's again reducing the levelized cost of hydrogen. And I'm happy to announce that we are going to inaugurate this factory of SOEC by tomorrow, which is 500 megawatt capacity in Denmark. Coming to the ATJ route, and we are happy to announce that we are very close to kind of, we are in advanced stage of development. And the goal of this particular, the process is to maximize the SAF, which means that we are talking about more than 90% of the SAF from this process with minimum capex. And in this particular process, we have a dehydrogenation, oligomerization, followed by the hydrogenation process. And in this particular, we bank upon our selective oligomerization catalyst, proven hydrogenation catalyst, and we try to maximize the SAF yield and reducing the cost of production of SAF. That is a key goal. And you can again see on the right-hand side that we are again able to module e-react. We are able to integrate this and again making the hydrogen. So which means that you can utilize, recycle the undesired product and make the hydrogen and make this process much more efficient. We are quite enthusiastic about it, and our plan is that we are going to be, by end of this year, we are going to complete the process, and maybe we are going to talk to the client. We are already talking to the client globally for this particular process. A little bit about the e-react. I think this is a module. We call it novel technology because this is an electrified reformer. It replaces the conventional reformer, and it can take methane, CO, CS2, hydrogen, and then it can make the syngas. So which means that it can make the syngas and send to the Fischer-Tropsch. Similarly, for ethanol to jet, we'll be using light hydrocarbon, which will be feeding to the e-react, and this e-react will be sending the hydrogen to the process, making it more efficient. As far as commercial experience is concerned, this plant has been already running for more than 3 years now in Foulum, in Denmark. And this has been operated in biogas and making the syngas. So it is ready for kind of commercial operation. We have already sold a license to 3-4 clients worldwide, and we are very excited that this particular module is going to be a game changer technology in energy transition. Coming to the commercial reference, if you see the HEFA, as Manish explained, we have a very thorough experience, and we are proud to mention here that Topsoe is the licensor who has the highest running unit worldwide. We have 79 licenses for HEFA as on date. And we are proud to mention that we have won first 2 projects of HEFA SAF in India. And this, along with that, we have also got the order of first SAF catalyst order that is within NOCL, within National Oil Refinery, that is IOCL, which is going to be started in January 2026. Coming to the FT route, as I said, like we have a technology partner, Sasol, and who has decades of experience in Fischer-Tropsch technology. Topsoe and Sasol has worked for decades, and we have many plants you can see which are running. So this is again a commercial proven step, and we are ready for implementing our commercial. Now coming to the reference, if you see particular slide, we have many plants which are already awarded to Topsoe. I want to highlight 2 plants here. One is 2,000 barrels per day, Arcadia. This project was awarded in 2023, and now FEED is completed. It is under FID. And then second project is in Germany, that is German Space Center. This is 200 barrels per day, and this is going to be commissioned by 2027, where they will be making eSAF from CO2 and green hydrogen. Now maybe last few slides. In overall, of course, as a Topsoe, we can offer these technology as a single point responsibility because we have technology, license, high performance catalyst, equipment, and technical service. And if I see the overall, what are the things which are making the project viable? You need to have a technology which is well proven, licensor who can supply these technology as a single point responsibility. You need logistic, project financing, regulation, offtake agreement, of course, the feedstock. And I want to finish my talk with the very short video, which I am going to play.
Somebody in Topsoe saw a puzzle within our data and said, you better keep an eye on this. You might have trouble down the road. That's unparalleled. My name's Bruce Fleming. I am the CEO of Montana Renewables. We are the largest SAF producer in the Western Hemisphere. I never get tired of saying that. But we're only producing 30 million gallons per year. We're going to increase that dramatically. We think we will be 300 million gallons per year of SAF about 2 years from now. That is 10% of the U.S. Grand SAF Challenge that the White House put out last year. This is a mic drop moment. You know, little Calumet in Great Falls, Montana, 10% in 2 years' time. The way that happened was we started off with a 24,000 barrel a day cat feed hydrotreater. But here's the kicker. We had no way to fill that. So in a very classical study where we said, what can we do with all of this idle capability? We ran into renewable fuel. We'll switch the feedstock to renewable feedstock and rearrange the rest of the refinery accordingly, and that's what we did. So start to finish was 18 months. Most people take 18 months to do the initial study before they actually do any of the work. That's simply signaling what's possible. We systematically and methodically removed every risk component that we could identify and point to. Chief among those was, does the technology work? And the best way to solve that is to select a technology provider with a proven track record, a history of operating units, if not directly relevant, at least immediately transferable. And Topsoe is head and shoulders above its competitors in that regard. The Topsoe Hydroflex catalyst offering was installed in our existing hydrocracker unit. That was a very easy conversion for us. The catalyst works exactly as advertised or better, and we've been very, very pleased with the performance.
Thank you very much. And I wish to say that we are also running many podcasts, and you are welcome to join. And this podcast, a lot of industry player experts are participating, and they share their experience and giving you new perspective. And thank you very much.
Thank you.
Thank you, Raju and Manish. That was an enlightening presentation because SAF doesn't have one option, and he has given us so many options to produce SAF. So hopefully we can reach net zero by 2050. Thank you so much. So our next speaker is Mr. Soumitra Deshmukh from Sulzer Chemtech, USA, and he will be presenting paper on feedstock treatment enabling low-cost production of SAF via co-processing in refineries.
Thank you for the kind words, and welcome everyone for this short presentation on looking at a little bit of different approach, which is pre-treatment approach, and how we can make better SAF with a better treatment approach. Legal disclaimers first. Everybody knows this. No need to talk more about it. Let's get right to the words. Right, but before that, I think most of us in the audience already know who Sulzer is and the Chemtech division within the Sulzer. They are best known for their mass transfer equipments, the trays, the packings that we have in the unit. Most of us are really familiar with all of these things, right? One more business division within the Chemtech is polymer and crystallization, and that's basically where we are looking at, biopolymers like PLA, PEF, PCL, and doing crystallization to improve what can be done with these technologies. A third division within the group, the Chemtech business unit, is the process solution unit, where we are looking at not only some energy efficiency improvement processes, but also looking at license processes where we are looking at SAF, HVO, and that's the range where we're going to talk a little bit about it today. And so with that, a lot has been said about sustainable aviation fuels in the last few minutes, the last few days, in fact, and of course, industry mandates, regulations, policies, everything else drives the SAF adoption. We have heard from the minister yesterday the target for 1%, 3%, 5%, and of course the net zero is very well known in that sense, right? So all of these things, they do exist. And despite 11 pathways being approved by ASTM and being recognized, as many speakers before me said it, not much SAF actually is available on the market today. The amount of SAF produced today is less than 1% of the total jet fuel demand. So these targets we have been talking about, 1%, 3%, 5%, actually need some magic to happen over the next few years. And of course, as my co-speakers earlier represented, core processing is one of the fastest ways to get to that answer. It basically uses existing refinery assets, the existing infrastructure, and basically it helps us get get to the right answer with minimal capex, minimal investments, shorter time span, and less delays. Feedstocks are again very well known: vegetable oils, seed oils, greases, fats, everything that you can take, you can co-process using your existing hydrotreater, and make fuel out of it. So this is the route that everybody knows. Every single refinery in the world does this. Take fossil feedstocks, get to the hydrotreater, make your jet, make your diesel, right? And then what does ASTM tell us about different processing? It says, okay, start with your fats, oils, and greases, do some pre-treatment, do some HEFA hydrotreating, and then what happens? You can actually blend your final jet product directly with the final jet. And that's the 50-50 blend that everybody knows about. The next approach you can take is, okay, well, so let's stop one step short of it, right? So what is the first step that is short of it? Is, okay, before we make your final jet, you can actually stop at the hydrotreating and then send it through your refinery fractionator already. And that is the route where we're looking at co-fractionation. And ASTM says, you know what, you can actually make 24% of the blend stock using this. Now, we can even stop one step even further shorter. Right? We say, okay, just do the pre-treatment first and then take it through your existing infrastructure and get to the final product. And what is that? That's basically our co-feeding. And ASTM says, you know what, you can only do 5% with it. We want to do more and more and more, right? And these limits are set by ASTM committees, the technical representatives there. UK has already made some strides saying, okay, the DEF stand 91 now allows up to 30%. So these limits may grow higher, but who knows? But how do we make the most of what's available to us? And that's where I think the approach that we are talking about is the co-processing approach and the novel treatment approach we want to do with it. The feedstock, everybody knows, they are the fats, oil, greases, they're very similar to each other. They basically are triglycerides. But the interesting part about this is that they have a varying amount of impurities. The different impurities that you have determine the quality of the feedstock, their quantity, their supply, at the end of the day, the pricing of those materials. And everybody knows that we want to buy the cheapest quality feedstock and make the most margin on it, right? So what is how can I maximize my profits? Allowing and choosing a technology that lets you access the feedstock independent of its quality is something unproven, and I think is the most critical answer to solving this piece of the puzzle. So just to give you an idea of what are the impurities that we're talking about, right? These feedstock, of course, have metals, several thousand ppm, phosphorus, another one that has been talked about, chlorides has been talked about, and all of these, the hydrotreaters that we already have installed in our refineries, they have limitations. These are, of course, numbers that are, some generic numbers out there, but each case will be specific. But you get the idea that there are feedstock impurities. The higher the impurity, the lower the cost of the feedstocks, the higher the profit margin. So what we want to do is take the worst quality feedstock and make it into the best quality jet fuel through the existing refinery infrastructure without causing any challenges, without causing any heartburn to the operators and the refining units. So that's where the approach that we are talking about comes in. As of today, most of the conventional pre-treatment option is the physical refining process, doing some water washes, doing some degumming, separation. You somehow manage and coax out a little bit of the phosphorus, a little bit of the metals that is available in that feedstock, and then you can do the oxygen removal step that has been talked about, the isomerization to get to the final product. But what we are seeing is there's another approach which the refiners are, the unit people running the refineries, the operators are much more familiar with, are the refinery unit, like a thermal cracking process, right? So where you can take these fats, oils, and greases, mildly crack them, get some separation done, get the right molecules that we're all already familiar with, and then make your jet and fuel. So let's look into this a little bit more. So that's the concept that we're talking about. Basically, do a light thermal pre-treatment of our feedstock that we have. Of course, you'll make some off gases. And then you follow that up with a mild severity hydrotreating. And what that does is it gives you a pre-processed feed that is very, very similar to the feed that is actually going already into your existing hydrotreater. And that is something that can unlock a lot of the answers to the questions that have been asked with the field of co-processing. So digging a little bit more into what happens into the pre-treatment. So somebody already mentioned, the triglycerides are the molecules that we have here. And analogous to refinery thermal cracking, we are going to use moderate temperatures to get to the right answers, reduce the molecular weight, break the chemical bonds. And what we are going to do is we are going to end up with a smaller subset of molecules. And of course, because it's a cracking process, you're going to have a mixture of paraffins, you're going to have some olefins, you're going to have some aromatics. And I think these are molecules that the refiners already know how to deal with. They don't know how to deal with fatty acids or triglycerides, but paraffins, olefins, aromatics, you give them to us, we know exactly how to deal with them, right? One of the biggest challenges is typically, the phosphate group, the phosphorus, and the oxygen associated with that phosphate group, and the metal that the phosphate group is bound to. And removing that is a very challenging problem for the conventional conventional pretreatment process. So and they rely on purely the hydrophilicity of this particular group to attract it and pull it out, cajole it out of the organic molecule into the aqueous phase, and that's how they remove it. Now, what we are doing with this thermal cracking process is we're giving it a little bit of energy boost to crack that molecule, crack that piece off, and make it easily go into the aqueous phase. And what does that do to us? Here's an example of a 10 kiloton per annum plant that was doing some thermal cracking the way we've described it. We have run the process for DCO, we have run the process for UCO, we have run the process for soy. And some of the impurities that we talked about, the metals content, few hundred ppm, phosphorus, few tens of ppm. The chlorides also in a similar range. And when we get to the product, what do we see? We are able to effectively remove the metals. We are able to effectively remove the phosphorus, so also the chlorides. Now, this is again just with the DCO, soy, and the UCO feeds. And not only that, we have tested feeds which are significantly worse than this. Few thousand ppms of metals, few thousand ppms of phosphorus, and even they can be processed to get to a point where you're looking at less than 10 ppm metals, less than 1 ppm phosphorus, and insignificant amount of chlorides. That's the beauty of the process that we're talking about. And of course, in the process, you're going to make some fatty acids, you're going to make some pionas that we talked about. And these are molecules, again, that are familiar to us. Now, as we go further, right, the next step that was described in the whole process, is, well, you know what, we need to worry about the oxygen that's in the feed. The beauty of the way we have designed the process with the thermal cracking part or the thermal pretreat part is that you can remove a majority of the oxygen. More than half the oxygen is already gone through that process. So now what is happening is you don't need as much hydrogen to remove the molecules that are remaining in that particular feedstock. So this is again a change, a paradigm shift in terms of, okay, how much extra hydrogen do I need to make this work? Right, and then of course we have some free fatty acids left. They will need to be removed, and these oxygen removing steps, they're quite exothermic. They can cause hotspot, they can cause catalyst, they can basically and you also make water in the process, as was talked about, and that's when you need newer catalyst solutions, you need upgraded metallurgy for the reactors, and that can actually add to the cost burden for the project that we are looking at. So that's typically what a conventional hydrotreater revamp would look like, right? But then, because we have already gone through this place where we are saying, okay, what we have is we have already done a thermal cracking step, which I think is, in the absence of a pointer, it's basically that green circle out there with a tiny furnace showing you the thermal cracking step. So that's where the thermal cracking has already happened. So now what we do is basically we say, okay, let's do a mild, low severity hydrotreating step, just enough to remove the oxygen, just enough to get rid of all your fatty acids, so that the feedstock, so that the pretreated material that is made is exactly the paraffins, the small amount of, actually the olefins will also get saturated. A lot of cyclics present, which are again not new to us as refiners in the world. So that feedstock is something that we already know our existing hydrotreaters are already very well familiar with, and it allows us to explore the whole potential of this scheme. And now, because you're already doing something which is a low severity hydroprocessing step, that 5% limit on that fats, oils, and greases actually goes up to 24. So you actually can process a lot more with the existing refinery itself. Right, so that's kind of shifting the way we look. We need to look at the market. We need to look at the technologies and how do I best select my technology to get to the right answer. So a brief case study. few seconds on this, essentially, more or less. Looking at, so if you had a refinery that produces about 20,000 barrels per day, a small, tiny refinery, targeting just, let's not even go to the 24% case, right? Let's just start with the basic 5% per ASTM 1655, something that we all have heard multiple times. And what happens, you do the conventional pretreatment, which is the degumming step. You have a certain make of your certain make of your jet fuel. You make some other feedstocks, and how much can you process through it. Now, without adding any extra capacity, without worrying about the hydrodynamics, without worrying about anything else, what the modified pretreatment approach, which is the thermal pretreatment treatment followed by the mild hydrocracking, what it allows us to do is it allows us to process a little bit more feed and make a lot more product using the same refinery, using the same setup that we already have. So these are, and again, I mean, whatever applies for the SAF case also works for the diesel case. That goes without saying, and that's something for us to just keep that in mind. So with that, just a couple of takeaways from the process is, the co-processing is a solution that refineries want to look at, so that we can actually get to that 1%, 3%, 5% numbers in a short range, allowing us to meet the goals that the governments expect out of us, that the world expects out of us. And of course, technology selection has a strong influence on the economics and the feasibility that we need to look at for the fuels complex. By that, what I mean, can I get to a cheaper feedstock? Can I maximize my profits while still doing what is right for the world? I think that's the answer that we are looking for. And what I hopefully presented to you is that this thermal pretreatment followed by a low severity hydrotreating step actually is an effective enabler to get us to a place where we can start to rapidly adopt the co-processing in our existing hydrotreaters, get to the initial targets first, and then get on to the more complex challenges of how do we get to final net zero answers. So with that, thank you so much for your time and attention, and we'll look forward to your questions or discussions later on once the session is done. Thank you again.
Thank you, Soumitra. That was a very novel presentation on a very critical step in SAF processing, which decides so many things for the technology going forward. Thank you so much. So now I invite Dr. Palak Dugar from Visolis to introduce us with a new molecule unheard of in biorefining.
Thank you for the introduction, and to CHT for the opportunity to participate in the 28th Energy Technology Meet. In today's presentation, I'll talk about Visolis' AeroSAF, which is aromatic sustainable aviation fuel produced via the mevalonate pathway. Am I audible? Visolis is an innovation-driven biotech company based in the Bay Area with a presence in Netherlands and India. It was started in 2012 when there were a handful of companies working on SAF. Since then, SAF has grown dramatically with a projected total market value of approximately $2 billion in 2025 and an expectation to reach $550 billion in 2050. So global government mandates will play a key driving role to reach this 2050 market size projection, similar to how in the 1990s, incentives drove technological innovation for drastically reducing costs, making solar and wind energy commercially viable. Legislative action for SAF is increasing globally, with EU and US leading strong initiatives to create policy technology maps and foster investments. The SAF industry is poised for rapid cost reduction through policy support, production scale-up, and technological advancements. With the global aviation industry consuming over 100 billion gallons of fuel annually, the SAF market presents a massive opportunity. So where does India come into play in this global picture? Over the past 2 days, we've heard a lot of speakers highlight that India sits in a unique and promising position, a true sweet spot, with our strong agricultural base and a well-established ethanol ecosystem. India already has two of its most critical building blocks for SAF. When you combine these strengths with well-designed mandates, India has the potential to become a net exporter of SAF by 2035. These mandates alone are expected to create a domestic supply of $9 billion by 2040, while global demand could reach an astonishing $370 billion. With the capacity to produce 10 to 30 million tons of SAF from domestic resources, India truly has what it takes, the feedstock, the talent, and with Visolis, the technology to position itself as a global leader in SAF. So Visolis's MEV platform, which is short for mevalonolactone, enables dozens of high-performance applications. MEV is made via fermentation using an ethanol yeast, which is programmed to hyperproduce MEV. This is followed by a thermochemical catalytic upgrading of MEV to produce advanced biofuels and chemicals. This pathway is feedstock agnostic and is capable of utilizing feedstocks such as molasses, damaged food grains, as well as 2G feedstocks such as municipal solid waste, agricultural residue, and 3G feedstocks like waste gases. This technology has been specifically demonstrated for the raw materials shown on the screen at a pilot scale. Visolis's patented technology and production pathway for MEV is the precursor to making high purity energy dense fuels and chemicals, offers capex savings as well, since the existing standard equipment from the ethanol industry can be used for brewing. Additionally, MEV is a flexible intermediate, as one can switch from different products just by adjusting the process conditions, giving us both versatility and scalability. So MEV is a liquid with 40% higher density than crude oil, and just like crude oil, it can be shipped globally and can be used to make high volume products. But unlike crude oil, MEV is non-toxic, bio-based, and biodegradable. Out of the dozen end products today, I will focus on SAF, which has the largest immediate opportunity. So SAF, sustainable aviation fuel, SAF is aviation fuel, not SAF. It also called Jet A, is composed of three main types of molecules: linear, cyclic, and aromatics. All of the SAF produced today and sold in the market consists of only linear molecules. In order to meet ASTM specifications and be compatible with existing infrastructure and airplanes, such SAF has to be blended with Petrojet A and is limited to a 50% maximum blending according to the ASTM requirements. Visolis's technology exclusively makes the other molecules, the aromatics and the cyclics, which together we call as AeroSAF. This AeroSAF has many key advantages in terms of improved properties, as well as it's expected to be more cleaner burning due to the absence of polycycloaromatics. This AeroSAF can be blended with other linear SAF to create 100% drop-in replacement for Jet A. So talking about the properties, AeroSAF is better on multiple fronts. It has 12% more dense. It is 12% more dense than HEFA-SAF and Jet A2. It has better cold flow properties due to a lower freeze point. At the same time, it also has a higher flash point, making it safer to handle. Such premium properties can be harnessed via synergistic blending with other SAF and as well as Jet A. So AeroSAF basically forms a very critical component of 100% SAF. While the majority is working to make linear molecules for SAF, Visolis is exclusively producing AeroSAF. With this premium offering, we're already working with marquee customers like the US Department of Defense. And as we scale production, the world moves towards 100% SAF beyond 2050. We need at least 50 million tons of AeroSAF, which will be needed to blend alongside 100 million tons of linear SAF. In total, AeroSAF represents a third of the jet fuel demand globally, which is about 150 million tons. So an assessment of the 100% SAF, which is comprised of 80% HEPA and 20% of the arrow SAF, is shown here. And this 100% SAF is fully compliant with a subset of ASTM properties. The distillation curve on the right, you can see that the 100% SAF mimics the Jet A fuels, which were selected here. Please keep in mind that Jet A also has a very wide range and band of distillation characteristics. We expect this 100% SAF to be fully compliant with the the other properties. Lastly, I would like to touch upon the overall impact potential of Visolis's platform from the perspective of greenhouse gas emissions. With 1G feedstock like grains, our product produces over 70% reduction in greenhouse emissions relative to Petrojet A. With 2G inputs like agri-residues, there's an opportunity to go carbon negative on a life cycle basis due to two main factors. The first, the feedstock-related emissions are minimal, and the feedstock represents renewable carbon that is fixed in the plant matter. The second is that the rubber copolymer that's produced alongside the fuel inside our facility continues to hold on to the renewable carbon. That is, it sequesters the carbon even at end of life, since it's not burnt, and this offsets all processing-related emissions at an 85 to 15 fuel polymer mix, and at a 50 to 50 fuel polymer mix, the entire operation is net carbon negative. So in summary, Visolis SAF is a high-performance fuel essential to a lower emissions future. Thank you for your attention.
Thank you, Palak, for introducing a new molecule. And I hope this will remove the blending requirements for the SAF. Thank you so much. So now I invite our last speaker, Mr. Vashane, to present his paper.
So I would like to use a little bit of stage space. So thank you. So first of all, I would like to thank the fellow speakers for talking about all the advanced pathways to produce SAF. I am going to make your life easy. I am going to talk about something simple and basic. But before I talk about anything, I want to ask one simple question. Please respond me by raising your hand. How many of you love our planet Earth? Okay. The follow-up question, if I ask you to sacrifice something to save planet Earth, how many of you will do? So within 20 minutes, we'll check how many of you will keep your promise. Next question, please hear carefully. How many of you love samosa and chola bhaturas? Guys, please raise your hand. Yesterday, I saw a long queue in front of the samosa parlor, right? During the gala dinner. So please be honest, raise your hand. How many of you love samosas and chola bhaturas? Thank you. We'll come back on this. So about company, Lamas Technology is a technology licensor, and we provide technology for gas processing, refining, petrochemical and polymer, and biofuel technologies. Additionally, we are the supplier of catalyst and proprietary equipments. We also provide digital solutions to all our technologies. When it comes to global footprint, we have a legacy of more than 100 years. We have currently 12 worldwide offices, 4 operating advanced facilities, more than 4,100 patents. When it comes to a technology portfolio, we have a massive portfolio of more than 160 technologies. Next point is very, very critical to understand. When it comes to ethylene, we are #1 in the world. It means more than 50% of the ethylene is being produced using our technology. And why it is important? Because in one of the pathways to produce SAF, ethylene is a critical intermediate step. We'll talk about it. So before we talk about a solution, first let's talk about a problem. So on the left side of the slide, you can see the trend. On the right side, you can see the impact. So the very first trend is more and more people are using flights. It means more consumption of the fuel, more carbon emission. Impact, urgent need for decarbonization. Second is global net zero commitments. It means a massive market for SAF. Third thing is that when it comes to passengers vehicle, you have CNG, you have electric fleet. But unfortunately, when it comes to plane, hydrogen powered vehicle, or hydrogen powered plane or electric fleet are not ready. And it will take decades to be ready. So what is the option? So as per the IATA report, the best option is to go with something which is sustainable. The next point is very, very critical. Looking at the current geopolitical situation, we have to be self-reliant. And our Prime Minister fondly says that we have to be Atmanirbhar in everything. And when it comes to energy security, it becomes even more critical. So it means we need to reduce the crude import. So we have talked about the problem, and now let's talk about the solution. There's a strange thing about SAF. This is the only fuel for which so many pathways have been approved. Currently, there are 11 pathways approved for producing SAF, and almost similar number of pathways are under approval. You know why? Because no single pathway can produce enough SAF which can meet the global demand. Each pathway has its own challenges. So for the ease of understanding, I have condensed 11 pathways into 4 categories. The first category is HEFA. HEFA stands for hydroprocessed ester and fatty acids, where the feedstock is used cooking oil, animal fat, and waste oil. When it comes to technology readiness level, worldwide, all SAF is being produced using HEFA. In terms of economics, the cost of production is low. It doesn't mean the cost of production is lower than the conventional jet fuel. It means the cost of production is lower than other routes. The biggest challenge is feed availability. It means the feed for HEFA competes for other fuel like renewable diesel or some oleochemicals. Well, again, it's a time for next question. If I ask you to sacrifice your samosas and chola bhaturas, how many of you would like to do that? I can see very few people are raising their hands. Guys, I'm sorry to say that we do not have sufficient UCO, used cooking oil, because most of the UCO in India either ends up in samosa or chola bhaturas. And please don't ask me the data source, because this is something which I am telling from my own experience of having a sweet shop, and I know how the economics of samosa and used cooking or chola bhaturas work. Thanks. Since I'm sorry to say that, since you guys are not planning to sacrifice your samosas and chola bhaturas, so we have to move to the next pathway, which is ethanol to jet. So when it comes to ethanol, I should say that it is a alcohol to jet. So there are two alcohol. One is ethanol, another one is isobutanol. Here I will talk about ethanol. So for the ethanol production, the main feedstocks are sugarcane, molasses, waste grain, energy crops, or agriculture residues. After HEFA, this is the only pathways where all steps are commercialized. I'll not talk about TRL number 4, 5, 6. All steps are commercialized. Already, all the steps, all the units are already in operation. When it comes to economics, the cost of production is higher than HEFA, but still comparatively lower than FT and PTL. The biggest challenge is variety of feed. It means variety of feed to produce ethanol. And when that ethanol processes in ethanol to ethylene process, which is the first step, then so many complexities come that we'll talk about in forthcoming slides. And the second critical step is ethanol dehydration process. So worldwide, there's only 1 or 2 plants which are in the operation at a commercial scale. I'm not talking about a small scale or pilot scale or demo scale plant. I'm talking about a commercial scale. So there are only very few plants. So that is one of the biggest challenge. Now you must be thinking that I'm going to ask another question. So if I ask you, how many of you would like to sacrifice your ethanol? Yesterday I saw the response of the people and the happiness on the face of everyone during the gala dinner. And nobody would like to fly a plane with a sad faces where people are sad. So thanks to our government and our farmers that we have sufficient amount of ethanol available, which can drive our car, which can drive our plane, and which can also drive us. So now let's talk about the next route, which is FT Fischer-Tropsch. Our fellow speakers have already talked about it, but I'll take one step back. And you must have seen there were many processes, different steps are involved. I'm going to talk about one more step, which comes before FT. So that step is gasification. Though FT process is pretty old. The FT stands for Fischer-Tropsch, primarily used to produce liquid fuels using coal gasification. But here, coal cannot be used. So we have to use the biomass. And the biggest boon for this process or the pathway is the variety of feed. But unfortunately, the biggest boon becomes the biggest curse for first step of this process, which is gasification. And so far, there is no commercial scale gasifiers available. Second thing, gasification, especially the biomass gasification technology, is very, very feed specific. The moment you try to change the feed, lot of complexities involved. So after the gasification, you get syngas. And for the syngas, one thing is critically important, which is hydrogen to CO ratio. And once you get the syngas, it goes to the FT reactor. So with the variety of feedstock, it is very, very difficult to control the ratio of hydrogen to CO. And then when it goes to the Fischer-Tropsch, to get the Fischer-Tropsch liquid, and then you need a hydrocracking catalyst, then you need an isomerization catalyst, hydroprocessing, fractionation. So these are the different steps involved. When it comes to technology readiness level, the whole process is not commercialized, especially because of the gasification part. Cost of production is high and highly capital intensive unit. The biggest challenge is feed aggregation, as I said. If we talk about any of the world scale unit, it would be very, very difficult to find a single kind of feed available at a single place. And another challenge, as I already said, the complex gasification process. Next is PTL. So PTL stands for power to liquid. Well, this is the perfect route to produce SAF. But unfortunately, something which is perfect may not be practical, at least today. So for this PTL, you need green hydrogen and carbon dioxide. Thanks to our National Green Hydrogen Mission, that we are doing really well, but everybody sitting in this forum already knows that still the cost of hydrogen is green hydrogen is very, very high. Second thing is carbon capture. Though this technology is also very, very old, but it's still not very optimized. And still it is evolving. And especially for PTL route, the carbon that can be captured through direct air capture method, for which the cost of production or cost of capturing the CO2 the cost of capturing the CO2 is as high as $500 to $600 per metric ton. The second route is biogenic CO2 capture, but there are issues related to the economies of scale. So once you have the carbon dioxide, once you have the green hydrogen, then the next magical step of reverse water gas shift reaction. Though this technology is also very, very old, but it has always remained either in lab or literature. And there's a reason for that. Because with reverse water gas shift reactor, you get syngas. And there are alternate methods available, like reforming or gasification, through which you can get the syngas. And this reaction is highly endothermic. So it means you need high temperature. At the same time, it's a catalytic process. So you need to increase the temperature as high as 700 to 800 degrees centigrade. So you need a robust catalyst which can sustain such a high temperature, at the same time, such a good metallurgy which can withstand such a high temperature. After the syngas, you need FT, the same pathway that we talked about. It means Fischer-Tropsch, hydrocracker, catalyst, isomerization catalyst, and then fractionation. So the biggest challenge is carbon capture process and the complex reverse water gas shift reactor. So I have talked about all those pathways, and another question that could be coming into your mind, what is best for India? I know you will not easily convince. So here are 4 categories through which you can judge on your own which is the best pathway for India to produce SAF. The first thing is strategic advantage. It means the feedstock. We have already concluded that we don't have a sufficient feedstock available for the UCO. Then next is what? We have existing ethanol infrastructure. And economics teaches us if we have something already available, we should try to utilize it. The third is the self-reliance. And as I already explained, and our Prime Minister keeps on saying about being self-reliant. So if you have the feedstock available in the country, then that is going to best for any of the pathway. When it comes to technology, as I said, all steps are commercialized, and it can be easily bolt on with ethanol plant. Additionally, it also produces byproducts like renewable diesel, and the unit can be designed in a flexible manner so that if you want to produce max SAF, you can produce or operate the unit in the max SAF mode or maybe in the max diesel mode. When it comes to economic and export potential, currently we per metric ton of jet fuel. And out of 18 million metric ton, we export almost more than 50%. It means more than 9 to 10 million metric ton we export currently. So similar thing we can do here with SAF. When it comes to social policy impact, huge investment would be needed to create a SAF ecosystem. It means job creation, boost in the farmer income. Now you must be thinking, after talking about so many pathways, what Lummus is going to offer. So Lummus, with our partner Chevron, we have a joint venture called Chevron Lummus Global. So with Chevron Lummus Global, we have a technology called IsoTerra, which is based on HEFA. So with HEFA route, we can process any kind of HEFA feedstocks to produce renewable diesel or SAF. When it comes to ethanol to jet, I talked about a critical challenge for ethanol to jet, which was ethanol dehydration process. And I'm glad to inform you that Lummus is the only licensor with a commercial scale ethanol to ethylene unit, which is in the operation in Brazil for more than 10 years. The capacity of the unit is 260 KTA ethylene production. Such a big unit. And I would candidly admit a fact that that unit has gone through its own learning curve, or it has gone through its own rough patches. The faults which we could not envisage during the design phase came up when the plant was in operation. Since the plant is in operation for last 10 years, all those things have been fixed to ensure that the plant can complete its on-stream factor. Next is dimerization and oligomerization. So after ethylene is dimerized to butene, and it is oligomerized to oligomer product. So here there's an important step, there's an important point to understand. The oligomer produced from this process is highly isoolefinic. It means you do not need hydrocracking catalyst, you do not need isomerization catalyst. Directly you can hydroprocess it, and the quantity of hydrogen needed is very, very minimum. So overall, when it comes to integrated unit, it is highly optimized for low capex, low OPEX, and low CO2 emission. Well, when it comes to ethanol, literally sky is the limit. You can set up a whole biorefinery around ethanol, or biorefinery come petrochemical or polymer complex. So when it comes to refineries are mainly built for 3 fuels, which is one is gasoline, another one is diesel, and third one is the jet fuel. And we have already seen that ethanol is being used as a blending component. The second thing is that with the jet process, you are getting jet fuel and renewable diesel. And additionally, you can also produce alkylate. When it comes to petrochemical complex, since as a process of ethanol to jet, ethanol to ethylene, you are already getting, and with a technology called OCT, you can get propylene. So once you have the bioethylene and biopropylene, you can produce all the polymers, whether it is biopolymers, whether it is polypropylene or propylene-based any other polymer, and everything will be called a bio-based polymer or bio-based petrochemical. Well, this is the second last slide. The next question that could be coming to your mind, how to make the project bankable. So I'll just talk about the very first point. Remaining points already fellow speakers have talked about. The proven technology pathway. It is very, very important before you decide to go with any of the technology partner, you understand that all the steps are commercialized. And when it comes to ethanol to jet, I'm giving you one example. All alcohols are not same. So being one of the leading licensor for methanol to olefins or ethanol to ethylene, I would like to highlight a point. The chemistry and the process for methanol to olefin is entirely different from ethanol to ethylene. So for each step, we have to be very, very careful. And as a producer or as a producer of SAF, your expectation should be to ask the licensor to facilitate a visit to the reference unit so that you can see how the unit is in operation. So that is the critical point that should be kept in the mind while you are deciding your technology partner. And other things we have already, other fellow speakers have already talked about. So this is the last slide, summary and the path forward. HEFA is definitely a short-term solution. And due to high capex and technology readiness level challenges, Fisher troughs and PTL routes, definitely these technologies can be an option for the future, probably beyond 2045 or beyond. Ethanol to jet is India's fast track to sustainable aviation. And Lummus is here to offer Isoterra, it means HEFA-based, or ethanol to jet technology. And the last but not the least, as our CEO famously, oftenly says that, never leave the customers. Trust me, as a licensor, we will not be associated with you with up to the basic engineering package, but we will be associated with you up to the commissioning and beyond. With this, thanks a lot. Thanks a lot for your patience listening. I'm available for any of the question answers, and also we have a booth here, and we will be available for tomorrow. You can come to the booth and ask about these technologies or maybe other 158 technologies. Thank you. Thanks a lot.
So thank you very much for very nice presentation. And you also talked about samosas and chola bhaturas, which must have brought water into the mouth so many who like it. Thank you very much. So we have almost, overshot the time by about 7-8 minutes, but still we'll take 2 or 3 questions if some people have some pressing. Please raise your hand, direct the question to someone who is, please let us know whom you are asking the question.
Myself, R.M. Thakur, working with CST. I have few questions with Suljar, Mr. Deshmukh.
Okay.
Actually, you have given a right solution for co-processing of biofeed. Actually, during this thermal processing, you can reduce the metals, no problem. It's good that you have suggested this solution. How do you take care of formation of coke during this thermal process? And how do you take care of formation of olefins? Because formation of olefins will consume more hydrogen in the next step. So how do you take care? Can you explain? I would like to know.
It's on. You
now it's on. Okay. I think those are really valid points that you make, right? So you are going to use some oxygen, you are going to use some hydrogen to saturate the olefins that you make. You are going to have some olefins that you made, but these are again molecules that you really know in the refinery. You're not dealing with oxygen that is removed inside a hydrotreating reactor where you have to worry about the exothermicity, where you have to worry about the corrosion due to the acid formation, things like that, right? So it's a lesser known evil in that sense, honestly. to say with you. In terms of the formation of the coke, I think that's something that is very manageable. You know, you design the right conditions, you operate. I mean, you design it right based on the right flow regimes, things like that. You know, this is not the forum to share the details on it. But of course, you and I can have a chat right after, and we can make sure that the people who are running the units downstream are very comfortable with what we offer. That's what I think you're getting out to, right?
Okay, we'll have one-to-one meeting. Thank you.
Absolutely.
There is a question from, please pass on the mic here. Yeah.
Good evening. Myself, R.K. Jha. I'm former Executive Director and Refinery Head with IOCL Badauni Refinery. Presently, I'm working as a Senior Vice President, Green Initiative with Himadri Specialty Chemicals Limited. It's a very generic question. My generic question to all the panelists, you have given so many methods, HIFA, FT, and power to, SAF. As a panelist, all of you, can you suggest that which methods would be adopted? Because as a Himadri, we are very keen in moving forward to implement the SAP production. So kindly suggest.
I don't know who can take it, but I think you want to take it?
Yeah, I can take it, please.
I think Loomis had given all the four type of, summarized the very well, and then had talked about.
Hello.
Anyway, he's.
Yeah, I think I know you are not a refinery, so maybe I cannot recommend you go for co-processing, but I think we have also, I think a lot of my colleague also mentioned about the HEFA is the cheapest route, but the challenge with HEFA is the feedstock availability. And I'm sure like maybe there'll be a feed diversification. A lot of new policies are coming where these UCO will be, preserved and maybe will not be using it multiple times. So maybe HEFA is the co-processing is the cheapest, followed by HEFA, 100%, that is a grassroots unit, the new unit. Then we see, we could see if we compare, feedstock is important. So maybe we could see if it is ethanol is available, maybe ethanol to jet could be, and then followed by the Fischer-Tropsch. But there could be, if you have a CO2 availability, then we could also see methanol to jet is a very attractive, and maybe we can say FT route is also quite competitive. But if I say you have to put a gasification process, then it is very, very cumbersome.
I think he's smiling. It looks like he will get further confused. I think anyone else would also like, but I think it depends on what kind of feedstock you have, what kind of existing infrastructure you have. Whether you have ethanol available, then you can take that ethanol to jet route. If you have expertise in biomass gasification, maybe you can pick up that route. So there are multiple options, So I think there is no single answer to any particular question. Any other question?
Maybe a quick side comment on this, right? How many million rupees do you have to invest? I think because they all said each one has a different price tag to it.
That's what I was wondering, that investment has not been talked about and the cost of the final product by various technologies has not been talked about by any of the presenters. So it's an upcoming technology, as was said, that is only 1% of SAF which is available at this point of time. So I think it's a difficult question. So any other question?
Yeah, one last question. Yes, sir.
I'm Vinay Amte from Reliance Industries. My question is to Velocis speaker. You mentioned that in power to liquid, about 90%, 90+% activity towards a liquid hydrocarbon. So out of this, how much is the distribution of naphtha, diesel, SAF, and wax?
I think it must be all. Yeah.
So the distribution from the FT liquids, typically you're looking between 75 and 80% to SAF, and then 15 to 17% naphtha, and then the rest made up of LPGs. With the option of recycling the naphtha and the LPGs to further reform to increase the yield of SAF from a given feed.
Okay, but as you mentioned that you are having the reactor with a multi-channel, and moreover you are targeting the conversion of more than 70%. So how you are maintaining the exothermicity of this reaction?
So the 70% is the per pass conversion, but the overall conversion with recycling of, we recycle tails gas back round to the start of our process, so you can achieve upwards of 96% total CO conversion, which leads to around about 90% conversion of CO to liquid hydrocarbons.
Okay, thank you.
So thank you. I think with this, I'd just like to mention that we have learned a lot. In fact, I have also learned during all these presentations. This is a upcoming field. SAF is going to contribute about 65% reduction of CO2 by 2050. That's a good news. But the issue of cost, the cost is, I was looking today in the morning that what are the kind of prices, nobody talked about that, is about globally, this is about 2,000 to 5,000 per ton, is the cost of SAF vis-a-vis the normal aviation fuel, which is available at about $700 to $900 per ton. So there is a large difference. So we have to, fine tune the technologies. We learned that 11 pathways are available, 49 recognized feedstocks are there. Multiple technologies have been talked about, but there are challenges. And if you look at the challenges, first I believe is the cost reduction. Whichever technology we need to go forward to has to reduce the cost. Availability of feedstock for particular technology, once HEFA, as you say, is the cheapest at this point of time. Lumas was mentioning that the FT process is not commercialized. On the other hand, Mr. Chopra mentions that FT process has already been commercialized. So there are, anyway, these are some of the challenges, but cost is an issue. Then supply infrastructure, and where these investments, what kind of investments are required for various kind of technologies also need to be discussed. So with this, I think I would like to thank all my speakers, panelists, and my co-chair also for conducting this session. So, and the audience for patient listening and interacting during this session. So thank you very much. Over to the organizer.
Thank you, Dr. Malhotra. Can I please request for a big round of applause? This session was truly insightful. A deep discussion on SAF. Thank you all. With that, may I please request Dr. R.K. Malhotra to kindly step forward and present mementos to our esteemed speakers for their phenomenal contribution during this session, starting with Mr. Shaktivelan Durai. Thank you so much, sir. May I please request for a round of applause, ladies and gentlemen? We now would like to thank Mr. Craig Harris for his thoughts and expertise that he shared during this session. Not without a round of applause, ladies and gentlemen. Let's keep it coming for all our speakers, because we have truly witnessed excellence and brilliance here on stage. A lot of learnings have come our way, so let's appreciate all of them. Thank you, Mr. Raju Chopra and Mr. Manish Das from Topso. Gentlemen, thank you so much. Thank you. I now request Mr. Siddharth Jain to step forward and present a memento to Mr. Soumitra Deshmukh. Thank you, Dr. Malhotra. Thank you. This was the last session, but I'm sure the energy is still there. So let's keep it coming. An applause celebrating the amazing experts that we have here. Thank you, Mr. Vishal Varshni, for that fantastic presentation, and thank you for sharing your thoughts. And Dr. Palak Dogar, thank you so much, ma'am, for being here. Your active participation is truly appreciated. I now invite Mr. R.K. Jha, former Executive Director, Baroni Refinery IOCL, to join us on the dais and present mementos to our chairpersons for their outstanding contribution in moderating the last technical session for day 2. Dr. R.K. Malhotra, sir, thank you so much for gracing this panel and for sharing your thoughts. And thank you, Mr. Siddharth Chen. A round of applause, please. We cannot get tired of hearing the audience applaud. Trust me, that's the way we feel celebrated here on stage. With that, it's time for a picture. Mr. Jas, sir, kindly remain with us on stage for a picture, a collective picture with all our panelists here on stage, our eminent speakers here on stage, along with our chairpersons. Everybody together for one picture. And of course, that calls for a collective round of applause. Please, everybody, put your hands together as we collectively celebrate the information, the learning, and of course, the thoughts and the insights that were shared during this session. Thank you all once again. On that note, ladies and gentlemen, day 2 of Energy Technology Meet 2025 comes to an end, and what a productive day this has been. In the beginning of the day, I did mention that it's going to be an impactful day, and it has truly been an impactful day for all of us. A lot of expertise, a lot of insights, a lot of thoughts and learnings have come our way. Great day and great way to finish day 2. Well, on that note, day 3 awaits. Tomorrow we will assemble in the same hall at 8:45 a.m. I repeat, at 8:45 a.m. we will be here at the same hall for our technical session. That will be the last day, so let's make the most of it. Let's be here on time and let's ensure that we make the 3rd day of ETM 2025 as well a grand success. Thank you so much for your participation. Thank you for being here. Thank you for your presence. Thank you for your questions. And thank you for your enthusiasm. We will see you all tomorrow. Until then, take care. Have a great evening. My name is Archana Deshmukh, signing off. Good evening and God bless you all. Thank you so much.